Neurosymbolic AI, the third wave. December 16, 2020. CSAI, Arxiv 2012.05876v2. Artur Davila Garces, 1, and Lu is CLAM 2, 1 City, University of London, UK. Adopt Garces at city.ac.uk. 2 Federal University of Rio Grande do Sul, Brazil. luislambacum.org.December. Abstract. Current advances in artificial intelligence AI and machine learning ML have achieved unprecedented impact across research, communities, and industry. Nevertheless, concerns about trust, safety, interpretability, and accountability of AI were raised by influential thinkers. Many have identified the need for well-founded knowledge representation and reasoning to be integrated with deep learning, and for sound explainability. Neurosymbolic computing has been an active area of research for many years, seeking to bring together robust learning in neural networks with reasoning and explainability via symbolic representations for network models. In this paper, we relate recent and early research results in neurosymbolic AI with the objective of identifying the key ingredients of the next wave of AI systems. We focus on research that integrates in a principled way neural network-based learning with symbolic knowledge representation and logical reasoning. The insights provided by 20 years of neurosymbolic computing are shown to shed new light onto the increasingly prominent role of trust, safety, interpretability, and accountability of AI. We also identify promising directions and challenges for the next decade of AI research from the perspective of neural symbolic systems. Keywords: neurosymbolic computing, machine learning and reasoning, explainable AI, AI fast and slow, deep learning. 1. Introduction. Over the past decade, artificial intelligence, and in particular deep learning, have attracted media attention, have become the focus of increasingly large research endeavors, and have changed businesses. This led to influential debates on the impact of AI both on academia and industry. 5266. It has been claimed that deep learning DL caused a paradigm shift not only in AI, but in several computer science fields, including speech recognition, computer vision and image understanding, natural language processing NLP, and machine translation. 49. The 2019 Montreal AI debate between Yoshua Bengio and Gary Marcus, mediated by Vincent Boucher. 52, and the TREP AI -2020 fireside conversation with economics Nobel laureate Daniel Kahneman, mediated by Francesca Rossi, and including the 2018 Turing Award winners and DL pioneers Geoffrey Hinton, Yoshua Bengio, and Yann LeCun, have pointed to new perspectives and concerns on the future of AI. It has now been argued eloquently that if the aim is to build a rich AI system, that is, a semantically sound, explainable, and ultimately trustworthy AI system, one needs to include with it a sound reasoning layer in combination with deep learning. Kahneman corroborated this point at TREP AI -2020 by stating that, as far as I'm concerned, System 1 certainly knows language. System 2 does involve certain manipulation of symbols. 41. Kahneman's comments at TREP AI -2020 go to the heart of the matter, with parallels having been drawn many times by AI researchers between Kahneman's research on human reasoning and decision-making, reflected in his book, Thinking Fast and Slow 40, and the so-called AI Systems 1 and 2, which would in principle be modeled by deep learning and symbolic reasoning respectively. In this paper, we place 20 years of research from the area of neurosymbolic AI, known as neural symbolic integration, in the context of the recent explosion of interest and excitement about the combination of deep learning and symbolic reasoning. We revisit early theoretical results of fundamental relevance to shaping the latest research, and identify bottlenecks and the most promising technical directions for the sound representation of learning and reasoning in neural and symbolic systems. 1. Thinking Fast and Slow by Daniel Kahneman, New York, for as well as pointing to the various related and promising techniques within AI, ML, and deep learning. This article seeks to help organize some of the terminology commonly used around AI. This seems important at this exciting time, when AI becomes popularized, and more people from other areas of computer science and from other fields altogether turn to AI: psychology, cognitive science, economics, medicine, engineering, and neuroscience, to name a few. In Section 2, we position the current debate in the context of the necessary and sufficient building blocks of AI and long-standing challenges of variable grounding and common sense reasoning. In Section, we seek to organize the debate, which can become vague if defined around the concepts of neurons versus symbols, around the concepts of distributed and localist representations. We argue for the importance of this focus on representation, since representation precedes learning as well as reasoning. We also analyze a taxonomy for neurosymbolic AI proposed by Henry Kautz at JE from the angle of localist and distributed representations. In Section 4, we delve deeper into a more technical discussion of current neurosymbolic systems and methods with their pros and cons. In Section 5, we identify promising approaches and directions for neurosymbolic AI from the perspective of learning, reasoning, and explainable AI. In Section 6, we return to the debate that was so present at TREP AI -2020 to conclude the paper and identify exciting challenges for the third wave of AI. 2 Neurons and symbols, context and current debate. Deep learning researchers and AI companies have achieved groundbreaking results in areas such as computer vision, game playing, and natural language processing. 49. Despite the impressive results, deep learning has been criticized for brittleness, being susceptible to adversarial attacks, lack of explainability, not having a formally defined computational semantics or even intuitive explanation, leading to questions around the trustworthiness of AI systems, and lack of parsimony, requiring far too much data, computational power at training time, or unacceptable levels of energy consumption. 52. Against this backdrop, leading entrepreneurs and scientists such as Bill Gates and the late Stephen Hawking have voiced concerns about AI's accountability, impact on humanity, and the future of the planet. 74. The need for a better understanding of the underlying principles of AI has become generally accepted. A key question, however, is that of identifying the necessary and sufficient building blocks of AI and how systems that evolve automatically based on machine learning can be developed and analyzed in effective ways that make AI trustworthy. Turing Award winner and machine learning theory pioneer Leslie Valiant pointed out that a key challenge for computer science is the principled combination of reasoning and learning, building a rich semantics and robust representation language for intelligent cognitive behavior. 92. In Valiant's words, the aim is to identify a way of looking at and manipulating common sense knowledge that is consistent with and can support what we consider to be the 2 most fundamental aspects of intelligent cognitive behavior: the ability to learn from experience and the ability to reason from what has been learned. We are therefore seeking semantics of knowledge that can computationally support the basic phenomena of intelligent behavior. Neurosymbolic computing seeks to offer such a principled way of studying AI by establishing provable correspondences between neural models and logical representations. 4.23. In neurosymbolic computation, logic can be seen as a language with which to compile a neural network, as discussed in more detail later in this paper. The success of deep learning, along with a number of drawbacks identified more recently, such as a surprising lack of robustness. 88, has prompted a heated debate around the value of symbolic AI by contrast with neural computation and deep learning. A key weakness, as Bengio et al. State in a recent article, is that current machine learning methods seem weak when they are required to generalize beyond the training distribution, which is what is often needed in practice. 6. In the recent AI debate between Yoshua Bengio and Gary Marcus, Marcus argues the case for hybrid systems. 52, and seeks to define what makes an AI system effectively hybrid. Many more drastic approaches might be pursued. Yoshua Bengio, for example, has made a number of sophisticated suggestions for significantly broadening the toolkit of deep learning, including developing techniques for statistically extracting causal relationships through a sensitivity to distributional changes and techniques for automatically extracting modular structure, both. Over the years, the terminology neural symbolic, integration computing system, etc. was used predominantly by the research community to indicate a combination of 2 paradigms: neural and symbolic AI. See, for example, 20. More recently, the more colloquial terminology neurosymbolic AI, approach system, etc. has become more commonly used in publications and the printed press. In this paper, we use the term neural symbolic when referring to the combination of paradigms, and we introduce the term neurosymbolic as a single word to symbolize the coming of age of a new area of research, of which I'm quite sympathetic to. But for reasons that will become apparent, I worry that even these sorts of tools will not suffice on their own for getting us to robust intelligence. Instead, I will propose that in order to get to robust artificial intelligence, we need to develop a framework for building systems that can routinely acquire, represent, and manipulate abstract knowledge, with a focus on building systems that use that knowledge in the service of building, updating, and reasoning over complex internal models of the external world. Key to the appreciation of the above statement by Marcus, also advocated in 46 and 28, is an understanding of the representational value of the symbolic manipulation of variables in logic and the compositionality of language. It is probably fair to assume that the next decade will be devoted to researching specific methods and techniques which seek to address the above issues of representation, robustness, and extrapolation. Such techniques will be drawn from a broader perspective of neurosymbolic machine learning and AI, which embraces hybrid systems, including a. variable grounding, and symbol manipulation, embracing hybrid systems requires the study of how symbols may emerge and become useful in the context of what deep learning researchers have termed disentanglement. Once symbols emerge, which may happen at different levels of abstraction, ideally within a modular network architecture, it may be more productive from a computational perspective to refer to such symbols and manipulate, that is, compute them symbolically rather than numerically. Once it becomes known that a complex neural network serves to calculate, for example, the sum of two handwritten digits provided as input images, or equally that a complex neural network has learned the function fx equal to x, then it is probably the case that one would prefer such a calculation to be precise and to extrapolate well to any value of x. This is easily achieved symbolically. Reasoning, in many cases too, is preferred to be precise and not approximate, although there are cases where approximate or human-like reasoning become more efficient than logical deduction. 34. B. Common sense and combinatorial reasoning. Another key distinction that is worth making explicit refers to the difference between common sense knowledge and expert knowledge. While the former is approximate and difficult to specify, the latter strives to be as precise as possible and to prove its properties. We believe that, once equipped with a solid understanding of the value of hybrid systems, variable manipulation and reasoning, the debate will be allowed to progress from the question of symbols versus neurons to the research question: how to compute and learn with symbols inside or outside of a neural network, and how efficiently computationally in a precise or approximate reasoning setting. Foundational work about neurosymbolic models and systems such as 16, 17, 20 will be relevant as we embark in this journey. In 20, correspondences are shown between various logical symbolic systems and neural network models. The current limits of neural networks as essentially a propositional free system are also evaluated. In a nutshell, current neural networks are capable of representing propositional logic, non-monotonic logic programming, propositional modal logic, and fragments of first-order logic, but not full first-order or higher-order logic. This limitation has prompted the recent work in the area of logic tensor networks LTN 795395, which, in order to use the language of full first-order logic with deep learning, translates logical statements into the loss function rather than into the network architecture. First-order logic statements are therefore mapped onto differentiable real-valued constraints using a many-valued logic interpretation in the interval 0, 1. The trained network and the logic become communicating modules of a hybrid system instead of the logic computation being implemented by the network. This distinction between having neural and symbolic modules that communicate in various ways and having translations from one representation to the other in a more integrative approach to reasoning and learning should be at the center of the debate in the next decade. 4. The current limitation of neural networks, which John McCarthy referred to as propositional fixation, is of course based on the current simple models of neuron. Although this may be about to change through important work on understanding the mind and brain, which may produce richer models of neural networks. 30. One should note that the recent state-of-the-art results obtained by deep networks using large amounts of data are predicated on the notion of a simple neuron. 4978. Having worked for 2 decades on integrative neurosymbolic AI, and more recently on hybrid neural symbolic systems, we are acutely aware of the tension between principal integration and practical value and application. Scientifically, there is obvious value in the study of the limits of integration to improve our understanding of the power of neural networks using the well-studied structures and algebras of computer science logic. When seeking to solve a specific problem, however, one may prefer to take, for example, an existing knowledge base and find the most effective way of using it alongside the tools available from deep learning and software, agents. As a case in point, take the unification algorithm, which is an efficient way of computing symbolic substitutions. It is notoriously difficult to implement in neural networks. One may, of course, wish to study how to. Among the recent neurosymbolic systems, one can identify quite a variety and range from integrative to hybrid systems. 51 can be seen as a loosely coupled hybrid approach, where image classification is combined with reasoning from text data, offers further integration by allowing a node in the probabilistic inference tree of a symbolic ML system ProBlock to be replaced by a neural network. Takes another step towards integration by using a differentiable many-valued logic in the loss function of a neural network in LTN. Theorem proving is left for the symbolic counterpart of the system. 54 proposes to perform differentiable unification and theorem proving inside the neural network. Out of the systems and techniques now available, some more integrative, others more loosely coupled, a common question clearly emerges. What are the fundamental building blocks, the necessary and sufficient components of neurosymbolic AI? For example, is the use of an attention layer necessary? 96, or can it be replaced by richer structures such as graph networks? 47. Is the explicit use of probability theory necessary, and in this case inside the network or at the symbolic level, or both? Is there a real computational gain in combinatorial problem solving by theorem proving using neural networks, or is this task better left to the devices of a symbolic system? One thing is now very clearer: there is great practical value in the use of gradient-based learning on distributed representations. In this paper, we also seek to bring attention to another perhaps less attractive, but equally if not more relevant question of adopting a distributed versus a localist representation. In a localist representation, the relevant concepts have an associated identifier. This is typically a discrete representation. By contrast, in a distributed representation, concepts are denoted by vectors with continuous values. This is therefore an issue of which representation is adequate or most appropriate. Symbolic machine learning takes a localist approach while neural networks are distributed, although neural networks can also be localist. 57. The next section will be devoted to the pros and cons of distributed and localist representations. Forms of neurosymbolic integration. Within neurosymbolic AI, one may identify systems that translate and encode symbolic knowledge in the set of weights of a network. 27. Or systems that translate and encode symbolic knowledge into the loss function of the network. 79. The neural symbolic cycle translating symbolic knowledge into neural networks and vice versa. Perform logical unification exactly or approximately using a neural network. Although at present the most practical way may be to adopt a hybrid approach whereby unification is computed symbolically. Offers a kind of compiler for neural networks. 5. Whereby prior knowledge is translated into the network, and a decompiler whenever symbolic descriptions are extracted from a trained network. The compiler can either set up the network's initial weights akin to a one-shot learning algorithm which is guided by knowledge, or define a knowledge-based penalty or constraint which is added to the network's loss function. A third form of integration has been proposed in 6, which is based on changing the representation of neural networks into factor graphs. The value of this particular representation deserves to be studied. Change of representation is a worthwhile endeavor on its own right, in that it may help us understand the strengths and limitations of different neural models and network architecture choices. This third form of integration, however, proposes to create an intermediate representation with factor graphs in between neural networks and logical representations. A note about terminology in 58th, Turing Award winner Judea Pearl offers a critique of machine learning which unfortunately conflates the terms machine learning and deep learning. Similarly, when Jeffrey Hinton refers to symbolic AI, the connotation of the term tends to be that of expert systems dispossessed of any ability to learn. The use of the terminology is in need of clarification. Machine learning is not confined to association rule mining. Cf. the body of work on symbolic ML and relational learning 55. The differences to deep learning being the choice of representation, localist logical rather than distributed, and the non-use of gradient-based learning algorithms. Equally, symbolic AI is not just about production rules written by hand. A proper definition of AI concerns knowledge representation and reasoning, autonomous multi-agent systems, planning and argumentation, as well as learning. In what follows, we elaborate on the above misunderstandings one at a turn. Symbolic machine learning and deep learning. In 58, Pearl proposes a hierarchy consisting of 3 levels: association, intervention, and counterfactual reasoning, and claims that ML is only capable of achieving association. A neurosymbolic or purely symbolic ML system should be capable of satisfying the requirements of all 3 of Pearl's levels, for example by mapping the neural networks onto symbolic descriptions. It is fair to say in relation to Pearl's top level in the hierarchy, counterfactual reasoning, that 5. In the study of programming languages, it is accepted that different levels of abstraction and different representations are needed, for example Java bytecode, and a Java program for the purpose of efficiency, system maintenance, user interaction, and verification. We argue that in AI, neural symbolic systems will provide equally important forms of abstract representation. Progress has only been made recently, and that much research is still needed, although good progress is being made towards the extraction of local, measurable counterfactual explanations from black box ML systems. 99. Once a neural network has been endowed with a symbolic interpretation, one has no reason to doubt the ability of a neural system to ask what-if questions. In fact, the very algorithm for extracting symbolic logic descriptions of the form a B from trained neural networks 15 uses a form of interrogation of the network akin to the intervention of Bayesian models advocated by Pearl. We argue therefore that a more important question is representational. Which representation is most effective, deep networks or Bayesian networks? While attempting to answer this question, as well as considering the demands of the practical applications, it is important to recognize that neural networks offer a concrete model of computation, one which can be implemented efficiently by message passing or propagation activation, differently from Bayesian networks, and trained by differentiable learning algorithms. A limitation of having such a concrete computational model, however, may be a difficulty of pure neural networks at modeling rich forms of abstraction which are not dependent on the data, images, audio, etc., but which exist instead at a higher conceptual level. We shall return to this challenge later in the paper. Knowledge representation and reasoning in AI. Complex problem solving using AI requires a much richer language than that of expert systems as suggested by Hinton 36. AI requires a language that can go well beyond horn clauses to include relational knowledge, time and other modalities, negation by failure, variable substitution, quantification, etc. In statistical relational learning, the use of first-order logic does not require instantiating or grounding all possible combinations of the values of the variables, for example x and y, in a relation rxy. In relational reasoning with neural networks, borrowing from the field of relational databases, it is typically the grounded and therefore propositional rather than first-order representation that is learned and reasoned about. For the avoidance of confusion, we would term this latter task relationship learning. Two other equally important attributes of a rich language for complex problem solving are compositionality, in the sense of the compositionality of the semantics of a logical language, and modularity. It is worth noting that in the original paper about deep learning 37, before much of the attention turned to convolutional networks, modularity was a main objective of the proposed semi-supervised greedy learning of stacks of restricted Boltzmann machines. The recently proposed stacked capsule autoencoders 44 and neurosymbolic approaches such as logic tensor network 79, as well as other weakly supervised approaches, revive the important stance of modularity in neural computation. Earlier efforts towards modularity in neurosymbolic AI can be traced back to the system for connectionist modal and intuitionistic logics 18, 19. Modal logics with a possible world semantics have been shown to offer a natural approach to modularity in neural computation 20. With AI understood as a superset of ML, which in turn is a superset of DL, we shall argue for the combination of statistical machine learning, knowledge representation KR, and logical reasoning. By logical reasoning, we shall mean not only classical logic reasoning with the traditional true-false interpretation, but non-classical reasoning, including non-monotonic, modal, and many-valued logics. In the study of the interplay between learning and reasoning, and how best to implement it, for example, in a continuous or discrete system, it shall become clear that universal quantification is easy to reason about and hard to learn. Using neural networks, existential quantification is easy to learn and harder to reason about in a symbolic system. Such limitations on either side of the spectrum will dictate a few practical design decisions to be discussed in this paper. In a nutshell, we claim that neurosymbolic AI is well placed to address concerns of computational efficiency, modularity, KR plus ML, and even causal inference. More researchers than ever on both sides of the connectionist symbolic AI divide are now open to studying and learning about each other's tools and techniques. This was not the case until very recently. The use of different terminology alongside some preconceived opinion, or perhaps idleness, fueled by the way that science normally rewards research that is carried out in silos, have prevented earlier progress. The fact that this is now changing will lead to faster progress in the overall field of AI. It is reassuring to see it happening in this way. The neural information processing community have shown the value of neural computation in practice, which has attracted the curiosity of great minds from symbolic AI. We hope that further collaboration in neurosymbolic AI will help solve many of the issues which are still outstanding. 3. Distributed and localist representation. The integration of learning and reasoning through neurosymbolic systems requires a bridge between localist and distributed representations. The success of deep learning indicates that distributed representations with gradient-based methods are more adequate than localist ones for learning and optimization. At the same time, the difficulty of neural networks at extrapolation, explainability, and goal-directed reasoning point to the need of a bridge. 10. Between distributed and localist representations for reasoning. Neurosymbolic computing has been an active area of research seeking to establish such a bridge for several years. 4, 25, 43. In neurosymbolic computation, knowledge learned by a neural network can be represented symbolically. Reasoning takes place either symbolically or within the network in distributed form. Despite their differences, both the symbolic and connectionist paradigms share common characteristics, offering benefits when put together in a principled way. See, for example, 17, 20, 84, 93. Change of representation also offers a way of making sense of the value of different neural models and architectures with respect to what is a more formal and better understood area of research, symbolic logic. Neural network-based learning and inference under uncertainty have been expected to address the brittleness and computational complexity of symbolic systems. Symbolism has been expected to provide additional knowledge in the form of constraints for learning, 2332, which ameliorate neural networks' well-known catastrophic forgetting or difficulty with extrapolation in unbounded domains or with out-of-distribution data. The integration of neural models with logic-based symbolism is expected, therefore, to provide an AI system capable of explainability, transfer learning, and a bridge between lower-level information processing for efficient perception and pattern recognition, and high-level abstract knowledge for reasoning, extrapolation, and planning. Suppose that a complex neural network learns a function fx. Once this function is known, or more precisely a simplified description of fx is known, computationally, it makes sense to use such a representation, not least for the sake of extrapolation, as exemplified earlier with the fx equal to x function. One could argue that at this point the neural network has become superfluous. Symbol manipulation, once symbols have been discovered, is key to further learning at new levels of abstraction. This is exemplified well in 52 with the use of the concept of a container which may be learned from images. Among the most promising recent approaches to neural symbolic integration, so-called embedding techniques seek to transform symbolic representations into vector spaces where reasoning can take place through matrix computations over distance functions 7, 85, 87, 80, 75, 11, 26, 124, 70. In such systems, learning of embedding is carried out using backpropagation 9873. Most of the research in this area is from knowledge such as peaks, y, in a distributed neural network. The logical predicate p relating variables x and y could be used to denote, for example, the container relation between two objects in an image, 11, such as a violin and its case, which are in turn described by their embedding. This process is known as relational embedding 7, 75, 85, 87. For representing more complex logical structures such as first-order logic formulas, for example, x, y, z, pexy, q, z. A system named logic tensor networks LTN80 was proposed by extending neural tensor networks NTN85, a state-of-the-art relational embedding method. Related ideas are discussed formally in the context of constraint-based learning and reasoning in 32. Two powerful concepts of LTN are 1, the grounding of logical concepts onto tensors with the use of logical statements which act as constraints on the vector space to help learning of an adequate embedding, and 2, the modular and differentiable organization of knowledge within the neural network, which allows querying and interaction with the system. Any user-defined statement in first-order logic can be queried in LTN, which checks if that knowledge is satisfied by the trained neural network. With such a tool, a user can decide when to keep using a distributed connectionist representation or switch to a localist symbolic representation. This last aspect brings the question of the emergence of symbols and their meaning in neural networks to the fore. Recent work using the weakly supervision of autoencoders and ideas borrowed from disentanglement have been showing promise in the direction of learning relevant concepts, which can in turn be reused symbolically. 10. Related work seeking to explore the advantages of distributed representations of logic include 11, which is based on stochastic logic programs, 26, 100, 24, with a focus on inductive programming, and 70, based on differentiable theorem proving. A taxonomy for neurosymbolic AI. With an understanding of the role of localist and distributed approaches, we now provide an analysis of Henry Kautz's taxonomy for neurosymbolic AI 42, which was introduced at Check AI 2020. In Kautz's taxonomy, a type 1 neural symbolic integration is standard deep learning, which some may argue is a stretch, but which is included by Kautz to note that the input and output of a neural network can be made of symbols, for example text in the case of language translation, or question answering applications. Type 2 are hybrid systems, such as DeepMind's AlphaGo and other systems, where the core neural network is loosely coupled with a symbolic problem solver, such as Monte Carlo tree search. Type 3 is also a hybrid system, whereby a neural network focusing on one task, for example, object detection, interacts via its input and output with a symbolic system specializing in a complementary task, for example, query answering. Examples include the neurosymbolic concept, Learner 51, and Deep Problog 50. In a Type 4 neural symbolic system, symbolic knowledge is compiled into the training set of a neural network. Kautz offers 48 as an example, to be. Read alongside the critique in, an approach to learn and reason over mathematical constructions is proposed in 2, and in 1, a learning architecture that extrapolates to harder symbolic maths reasoning problems is introduced. We would also include in Type 4 other tightly coupled but localist neural symbolic systems, where various forms of symbolic knowledge, not restricted to if-then rules, is translated into the initial architecture and set of weights of a neural network, in some cases with guarantees of correctness 20, as well as logical neural networks, where the key concept is to create a one-to-one correspondence between neurons and the elements of logical formulas, 69. Type 5 are those tightly coupled but distributed neurosymbolic systems, where a symbolic logic rule is mapped onto an embedding which acts as a soft constraint, a regularizer, on the network's loss function. Examples of these include logic tensor networks 79 and tensor product representations 39, referred to in 13 as tensorization methods. Finally, a type 6 system should be capable, according to Kautz, of true symbolic reasoning inside a neural engine. This is what one could refer to as a fully integrated system. Early work in neurosymbolic computing has achieved this C20 for a historical overview. Some type 4 systems are also capable of it, but using a localist rather than a distributed representation and using much simpler forms of embedding than type 5 systems. Kautz adds that a type 6 system should be capable of combinatorial reasoning, possibly by using an attention schema to achieve it effectively. Recent efforts in this direction include 84763, although a fully fledged type 6 system for combinatorial reasoning does not exist yet. Further research into type 5 systems will likely focus on the provision of rich embeddings and the study of the extent to which such embeddings may correspond either to predefined prior knowledge or to learned attention. Mechanisms. Further research onto type 6 systems is highly relevant to the theory of neurosymbolic computing, as discussed in more detail in the next section. In practical terms, attention exists between effective learning and sound reasoning, which may prescribe the use of a more hybrid approach of types 3 to 5, or variations thereof, such as the use of attention with tensorization. Orthogonal to the above taxonomy, but mostly associated thus far with type 4, is the study of the limits of reasoning within neural networks, which was already of interest since the first efforts by Valiant at providing a foundation for computational learning, 91. Recently, this has been the focus of experimental analyses of deep learning in symbolic domains, 89, and it should include the study of first-order logic, higher-order, many-valued, and non-classical logic. 13. 4 neurosymbolic computing systems, technical aspects. In symbolic ML, symbols are manipulated as part of a discrete search for the best representation to solve a given classification or regression task. The most well-known form of symbolic ML are decision trees, but richer forms of representation exist, in particular relational representations using first-order logic to denote concepts ranging over variables, x, y, z. Within a possibly infinite domain, for example, x, y, z, grandfather x, father x, mother z, the father of someone's mother is that person's grandfather. Probabilistic extensions of this approach seek to learn probability distributions for such logical rules or functional programs as a way of accounting for uncertainty in the training data. Work in these areas is probably best characterized by the conference series on inductive logic programming 6556, statistical relational learning 6825-381, and probabilistic or inductive programming 77. All of the excitement and industrial interest in the past 10 years surrounding AI and machine learning, though, have come from an entirely separate type of ML, deep learning. Deep learning uses neural networks and stochastic gradient descent to search through a continuous space, also to solve a given classification or regression task, but creating vector-based distributed representations rather than logical or symbolic ones. For this reason, such systems are called subsymbolic. Whilst it is clear now that AI will not be achieved by building expert systems by hand from scratch, but by learning from large collections of data, one would be misguided to conflate all of machine learning or dismiss the role of symbolic logic, which remains the most powerful and adequate representation for the analysis of computational systems. As put simply by Moshe Vardi, logic is the calculus of computer science, and differently from statistics, machine learning can only exist within the context of a computational system. Specifically, deep neural networks will require a language for description, as also advocated by Leslie Valiant. Neural network-based AI is distributed and continuous, deals well with large-scale multimodal noisy perceptual data such as text and audio, handles symbol grounding better than symbolic systems since concepts are grounded on feature vectors, and is by definition a computational model, frequently implemented efficiently using propagation of activation and tensor processing units. Symbolic AI is generally localist, contrast with Bayesian networks, which may be inefficient as a computational model, 14, and discrete, capable of sophisticated reasoning, including temporal, epistemic and non-monotonic reasoning, planning, extrapolation and reasoning by analogy. Neurosymbolic AI has shown that non-classical logics, in particular many-valued logics, offer an adequate language for describing neural networks, 79-69. As the field of AI moves towards agreement on the need for combining the strengths of neural and symbolic AI, it should turn next to the question, what is the best representation for neurosymbolic AI? To answer this question, one should seek to be informed by developments in neurosymbolic computing of the past 20 years, and to evaluate in a precise manner the methods, algorithms, and applications of neurosymbolic AI. For instance, it is known that current recurrent neural networks are capable of computing the logical consequences of propositional modal logic programs and other forms of non-classical reasoning and fragment of first-order logic programs. 5.20. Obtaining results for full first-order logic has not been possible thus far, which reinforces John McCarthy's claim that neural networks are essentially propositional. In terms of applications of AI, these have been largely focused on perceptual or pattern-matching tasks, such as image and audio classification. Recent efforts at question answering and language translation, as well as protein folding classification, have highlighted the importance of the neurosymbolic approach. The ideal type of application for a neurosymbolic system, however, should be that where abstract information is required to be reasoned about at different levels beyond that what can be perceived from data alone, such as complex concept learning, whereby simpler concepts are required to be organized systematically as part of the definition of a higher concept. Such a conceptual structure, which is still to be discovered using data, also requires knowledge which is governed by general rules and exceptions to the rules, allowing for sound generalization in the face of uncertainty, but also capable of handling specific cases, the many exceptions, which may be important for the sake of robustness, although not necessarily statistically relevant. Similarly, it seems hard to achieve true relational learning using only neural networks. A useful but simple example can be borrowed from the area inductive logic programming, learning the concept of ancestor from a few examples of the mother, father, and grandparent relations. Grounding the entire knowledge base in this case would not be productive, since the chain of reasoning to derive the concept of ancestor may be arbitrarily large depending on the data available. In this case, one is better off learning certain relations by jumping to conclude frequently requiring simplification of graphs into tree-based representations. 15. Scions, such as for example xy, father xy, ancestor xy, from relatively few examples and using similarity measures to infer new relations. At the same time, deriving symbolic descriptions which can be used for reasoning beyond the distribution of the data, allowing in turn for extrapolation. In this example, once a description for ancestor is obtained, one should be able to reason about arbitrarily long chains of family relationships. Notice that key to this process is the ability to revise the conclusion, taken once new evidence to the contrary of what has been inferred is made available from the data. In other words, the reasoning here is non-monotonic. 14. In summary, at least two options exist for neurosymbolic AI. In option 1, symbols are translated into a neural network, and one seeks to perform reasoning within the network. In option 2, a more hybrid approach is taken, whereby the network interacts with a symbolic system for reasoning. A third option, which would not require a neurosymbolic approach, exists when expert knowledge is made available, rather than learned from data, and one is interested in achieving precise sound reasoning, as opposed to approximate reasoning. We discuss each option briefly next. In option 1, it is desirable still to produce a symbolic description of the network for the sake of improving explainability, discussed later, or trust, or for the purpose of communication and interaction with the system. In option 2, by definition, a neurosymbolic interface is needed. This may be the best option in practice given the need for combining reasoning and learning in AI, and the apparent different nature of both tasks, discrete and exact versus continuous and approximate. However, the value of distributed approximate reasoning using neural networks is only starting to be investigated, as in the case of differentiable neural computers and neural theorem proving, although early efforts did not prove to be promising in terms of practical efficiency. 62-38-82. In option 3, a reasonable requirement nowadays would be to compare results with deep learning and the other options. This is warranted by the latest practical results of deep learning, showing that neural networks can offer, at least from a computational perspective, better results than purely symbolic systems. In practice, the choice between options 1 and 2 above may depend on the application at hand and the availability of quality data and knowledge. A comparatively small number of scientists will continue to seek to make sense of the strengths and limitations of both neural and symbolic approaches. On this front, the research advances faster on the symbolic side due to the clear hierarchy of semantics and language expressiveness and rigor that exists at the foundation of the area. By contrast, little is known about the expressiveness of the latest deep learning models in relation to established 16 neural models beyond data-driven comparative empirical evaluations. As advocated by Paul Smolensky, neurosymbolic computing can help map the latest neural models into existing symbolic hierarchies, thus helping organize the extensively ad hoc body of work in neural computation. 5 challenges for the principled combination of reasoning and learning. For a combined perspective on reasoning and learning, it is useful to note that reasoning systems may have difficulties computationally when reasoning with existential quantifiers and function symbols, such as XPF. Efficient logic-based programming languages, such as Prolog, for example, assume that every logical statement is universally quantified. By contrast, learning systems may have difficulty when adopting universal quantification over variables. To be able to learn a universally quantified statement such as XPX, a learning system needs, in theory, to be exposed to all possible instances of X. This simple duality points to a possible complementary nature of the strengths of learning and reasoning systems. To learn efficiently XPX, a learning system needs to jump to conclusions, extrapolating XPX given an adequate amount of evidence the number of examples or instances of X. Such conclusions may obviously need to be revised over time in the presence of new evidence, as in the case of non-monotonic logic. In this case, a statement of the form XPX becomes a data-dependent generalization, which is not to be assumed equivalent to a statement WPI, as done in classical logic. Such statements may have been learned from different samples of the overall potentially infinite population. On the other hand, a statement of the form XPX is trivial to learn from data by identifying at least one case par, although reasoning from XPX is more involved, requiring the adoption of an arbitrary constant B such that PB holds. It is now accepted that learning takes place on a continuous search space of subdifferentiable functions. Reasoning takes place in general on a discrete space, as in the case of goal-directed theorem proving. The most immediate way of benefiting from the combination of reasoning and learning, therefore, is to adopt a hybrid approach whereby a neural network takes care of the continuous search space and learning of probabilities, while a symbolic system consisting of logical descriptions of the network uses discrete search to achieve extrapolation and goal-directed reasoning. 7. As hinted already in. The investigation of continuous reasoning or discrete learning approaches is of course worth pursuing too. There have been a number of recent developments with relevant. 17. This paper, a property of early deep learning, may hold the key to the above hybrid perspective, modularity. In the original paper on deep learning 37, a modular system is proposed consisting of a stack of restricted Boltzmann machines, RBMs. The extraction of symbolic descriptions from each RBM is thus made considerably easier. 90. Each RBM learns a joint probability distribution, while their symbolic description reflects the result of learning without manipulating probabilities explicitly, thus avoiding the complexity of probabilistic inference found in symbolic AI. In 90, an efficient algorithm is presented that extracts propositional rules enriched with confidence values from RBMs, similar to what was proposed with penalty logic for Hopfield networks in 62. When RBMs are stacked onto a deep belief network, however, the modular extraction of compositional rules may be accompanied by a compounding loss of accuracy, indicating that knowledge learned by the neural network might not have been as modular as one would have wished. Systems that impose a more explicit separation of modules may hold the answer to this problem, in particular systems where unsupervised learning is combined with weakly supervised classification at distinct levels of abstraction, such as with the use of variational autoencoders 86 or generative adversarial networks 31. In the area of reinforcement learning too, deep learning systems combined with symbolic rules were first proposed in 29, and there is promise of considerable progress with the use of neurosymbolic approaches, especially in the case of model-based reinforcement learning. We therefore do not advocate the adoption of monoblock networks with millions of parameters, even though this may be how the human brain works. Loss of modularity seems to be, at least at present from a computational perspective, a price that is too high to pay. Modularity remains a fundamentally relevant property of any computing system. Applications of neurosymbolic AI. One major way of driving advances in AI continues to be through challenging applications, be it language translation, computer games, or protein folding competitions. Language understanding in the broadest sense of the term, including question answering that requires common sense reasoning, offers probably the most complete application area for neurosymbolic AI. As an example, consider this question and its common sense answer from the Cooper dataset 72. It got dark outside. What happened as a result? Snowflakes began to fall from. Results in both of these directions, 71, 50, 164. Computational complexity issues remain a challenge though for the combination of first-order logic and probabilities in symbolic AI. 18. The sky, B, the moon, became visible in the sky. Another very relevant application domain is planning, which requires learning and reasoning over time. As in this example adapted from 76, Daniel picks up the milk, Daniel goes to the bedroom, Daniel places the milk on the table, Daniel goes to the bathroom. Where is the milk? Finally, an area where machine learning and knowledge representation and reasoning have complementary strengths is knowledge engineering, including knowledge-based completion and data-driven ontology learning. In this area of application, rich and large-scale symbolic representations exist alongside data, including knowledge graphs to be combined with neural networks, such as graph neural networks. A common thread across the above examples and applications is the need for modeling cause and effect with the use of implicit information. This requires learning of general rules and exceptions to the rules that evolve over time. In such cases, deep learning alone fails when presented with examples from outside the distribution of the training data. This motivated Judea Pearl's critique of machine learning 58, which we shall address in some detail next. In Pearl's three-level causal hierarchy, association, intervention, and counterfactuals, association involves purely statistical relationships. In Pearl's words, observing a customer who buys toothpaste makes it more likely that this customer will also buy floss. Such associations can be inferred directly from the observed data using standard conditional probabilities and conditional expectation or other standard non-probabilistic ML model. Questions asked at this level require no causal information, and for this reason, this layer is placed at the bottom of the hierarchy. Answering such questions is the hallmark of current machine learning methods. Pearl's hierarchy may unintentionally give the impression that machine learning is confined to this bottom layer, since no reference is made in 58 to the body of work on symbolic machine learning, which is unequivocally not confined to association rules 55-70. Pearl continues, the second level, intervention, ranks higher than association because it involves not just seeing what is, but changing what we see. A typical question at this level would be, what will happen if we double the price? Such a question cannot be answered from sales data alone, as it involves a change in customers' choices in reaction to the new pricing. These choices may differ substantially from those taken in previous price-raising situations, unless we replicate precisely the market conditions that existed when the price reached double its current value. At this level, there is a need for inference that can reach beyond the data distribution. Finally, the top level invokes counterfactuals, a mode of reasoning that reverts to the philosophers David Hume and John Stuart Mill, and that has been given computational semantics in the past 2 decades. A typical question in the counterfactual category is, what if I had acted differently, thus necessitating retrospective reasoning? As noted earlier in the paper, neurosymbolic computing can implement all 3 of Pearl's levels. Once a symbolic description of the form if A then B has been associated with a neural network, surely the idea of intervention 9 and counterfactual reasoning become possible. CF, for example, 99, on the measurement and extraction of counterfactual knowledge from trained neural networks. Our conclusion from the above discussion is that in neurosymbolic AI, knowledge should be grounded onto vector representations for efficient learning from data based on message passing in neural networks as an efficient computational model. Symbols should become available as a result of querying and knowledge extraction from trained networks, and offer a rich description language at an adequate level of abstraction, enabling infinite uses of finite means, but also compositional discrete reasoning at the symbolic level, allowing for extrapolation beyond the data distribution. The combination of learning and reasoning should offer an important alternative to the problem of combinatorial reasoning by learning to reduce the number of effective combinations, thus producing simpler symbolic descriptions as part of the neurosymbolic cycle. As an example, consider an autoencoder, which learns in unsupervised fashion to maximize mutual information between pixel inputs and a latent code, or some other embedding consisting of fewer relevant features than pixels. Suppose that this neural network has learned to find regularities, such as, for example, when it sees features of type A, it also sees features of type B but not features of type C. At this point, such regularities can be converted into symbols, x, y, b, z, c's. As a result of the use of variables, x, y, z at the symbolic level, one can extrapolate the above regularity to any features of type A, B, or C. A symbolic description is also a constraint on the neurosymbolic cycle. It is generalized from data during learning, and 8. As another example, consider a neural network trained to classify graphs into those which contain a Hamiltonian cycle, and those which do not, given a fixed range of available graph sizes as training examples. Contrast this network with a symbolic description of the definition of Hamiltonian cycle, which therefore applies to graphs of any size. 20. It certainly includes an ability to ask what-if questions. Reasoning about what has been learned allows for extrapolation beyond the data distribution. And finally, the symbolic description can serve as prior knowledge as a constraint for further learning in the presence of more data, which includes the case of knowledge-based transfer learning 90. Further training can now take place at the perceptual or sub-symbolic level, or at the conceptual or symbolic level. This is when having a distributed sub-symbolic and a localist symbolic or sub-symbolic representation becomes relevant. Assuming that probabilities are dealt with at the sub-symbolic distributed level, as in RBMs, and that the symbolic level is used for a more qualitative representation of uncertainty in the form of general rules with exceptions, we avoid the complications of having to deal simultaneously with discrete and continuous learning of rules and probabilities. A note about explainable AI, XAI. Knowledge extraction is an integral part of neural symbolic integration and a major ingredient towards explainability of black box AI systems. The main difficulty in XAI is the efficient extraction of compact and yet correct and complete knowledge. It can be argued that a large knowledge base is not more explainable than a large neural network. Although this may be true at the level of the entire model explainability, in the case of local explanations, that is, explanations of individual cases, a knowledge base is certainly more explainable than a neural network because it offers a proof history showing why an outcome was obtained, as opposed to simply showing how propagation of activation through the network has led to that outcome. It is a main goal of knowledge extraction algorithms to seek to derive compact relevant representations from large complex networks. This is not always possible to achieve efficiently, in which case one may need to resort to having local explanations only. Many aspects of XAI are being investigated at present. Some of the research questions include: is the explanation intended for an expert or layperson? Is an explanation required because one does not trust the system, expected a different outcome, would like to induce a different outcome, or would like to question the normative system that has led to the outcome? Is an explanation intended to try and improve system performance, reduce bias, increase fairness, or is it the case that one would simply like to be able to understand the decision process? The answers to these questions are likely. The now apparent lack of explainability of random forests, which amount to a collection of decision trees and therefore propositional logic formulas with probabilities, serves as a good reminder that XAI is not confined to neural networks. 21. To be application and user specific. While some stakeholders may be happy without an explanation, as in the case of a patient faced with a medical diagnosis, in most cases, some form of explanation is needed to improve system performance or trust. In some cases, producing an explanation is in fact the main goal of the system, as in the application of ML to responsible gambling in 5960. Early efforts at knowledge extraction in neurosymbolic AI as a form of explanation were always evaluated WRT fidelity, a measure of the accuracy of the extracted knowledge in relation to the neural network, rather than the data, or in today's terminology, a measure of the accuracy of the student model WRT, the teacher model. High fidelity is therefore fundamental whenever a student model is to be claimed to offer a good explanation for a more complex teacher model. Unfortunately, many recent XAI methods have abandoned fidelity as a measure of the quality of an explanation, making it easier for an apparently excellent explanation to be simply wrong, in that it may not be at all an explanation of the ML model in question. This is particularly problematic for very popular local XAI methods such as Lime 67. Local explanation systems currently in use by consultancy firms and available in many AI toolboxes can be shown to achieve very low levels of fidelity. Without high fidelity results, an apparently perfectly good explanation produced by an XAI system is likely not to be an explanation of the underlying ML system which it is expected to explain. In 99, a way of measuring fidelity of local methods was introduced, which we argue should be adopted by all XAI methods. The same paper exemplifies how Lime's explanations may achieve very low fidelity. Even better than fidelity, if an XAI method can be shown to be sound 15, then it will probably converge to a high fidelity. Soundness, however, is normally associated with exponential complexity, and so in practice, a measure of fidelity may be all that is available. Knowledge extraction should also allow communication between users and the ML system. Current interactive ML is insufficient to the extent that it proposes to replace sound statistical evaluation by subjective user evaluation. Communication with the system implies an ability to ask questions, query the system, and check one's understanding, obtain a rationale for the outcome. The user can then either agree with the outcome and the rationale, agree with the outcome but not the rationale, or disagree with the outcome, thus providing useful feedback or direct intervention to change the system and its outcomes, probably through the system's symbolic description language in the case of neurosymbolic AI. Knowledge extraction also offers a way of identifying and correcting for 22. Bias in the ML system, which is a serious and present problem. 25. As a result of the General Data Protection Regulation (GDPR), many companies have decided as a precaution to remove protected variables such as gender and race from their ML system. It is well known, however, that proxies exist in the data which will continue to bias the outcome, so that the removal of such variables may serve only to hide a bias that otherwise could have been revealed via knowledge extraction. 61. Current AI-based decision support systems process very large amounts of data which humans cannot possibly evaluate in a timely fashion. Thus, even with a so-called human-in-the-loop approach where technology domain experts or end users may become accountable to the decisions, domain experts or end users are likely to quickly feel progressively less capable of overriding recommendations which were deemed accurate and based on so much more data than they can handle. Even when such AI systems are portrayed as decision support systems, the current reality is that in order to function well with big data, the system must execute a form of triage of the data to be presented to the expert, thus only offering partial information to the decision maker. Without knowledge extraction and a capacity for system communication, the decision maker will, by the very nature of the automated data triage, not be in control. Finally, the simple extraction of rules from trained networks may be insufficient. One may need to extract also confidence values so as to be able to rank extracted rules. This offers a system that knows when it does not know. As a simple example, consider a typical neural network trained to classify the well-known MNIST handwritten digits from 0 to 9. Faced with an image of an obvious non-digit such as an image of a cat, this system must surely provide a very low confidence value to any of the outcomes 0 to 9. The use of adversarial approaches alongside knowledge extraction for robustness has a contribution to make here. In summary, for the many reasons discussed above, neurosymbolic AI with a measurable form of knowledge extraction is a fundamental part of XAI. 6. Take AI 2020, a turning point. We now return to the debate around System 1 and System 2 that motivated the introduction of this paper and provide a short summary of the EAI 2020 conference. Not only did the AAAI 2020 conference contain a larger than usual number of papers proposing to combine neural networks and symbolic AI, there were a number of keynote addresses and debates directly relevant to neural symbolic computing, notably 23. 1. Fireside conversation between 2019 Turing Award winners Francesca Rossi and Nobel laureate Daniel Kahneman on thinking fast and slow and its relation to neural networks and symbol manipulation. The third AI summer, Henry Kautz's AAI 2020 Robert S. Engelmore Memorial Award lecture, which introduced a taxonomy for neurosymbolic computing. 3. The director of MIT, IBM, Watson AI Laboratory David Cox IDAI keynote address, which focused on neurosymbolic AI and applications on vision and language understanding, machine common sense, question answering, argumentation, and XAI. At the Turing Award session and fireside conversation with Daniel Kahneman, there was a clear convergence towards integrating symbolic reasoning and deep learning. Kahneman made his point clear by stating that on top of deep learning, a System 2 symbolic layer is needed. This is reassuring for neurosymbolic AI going forward as a single, more cohesive research community that can agree about definitions and terminology rather than a community divided as AI has been up to now. AI is still in its infancy, so perhaps some of the early disputes can be understood. The debate around symbols versus neurons is unlikely to produce concrete results unless it prompts researchers on either side of the divide to learn about each other's methods and techniques. As the saying goes, all vectors are symbols, but not all symbols are vectors. Kahneman made the point that System 1's 1 and System 2's 2 are terms not coined by him which have a long history in psychology research 40, and that he prefers to use implicit versus explicit thinking and reasoning 41. He argued that S1, as the intuitive parallel system, is capable of understanding language, in contradiction with Joshua Bengio's account of deep learning's S1 and S2. Kahneman also stated that S2, as the sequential deliberative system, is most probably performing symbol manipulation, as argued by Gary Marcus in 52. In his next decade of AI paper, Marcus argues strongly in favor of hybrid systems and seeks to define what makes a system hybrid. Marcus's definition is important, inasmuch as the main problem of deep learning is a lack of definition. By contrast, Jan LeCun's recent attempt at defining deep learning, also presented at the JAI 2020 debate 41, falls short of what is a useful formal definition. For example, LeCun's definition fails to distinguish deep and shallow networks. All attempts to create such a bridge between S1 and S2 are at this point useful and should be commended given our state of lack of understanding of how the brain works. For example, attempts to create differentiable reasoning are useful, although we would require an important distinction be made, whether the purpose 24 is to achieve brain-like systems or to create robust AI. It is possible that these two goals may soon lead into two quite separate research directions, those who seek to understand and model the brain, and those who seek to achieve or improve AI. Maybe from that perspective, the field is too broad and will require further specialization. A common challenge that will persist, however, is embodied in the question how symbolic meaning emerges from large networks of neurons. Perhaps an important choice for neurosymbolic AI is the choice between combinatorial exact reasoning and common sense approximate reasoning. While learning is always approximate, reasoning can be approximate or precise. In a neurosymbolic system, it is possible to envisage the combination of efficient approximate reasoning jumping to conclusions with more deliberative and precise or normative symbolic reasoning. 94. Conclusions may be revised through learning from new observations and via communication with the system through knowledge extraction and precise reasoning. One might expect common sense to emerge as a result of this process of reasoning and learning, although the modeling and computing of common sense knowledge continues to be another challenge. From a practical perspective, a recipe for neurosymbolic AI might be: learning is carried out from data by neural networks, which use gradient descent optimization. Efficient forms of propositional reasoning can also be carried out by the network. Cf. Neural symbolic cognitive reasoning. 20. Rich first-order logic reasoning and extrapolation needs to be done symbolically from descriptions extracted from the trained network. Once symbolic meaning has emerged from the trained network, symbols can be manipulated easily by the current computer and can serve as constraints for further learning from data, as done in 79. This establishes a practical form of neurosymbolic cycle for learning and reasoning, which is feasible with the current technology. Of neurosymbolic AI, narrow AI based on neural networks, is already successful and useful in practice with big data. There is obvious value in this, as shown by the flourishing of the machine learning community and the growing Neurips conference community. Data scientists will do this work. In this paper, however, we have been discussing the science of what constitutes the fundamental ingredients of an intelligent system. 92. One such ingredient, current results show, is gradient-based optimization, used by deep learning to handle large amounts of data, but other ingredients are surely needed. At the JAI-2020 fireside conversation, a question was asked about the beauty and value of abstract compact symbolic representations such as fecal to may, or E equal to MC2. Joshua Bengio's answer, 25, was to point out that these must have come out of someone's brain, Isaac Newton and Albert Einstein to be precise. As Stephen Muggleton noted at another debate on the future of AI, his goal is to shorten the wait for the next Newton or Einstein or Alan Turing. Muggleton's bet is on the use of higher-order logic representations and meta-interpretive learning. With this example, we seek to illustrate that among highly respected researchers, the choice of ingredients may vary widely, from the need for much more realistic models of the brain to the need for ever more sophisticated forms of higher-order computation. With the neurosymbolic methodology, the goal is to develop neural network models with a symbolic interpretation. The key is how to learn representations neurally and make them available for use symbolically. As for example, when an AI system is asked to explain itself. In this paper, we have argued for modularity as an important ingredient, allowing one to refer to large parts of the network by the composition of symbols and relations among them. Having an adequate language for describing knowledge encoded in such networks is another important ingredient. We have argued for the use of first-order logic as this language, as a canonical form of representation, but also other forms of non-classical representation, such as non-monotonic and modal logic and logic programming. Once a complex network can be described symbolically, ideally in an abstract compact form as in E equals MC2, any style of deductive reasoning becomes possible. Reasoning is obviously another fundamental ingredient, either within or outside the network, exact or approximate. Finally, symbolic meaning can serve to improve performance of each one. In other words, symbols which have been learned, derived, or even invented can act as constraints on the large network and help improve learning performance as part of a positive cycle of learning and reasoning. Constraint satisfaction, as part of the interplay between learning and reasoning, is therefore another ingredient. Summary and future directions, with the above 5 ingredients of neurosymbolic AI gradient-based optimization, modularity, symbolic language, reasoning and constraint satisfaction. The reader will not be surprised to know that there are many outstanding challenges for neurosymbolic AI. First, no agreement exists on the best way of achieving the above combination of language and structure, of knowledge acquired by agents acting in an environment, and the corresponding reasoning that an agent must implement to achieve its goals. It is highly desirable, though, that the study of how to. In a recent paper, Pedro Domingos has shown that gradient descent achieves in effect a superposition of the training examples, similar to a data-dependent form of kernel 22, which in our view highlights the importance of the structure of neural networks and not just their function. 26. Achieve the combination of symbolic language and neural structure be principled, in that both language and structure should be formally specified with theorems proven about their correspondence or lack thereof. As done in the case of Noam Chomsky's language hierarchy, proofs are needed of the capability of different neural architectures at representing various logical languages. Proofs of correspondence have been shown between neural networks and propositional, non-monotonic, modal, epistemic, and temporal logic in 20. Similar proofs are required for first-order and higher-order logic. Henry Coutts spoke of 6 types of neurosymbolic AI and said that what is important next is to work out which specific technique is best. 42. Coutts made a distinction between expert knowledge and common sense knowledge, and noted that one should not necessarily want to backpropagate through expert knowledge. In this case, exact reasoning is needed, a la neural symbolic computing with knowledge extraction. An equally valid argument exists for differentiable reasoning in the case of common sense knowledge. The use of probabilistic languages or higher-order functional or logical languages may also have a central role in the technical debate, including on the best place for probability theory in S1 or S2 or both. In the meantime, we say, translate back and forth between representations, take a principled approach, adopt a language as a constraint on the structure, seek to provide explanations, combine reasoning and learning, and repeat. We also set out 3 immediate challenges for neurosymbolic AI, each capable of spinning out multiple research strands, which may become area-defining in the next decade. Challenge 1. First-order logic and higher-order knowledge extraction from very large networks that is provably sound and yet efficient. Explains the entire model and local network interactions, and accounts for different levels of abstraction. Challenge 2. Goal-directed common sense and efficient combinatorial reasoning about what has been learned by a complex deep network trained on large amounts of multimodal data. Challenge 3. Human network communication as part of a multi-agent system that promotes communication and argumentation protocols between the user and an agent that can ask questions and check her understanding. Whether or not an AI system truly understands what it does is another. 27. Recurring theme in the current debate. A point made recently by Jeff Hinton on this issue was that the goalposts keep changing. Before, if an AI system could translate a text, it would have been deemed as having understood the text, or if the system could sustain a conversation or describe the scene on an image. Now, none of these count as proper understanding. One may argue that it is the very definition of AI and the recent success of deep learning itself that have been responsible for this situation. Perhaps instead of proper understanding, a more forgiving approach might be to specify comprehensibility tests of the kind used in schools to evaluate the performance of students on various subjects, including, for example, foreign language comprehensibility tests as proposed by Stephen Muggleton. Neurosymbolic AI is in need of standard benchmarks and associated comprehensibility tests which could in a principled way offer a fair comparative evaluation with other approaches with a focus on learning from fewer data, reasoning about extrapolation, computational complexity, and energy consumption. Just as the field of AI progressed when challenging applications were set, such as chess playing, robotic football, self-driving vehicles, and protein folding, neurosymbolic AI should benefit from a similar challenge and benchmark being set by the AI community specifically for the next decade. References. 1. F. Arabshahi. Neurosymbolic artificial intelligence. Current trends. Neurosymbolic artificial intelligence. Current trends. MD Kamruzaman Sarkar A, Lujo B, Aaron Eberhard B, and Pascal Hitzler B, a Department of Computing Sciences, University of Hartford, CT, USA B, Department of Computer Science, Kansas State University, KS, USA email, Hitzler@ksu.edu. Abstract. Neurosymbolic artificial intelligence, the combination of symbolic methods with methods that are based on artificial neural networks, has a long-standing history. In this article, we provide a structured overview of current trends by means of categorizing recent publications from key conferences. The article is meant to serve as a convenient starting point for research on the general topic. Keywords: artificial neural networks, deep learning, knowledge representation and reasoning, neurosymbolic artificial intelligence. 1. What is neurosymbolic artificial intelligence? We should begin by attempting to define the subject matter. In a general sense, we understand neurosymbolic artificial intelligence, in short, NASI AI, to be a subfield of the field of artificial intelligence, in short, AI, which focuses on bringing together, for added value, the neural and the symbolic traditions in AI. Different spellings are currently in use that include neural, symbolic, and neurosymbolic, but also symbolic, subsymbolic, and others, which we consider to be equal. The term neural in this case refers to the use of artificial neural networks or connectionist systems in the widest sense. The term symbolic refers to AI approaches that are based on explicit symbol manipulation. This in general would include things like term rewriting, graph algorithms, and natural language question answering. It is often more narrowly understood, though, as a reference to methods based on formal logic, as utilized, for instance, in the subfield of AI called knowledge, representation, and reasoning. The lines easily blur, though, and for the purposes of this overview, we will not restrict ourselves to logic-based methods only. The general promise of NASI AI lies in the hopes of a best-of-both-worlds scenario, where the complementary strengths of neural and symbolic approaches can be combined in a favorable way. On the neural side, the desirable strengths would include trainability from raw data and robustness against faults in the underlying data, while on the symbolic side, one would like to retain the inherently high explainability and provable correctness of these systems, as well as the ease of making use of deep human expert knowledge in their design and function. In terms of functional features, utilizing symbolic approaches in conjunction with machine learning, in particular with deep learning, which is currently most busily researched on, one would hope to do better on issues like out-of-vocabulary handling, training from small datasets, recovery from errors, and in general, explainability, as opposed to systems that rely on deep learning alone. One of the fundamental differences between neural and symbolic AI approaches that is relevant for our discussion is that of representation of information within an AI system. For symbolic systems, representation is explicit, and in such terms that are in principle understandable by a human, e.g., a rule such as square x rectangle x, is readily understood and manipulated by symbolic means. In neural systems, though, representations are usually by means of weighted connections between many neurons and or simultaneous activations over a possibly large. Corresponding author, email, hitslurksu.edu, iOS Press, all rights reserved, MK Sarkar et al., Neurosymbolic Artificial Intelligence, Current Trends, Number of Neurons. In particular, a human observer would not be able to readily recognize what is being represented. In a deep learning context, these distributed representations are called embeddings, are learned during training, and are thus an explicit part of the architecture of the deep learning system. On a fundamental level, these two types of representing information are very different indeed. Representations by vectors of real numbers, or even more ephemerally, by connections weighted by real numbers, are in terms of entities within a high-dimensional and continuous, differentiable vector space, as required for standard learning algorithms, and are sometimes called subsymbolic representations. Symbolic representations, on the other hand, are by their nature discrete, and their natural relationships such as implications do not readily lend themselves to representation into a continuous space. Correspondingly, representational questions are often at the heart of the development of neurosymbolic approaches. Neurosymbolic AI has a long-standing history with even deeper roots, such as the McCulloch and Pitts 1943 landmark paper 53, that predate the field of AI. A lot of work on the topic is also not explicitly placed as NASI AI research, as the term itself only began to be used more systematically since the 1990s, and only very recently, as we will see below, has seen an increase in the context of major AI conferences. The general theme is also of importance in the context of the field of cognitive science 8. We know of one series of annual workshops on the topic, the International Workshop on Neural Symbolic Learning and Reasoning 2, that dates back to 2005. But in recent years, several additional venues have been established, including the AAAI Spring Symposium, AAAI, make on combining machine learning and knowledge engineering, the workshop on combining symbolic and subsymbolic methods and their applications, CSSA, the workshop on cognitive computation, integrating neural and symbolic approaches, COCO 5, and the Expo workshop. The remainder of this article will focus on providing an overview of recent research contributions to the NASI AI topic, as reflected in the proceedings of leading AI conferences. In order to provide a structured approach to this, we will group these recent papers in terms of a topic categorization proposed by Henry Kautz at an AAI 2020 address. We will also categorize the same recent papers according to a 2005 categorization proposal 7, and discuss and contrast the two. In section 2, we will first present the two categorizations. In section 3, we will then discuss the categorization results, and in section 4, we will provide a future outlook. 2. Categorizing neurosymbolic artificial intelligence. Henry Kautz, in his AAI 2020 Robert S. Engelmore Memorial Award lecture, discusses 5 categories for neurosymbolic AI systems in his discussion about the future of AI. Symbolic neurosymbolic refers to an approach where input and output are presented in symbolic form, however, all the actual processing is neural. This, in his words, is the standard operating procedure whenever inputs and outputs are symbolic. Symbolic neuro refers to a neural pattern recognition subroutine within a symbolic problem solver with exam players such as AlphaGo, AlphaZero, and current approaches to self-driving cars. Neurocompile symbolic refers to an approach where symbolic rules are compiled away during training. For example, like the 2020 work on deep learning for symbolic mathematics 44. This gap between the discrete and the continuous can be bridged by mathematical means, for example using Cantor space as Neurosymbolic refers to a cascading from a neural system into a symbolic reasoner, such as in the Neurosymbolic concept, Learner 51. Neurosymbolic refers to the embedding of symbolic reasoning inside a neural engine, where symbolic reasoning is understood as deliberative type 2 reasoning, as common, e.g. in business AI, and including an internal model of the system's state of attention. Concepts are decoded to symbolic entities in an attention schema when attention to these concepts is high. A goal in the attention schema then signals that deliberative reasoning be executed. Coutts presented these as 5 ways to bring together the neural and symbolic traditions. In the brief address, only a few examples were given of corresponding work. In a much older survey from 2005-7, work on NESI AI was classified according to 8 dimensions, grouped into 3 aspects. Interrelation. 1. Integrated versus hybrid. This was included mostly for delineation to hybrid systems. Indeed, the focus was entirely on integrated systems, where symbolic processing functionalities emerge from neural structures and processes. We will have the same emphasis here in 2. Neuronal versus connectionist. This aspect refers to the question whether the artificial neural network architecture is dominantly chosen in order to mimic biological neural networks, neuronal, versus a more technological approach that focused on desirable computational properties, as emphasized in the field of AI, connectionist. 3. Local versus distributed. This dimension refers to the question how symbolic information is represented within the neural system, namely whether this happens in a very localist way, one or a few dedicated neurons for a symbolic piece of knowledge, or in a highly distributed way, where representation consists of a large number of activation values and or weights. 4. Standard versus non-standard. This refers to the question whether a NESI AI system draws on artificial neural network architectures that are standard in the sense that they are widely used, propagate real numbers and nodes, compute only simple functions. Language. 5. Symbolic versus logical. This refers to the symbolic aspect of the NESI AI system, namely whether it is based on formal logic, logical, or on other symbolic processing, such as structured data types like graphs. 6. Propositional versus first order. For the logical aspect only, a delineation whether the underlying logic is propositional in nature, or more expressive like using higher arity predicates and quantifiers. Usage. 7. Extraction versus representation. This aspect refers to the information flow within the system, namely whether it primarily extracts symbolic information from a neural substrate, or whether it is primarily based on neural representations of symbolic knowledge. 8. Learning versus reasoning. This refers to the core functionality of the system, namely whether its focus is on machine learning or on automated symbolic reasoning. These 8 dimensions systems presented a view of the existing facets of the field in 2005, and examples were given for each of the dimensions. It is important to note that they were presented as dimensions and not as binary values, e.g. a system may fall anywhere on a continuum or even fall under both aspects of the dimension, i.e. span the dimension. We gather that the above listed dimensions are mostly self-explanatory as described. Further details can be found in 7. We started out on our investigations with the hypothesis that the NASI AI field has shifted focus in recent years, for example, rendering some of the 2005 dimensions obsolete, at least for the time being. We will discuss this in more detail below. At this stage, however, we remark that the CAUTS categories listed above seem to address only interrelation aspects. However, they cover these in a rather different way than the 2005 survey, with a focus on more precise architectural description of the system workflows. M.K. Sarkar et al., Neurosymbolic Artificial Intelligence, Current Trends. Figure 1. Neurosymbolic Learning Cycle according to 7. Interestingly though, a diagram presented in the 2005 survey C Figure 1 bears striking similarity to a diagram from CAUTS presentation 9, and indeed the CAUTS categories can be understood as utilizing part of this diagram as architectural substrate. And can serve by itself as a description of the essence of NASI AI. In particular, in the diagram note that I is situated on the symbolic side only, while training is situated only on the neural side, whereas reasoning can happen in either part. This is congruent with the best of both worlds perspective discussed earlier, as neural systems excel in training and in reasoning despite faults in the data, whereas symbolic systems excel in dealing with explicit knowledge, or serving human understandable explanations and support provably correct reasoning procedures. 3. Neurosymbolic Artificial Intelligence, Trends. For the purpose of this overview, and as a guide to recent literature, we had a look at mainstream and top-tier AI publications on NASI AI. We particularly looked at all published papers since 2011, except ICLR, which started in 2013, at top conference venues, and selected all original research papers on NASI AI. We disregarded in order to determine whether a paper falls into the NASI AI theme, we read the abstract, and sometimes the introduction. As mentioned before, we are aware that not all papers relevant for NASI AI are phrased in such terms. That is, we acknowledge that we may have missed a few relevant papers. It still seems a reasonable assumption that the sum of our selected papers represents a valid cross-section. We are also aware that restricting our attention to the above-mentioned 5 conferences leaves out a lot of relevant work. However, our focus was on recent, mainstream AI research, and we believe that our selection is reasonable for this purpose. It is conceivable that an analysis of publications at second-tier conferences and at workshops, or in other fields such as cognitive science, may provide a different picture. However, this was not the focus of our effort. The number of papers per year for each of the conferences is listed in Table 1. Several things are already remarkable. There was only 1 paper before 2016, and 41 papers since 2017. This alone indicates a shift towards a more mainstream adoption of the NASI AI research area. 9 at minute 35. M.K. Sarkar et al., Neurosymbolic Artificial Intelligence, Current Trends 201, Table 1, included paper counts per year and conference. Conference 2011, 2012, 2000, and 14, 2000. And 13, and 14, ICML, Neurips, I, Ichgai, ICLRNANA, total. Table 2, CAUTS, we. At 20% note to have lower, insights it seems into reasonable. The accepted total papers, but paper, selected 2000 and we. At 20% note to have lower, insights it seems into reasonable. We now manually assessed each of these papers as to their categorization with respect to the 2 schemes described in section 2. Doing so was not straightforward at all, as the descriptions of the categories are somewhat ambiguous, and it is not always clear which categorization would be most adequate. Still, from the resulting table 2, we can see that the first 4 CAUTS categories seem to provide a reasonably balanced perspective on the recent publications at these conferences. The 5th category, in fact, as also discussed by CAUTS in his address, was meant to be more forward-looking, a goal to aspire to in future research, so we're not surprised to not see any papers in this category. Categorizations with respect to the 2005 paper are given in Table 3 and the corresponding paper list in Table 4. A number of interesting observations can be made, and we go through each of them in the following. Regarding the integrated versus hybrid dimension, we are taking a similar tack as the 2005 survey. This is mostly for delineation, that is, we focus on integrated approaches. M.K. Sarkar et al., Neurosymbolic Artificial Intelligence, Current Trends, Table 4. 2005 survey dimensions paper classification. Dimensions with no entries have been omitted. Dimension, integrated, connectionist, local, distributed, standard, symbolic, logical, propositional, first order, extraction, representation, learning, reasoning. Regarding the neuronal versus connectionist dimension, it is noteworthy but perhaps unsurprising that there were no papers with emphasis on biological plausibility. Much of the current rise of NASI AI as a topic is fueled by deep learning, with a heavy emphasis on desirable computational functionality. The 2005 survey, however, shows a much more balanced picture, and indeed several early works such as 62 put much more emphasis on biological plausibility. However, it is also conceivable that such papers may not be considered as interesting by typical top-tier AI conference reviewers, and thus may seek publication outlets elsewhere. Similar considerations may apply on both the local versus distributed and the standard versus non-standard network architecture dimension. The recent heavy influence of deep learning, as well as our restriction to top-tier AI conferences, may explain the lopsided counts. Architectures are more or less standard deep learning architectures, and in these, knowledge is usually encoded in a distributed fashion using some kind of embeddings in multi-dimensional Euclidean space. In the 2005 survey, non-standard architectures and localist representations featured much much more prominently, and the previously cited 62 is also an example for such work. The counts on the symbolic versus logical dimension mark another departure from the situation described in the 2005 paper, which indicated a much stronger emphasis on formal logic in easy AI, as opposed to symbolic aspects. The lopsided count for first-order logic, as opposed to propositional logic, illustrates another shift in the subfield. It was discussed in the 2005 survey that a majority of NESI AI work appears to focus on propositional aspects. It was previously understood that developing NESI AI solutions is much harder when dealing with logics that are more expressive than propositional logics. John McCarthy indeed used the term propositional fixation of artificial neural networks to point this out. As early as 1988-52, that first-order logics beyond propositional play a more prominent role now is an indicator not only of new and enhanced capabilities, it also means that it is now possible to utilize logics that are of increasing relevance to the knowledge representation and reasoning subfield of AI. This is an excellent and promising development. The NA papers in this row in Table 3 indicate papers that did not involve logic at all, and instead used symbolic information that is not based on formal logic. On the extraction versus representation dimension, we notice that explicit work on extracting symbolic information from trained neural networks is less of an emphasis. This makes sense in the light of Kautz's categories above, where the first three categories would usually not involve an extraction aspect, and the fourth also may not. Knowledge extraction was a more prominent and emphasized topic in the past. On the learning versus reasoning dimension, we see a rather balanced count, which indicates that both aspects are not only important, as is to be expected, but can actually be done. In the past, both learning of first-order logic and reasoning with it was particularly difficult for systems based on artificial neural networks, but it appears that large strides have been made since the advent of deep learning and the growing understanding that these aspects are of importance for advancing the AI field. 10 symbolic but non-logical aspects were of course also relevant. See for example 34, where 7 out of 12 chapters did not touch on logical aspects. M.K. Sarkar et al. Neurosymbolic Artificial Intelligence. Current Trends 203. Table 5. Some desirable neurosymbolic features. Feature number of papers. Out of distribution handling 8. Interpretability 25. Error recovery 2. Learning from small data 7. Out of interest, we also looked at the selected 44 papers from a perspective of some possible benefits that may arise from integrating neural and symbolic systems, as indicated in the introduction. The following seem particularly pertinent to us. Out of distribution handling, whether the design system is able to extrapolate from training input data by means of utilizing symbolic means such as background knowledge, and thus is able to handle scenarios that are significantly different from the training input. Interpretability, whether the fact that the system is neurosymbolic is instrumental to enhance interpretability of system behavior or outputs, for example in terms of making system decisions more transparent and explainable for a human user. Error recovery, whether the design system makes use of its neurosymbolic design in order to recover more easily from erroneous decisions or outputs. Learning from small data, whether the fact that the system is neurosymbolic is instrumental in making the SIS-TEM trainable on less data than you would expect from a system that is not neurosymbolic. As for the previous categorizations, decisions how to classify each paper were often not clear-cut. We usually went with the author's own positioning, if there was one. The resulting counts can be found in Table 5. We see that interpretability aspects are most common. Only few papers address out-of-distribution issues or learning from small data, and there is hardly any work related to error recovery. 4. Paths forward. Like so many recent topic shifts in AI, it appears that the increased attention to NESI AI is mostly due to the rise of deep learning, which has shown tremendous success even in areas which previously were mostly in the domain of symbolic approaches, such as chess or Go game engines. There seems to be a reasonable expectation that deep learning solutions may be much more suitable to address the sub-symbolic-symbolic gap than previous connectionist machine learning technology. However, despite these advances and promises, it seems imperative to explicitly explore and understand the capabilities and limitations of deep learning-based symbolic manipulation as a basis for further progress on combining neural and symbolic aspects in a best-of-both-worlds fashion. Indeed, a systematic exploration of the extent to which deep learning systems can learn straightforward and well-understood symbol manipulation tasks would shed significant light on this question. Possible concrete symbol manipulation tasks for study can be found all over AI and computer science, and some authors have begun studying particular instances of some of these from a deep learning perspective. Examples would be deep learning approaches to term rewriting 15, list tree and graph manipulations 10,255,667, executing formal grammars 16, elementary algebra 1,144, logical deduction 404,146,505,476, planning 567,477, traveling salesman problem 68. In-depth studies along such lines promise to provide systems with elementary capabilities that can then be composed for more complex solutions or used as modules in larger AI systems 65. At the same time, it also appears to be important to contrast recent NESI AI publications with the much larger vision of the subfield. Indeed, the current promise of NESI AI lies in a favorable combination or integration of deep learning with symbolic AI approaches from the subfield of knowledge representation and reasoning, where complex formal logics dominate. As we have seen in Section 3, current NESI AI publications at top conferences involve complex logics to a much larger extent than was the case 2 decades ago. However, much of the work is still M.K. Sarkar and others, neurosymbolic artificial intelligence, current trends, mostly on the non-logical symbolic level, and desirable features which conceptually should arise out of a systematic use of neurosymbolic approaches, such as those listed in Table 5, are often still not met. Whether it is possible, or to what extent, to achieve a much stronger integration of complex formal logics and deep learning, including best of both worlds features, is of course currently not known, and is in fact in itself a fundamental research question that remains to be addressed. We thus posit that more emphasis is needed in the immediate future on deepening the logical aspects in NESI AI research even further, and to work towards a systematic understanding and toolbox for utilizing complex logics in this context. In particular, it would be helpful for advancing the field to conduct experiments with different levels of sophistication in the logical aspects. For example, systems that utilize flat annotations, metadata tags that are simply keywords, are essentially operating on the logical level of facts only. Examples for these would be 24,617,580. We can then ask the question whether such a system can be improved by using, say, a class hierarchy of annotations, such as schema.org, which corresponds to making use of a knowledge base with simple logical implications, i.e., subclass relationships. Some preliminary work along such lines can be found, for instance, in 5960. If the answer to this is affirmative, then more complex logical background knowledge can be attempted to be leveraged. The semantic web field of Research 35, for example, provides a whole hierarchy of logics on metadata 38 that can be utilized at the level at which a deep learning system can ingest them for added value, and can thus be an excellent playground for developing fundamental NESI AI capabilities. 36. An example for a currently emerging line of research compatible with the thoughts just laid out is that of so-called deep deductive reasoners. 29, which are deep learning systems trained to perform deductive reasoning over formal logics. The deductive reasoning task can be framed as classification. A statement is or is not a logical consequence of a given theory, or as regression, produce all logical consequences under some finiteness constraints. Different deep learning architectures have already been investigated on logics that range from very straightforward ones like RDF to first-order predicate logic. While the body of work is still relatively small, it is obvious from the published results, 92,830,313,949, that deductive reasoning is a very hard task for deep learning, and with increasing hardness and scalability issues as logics become more complex. 5. Conclusions. The recent rise in publications, events, and public addresses on NESI AI indicates that there is increasing awareness of the importance of the subfield in the mainstream AI community. Arguably, this is also happening at the inflection point in time when we are slowly beginning to explore and understand the inherent limitations of pure deep learning approaches. The use of additional background knowledge is a natural path to attempt to further improve deep learning systems, and much of this line of work falls into the NESI AI theme. The broad consensus seems to be that combining neural and symbolic approaches in the sense of NESI AI is at least a path forward to much stronger AI systems. Arguably, it may also turn out to be a major stepping stone towards human-level artificial intelligence. References 1. A Path Towards Autonomous Machine Intelligence, version 9.2, June 27, 2022. Jan LeCun, Courant Institute of Mathematical Sciences, New York University, Jan, at cs.nyu.edu. Metafundamental AI Research, janfb.com. June 27. Abstract. How could machines learn as efficiently as humans and animals? How could machines learn to reason and plan? How could machines learn representations of percepts and action plans at multiple levels of abstraction, enabling them to reason, predict, and plan at multiple time horizons? This position paper proposes an architecture and training paradigms with which to construct autonomous intelligent agents. It combines concepts such as configurable predictive world model, behavior driven through intrinsic motivation, and hierarchical joint embedding architectures trained with self-supervised learning. Keywords: artificial intelligence, machine common sense, cognitive architecture, deep learning, self-supervised learning, energy-based model, world models, joint embedding architecture, intrinsic motivation. One prologue. This document is not a technical nor scholarly paper in the traditional sense, but a position paper expressing my vision for a path towards intelligent machines that learn more like animals and humans, that can reason and plan, and whose behavior is driven by intrinsic objectives rather than by hardwired programs, external supervision, or external rewards. Many ideas described in this paper, almost all of them, have been formulated by many authors in various contexts in various form. The present piece does not claim priority for any of them, but presents a proposal for how to assemble them into a consistent whole. In particular, the piece pinpoints the challenges ahead. It also lists a number of avenues that are likely or unlikely to succeed. The text is written with as little jargon as possible and using as little mathematical prior knowledge as possible, so as to appeal to readers with a wide variety of backgrounds, including neuroscience, cognitive science, and philosophy, in addition to machine learning, robotics, and other fields of engineering. I hope that this piece will help contextualize some of the research in AI whose relevance is sometimes difficult to see. 2. Introduction. Animals and humans exhibit learning abilities and understandings of the world that are far beyond the capabilities of current AI and machine learning ML systems. How is it possible for an adolescent to learn to drive a car in about 20 hours of practice, and for children to learn language with what amounts to a small exposure? How is it that most humans will know how to act in many situations they have never encountered? By contrast, to be reliable, current ML systems need to be trained with very large numbers of trials, so that even the rarest combination of situations will be encountered frequently during training. Still, our best ML systems are still very far from matching human reliability in real-world tasks such as driving, even after being fed with enormous amounts of supervisory data from human experts, after going through millions of reinforcement learning trials in virtual environments, and after engineers have hardwired hundreds of behaviors into them. The answer may lie in the ability of humans and many animals to learn world models, internal models of how the world works. There are three main challenges that AI research must address today. 1. How can machines learn to represent the world, learn to predict, and learn to act largely by observation? Interactions in the real world are expensive and dangerous. Intelligent agents should learn as much as they can about the world without interaction by observation, so as to minimize the number of expensive and dangerous trials necessary to learn a particular task. 2. How can a machine reason and plan in ways that are compatible with gradient-based learning? Our best approaches to learning rely on estimating and using the gradient of loss, which can only be performed with differentiable architectures and is difficult to reconcile with logic-based symbolic reasoning. 3. How can machines learn to represent percepts and action plans in a hierarchical manner at multiple levels of abstraction and multiple timescales? Humans and many animals are able to conceive multi-level abstractions with which long-term predictions and long-term planning can be performed by decomposing complex actions into sequences of lower-level ones. The present piece proposes an architecture for intelligent agents with possible solutions to all three challenges. The main contributions of this paper are the following. 1. An overall cognitive architecture in which all modules are differentiable and many of them are trainable. Section 3, Figure 2, JEPA and hierarchical JEPA, a non-generative architecture for predictive world models that learn hierarchy of representations. Sections 4.6. 3. A non-contrastive self-supervised learning paradigm that produces representations that are simultaneously informative and predictable. Section 4. A way to use HJEPA as the basis of predictive world models for hierarchical planning under uncertainty. Section 4.7, Figures 16 and 17. Impatient readers may prefer to jump directly to the aforementioned sections and figures. 2.1. Learning world models. Human and non-human animals seem able to learn enormous amounts of background knowledge about how the world works through observation and through an incomprehensibly small amount of interactions in a task-independent, unsupervised way. It can be hypothesized that this accumulated knowledge may constitute the basis for what is often called common sense. Common sense can be seen as a collection of models of the world that can tell an agent what is likely, what is plausible, and what is impossible. Using such world models, animals can learn new skills with very few trials. They can predict the consequences of their actions. They can reason, plan, explore, and imagine new solutions to problems. Importantly, they can also avoid making dangerous mistakes when facing an unknown situation. The idea that humans, animals, and intelligent systems use world models goes back a long time in psychology. Craig, 1943. The use of forward models that predict the next state of the world as a function of the current state and the action being considered has been standard procedure in optimal control since the 1950s. Bryson and Ho, 1969, and bears the name model predictive control. The use of differentiable world models in reinforcement learning has long been neglected, but is making a comeback. See, for example, Levine. A self-driving system for cars may require thousands of trials of reinforcement. Learning to learn that driving too fast in a turn will result in a bad outcome, and to learn to slow down to avoid skidding. By contrast, humans can draw on their intimate knowledge of intuitive physics to predict such outcomes and largely avoid fatal courses of action when learning a new skill. Common sense knowledge does not just allow animals to predict future outcomes, but also to fill in missing information, whether temporally or spatially. It allows them to produce interpretations of percepts that are consistent with common sense. When faced with an ambiguous percept, common sense allows animals to dismiss interpretations that are not consistent with their internal world model and to pay special attention as it may indicate a dangerous situation and an opportunity for learning a refined world model. I submit that devising learning paradigms and architectures that would allow machines to learn world models in an unsupervised or self-supervised fashion and to use those models to predict, to reason, and to plan is one of the main challenges of AI and ML today. One major technical hurdle is how to devise trainable world models that can deal with complex uncertainty in the predictions. 2.2. Humans and animals learn hierarchies of models. Humans and non-human animals learn basic knowledge about how the world works in the first days, weeks, and months of life. Although enormous quantities of such knowledge are acquired quite quickly, the knowledge seems so basic that we take it for granted. In the first few months of life, we learn that the world is three-dimensional. We learn that every social communication helping with shindering, point, false perceptual beliefs, perception, production, actions, physics, objects, face tracking, 0, 1, 2, 3, 4, 5, 6, 7, 8, proto-imiton, immunal contagion, biological moon, object permanence, solidity, rigidity, stability, support, natural kind categories, gravity, inera conservant of momentum, Reynolds, goal-directed acons, shape constancy. Figure 1. This chart, courtesy of Emmanuel Dupuy, indicates at what age infants generally acquire various concepts about how the world works. It is consistent with the idea that abstract concepts, such as the fact that objects are subject to gravity and inertia, are acquired on top of less abstract concepts, like object permanence and the assignment of objects to broad categories. Much of this knowledge is acquired mostly by observation, with very little direct intervention, particularly in the first few weeks and months. Source of light, sound, and touch in the world has a distance from us. The fact that every point in a visual percept has a distance is the best way to explain how our view of the world changes from our left eye to our right eye, or when our head is being moved. Parallax motion makes depth obvious, which in turn makes the notion of object obvious, as well as the fact that objects include more distant ones. Once the existence of objects is established, they can be automatically assigned to broad categories as a function of their appearance or behavior. On top of the notion of object comes the knowledge that objects do not spontaneously appear, disappear, change shape, or teleport. They move smoothly and can only be in one place at any one time. Once such concepts are acquired, it becomes easy to learn that some objects are static, some have predictable trajectories, inanimate objects, some behave in somewhat unpredictable ways, collective phenomena like water, sand, tree leaves in the wind, etc., and some seem to obey different rules, animate objects. Notions of intuitive physics such as stability, gravity, inertia, and others can emerge on top of that. The effect of animate objects on the world, including the effects of the subject's own actions, can be used to deduce cause and effect relationships, on top of which linguistic and social knowledge can be acquired. Figure 1, courtesy of Emmanuel Dupuy, shows at what age infants seem to acquire basic concepts such as object permanence, basic categories, intuitive physics, etc. Concepts at higher levels of abstraction seem to develop on top of lower level ones. Equipped with this knowledge of the world, combined with simple hardwired behaviors and intrinsic motivations, objectives, animals can quickly learn new tasks, predict the consequences of their actions and plan ahead, foreseeing successful courses of actions and avoiding dangerous situations. But can a human or animal brain contain all the world models that are necessary for survival? One hypothesis in this paper is that animals and humans have only one world model engine somewhere in their prefrontal cortex. That world model engine is dynamically configurable for the task at hand. With a single configurable world model engine, rather than a separate model for every situation, knowledge about how the world works may be shared across tasks. This may enable reasoning by analogy, by applying the model configured for one situation to another situation. To make things concrete, I will directly dive into a description of the proposed model. Configurator, short-term memory world model, perception actor, critic, intrinsic cost, action, percept. Figure 2, a system architecture for autonomous intelligence. All modules in this model are assumed to be differentiable, in that a module feeding into another one through an arrow connecting them can get gradient estimates of the cost scalar output with respect to its own output. The configurator module takes inputs not represented for clarity from all other modules and configures them to perform the task at hand. The perception module estimates the current state of the world. The world model predicts possible future world states as a function of imagined action sequences proposed by the actor. The cost module computes a single scalar output called energy that measures the level of discomfort of the agent. It is composed of two submodules, the intrinsic cost, which is immutable, not trainable, and computes the immediate energy of the current state, pain, pleasure, hunger, etc., and the critic, a trainable module that predicts future values of the intrinsic cost. The short-term memory module keeps track of the current and predicted world states and associated intrinsic costs. The actor module computes proposals for action sequences. The world model and the critic compute the possible resulting outcomes. The actor can find an optimal action sequence that minimizes the estimated future cost and output the first action in the optimal sequence. See section 3. for details. 3. A model architecture for autonomous intelligence. The proposed architecture for autonomous intelligent agents is depicted in Figure 2. It is composed of a number of modules whose functions are described below. Some of the modules are configurable on the fly, that is, their precise function is determined by the configurator module. The role of the configurator is executive control. Given a task to be executed, it preconfigures the perception, the world model, the cost, and the actor for the task at hand. The configurator modulates the parameters of the modules it feeds into. The configurator module takes input from all other modules and configures them for the task at hand by modulating their parameters and their attention circuits. In particular, the configurator may prime the perception, world model, and cost modules to fulfill a particular goal. The perception module receives signals from sensors and estimates the current state of the world. For a given task, only a small subset of the perceived state of the world is relevant and useful. The perception module may represent the state of the world in a hierarchical fashion with multiple levels of abstraction. The configurator primes the perception system to extract the relevant information from the percept for the task at hand. The world model module constitutes the most complex piece of the architecture. Its role is twofold. 1. Estimate missing information about the state of the world not provided by perception. 2. Predict plausible future states of the world. The world model may predict natural evolutions of the world or may predict future world states resulting from a sequence of actions proposed by the actor module. The world model may predict multiple plausible world states parameterized by latent variables that represent the uncertainty about the world state. The world model is a kind of simulator of the relevant aspects of the world. What aspects of the world state is relevant depends on the task at hand. The configurator configures the world model to handle the situation at hand. The predictions are performed within an abstract representation space that contains information relevant to the task at hand. Ideally, the world model would manipulate representations of the world state at multiple levels of abstraction, allowing it to predict over multiple timescales. A key issue is that the world model must be able to represent multiple possible predictions of the world state. The natural world is not completely predictable. This is particularly true if it contains other intelligent agents that are potentially adversarial, but it is often true even when the world only contains inanimate objects whose behavior is chaotic or whose state is not fully observable. There are two essential questions to answer when building proposed architectures. 1. How to allow the world model to make multiple plausible prediction and represent uncertainty in the predictions. And 2. How to train the world model. The cost module measures the level of discomfort of the agent in the form of a scalar quantity called the energy. The energy is the sum of two energy terms computed by two submodules, the intrinsic cost module and the trainable critic module. The overall objective of the agent is to take actions so as to remain in states that minimize the average energy. The intrinsic cost module is hardwired, immutable, non-trainable, and computes a single scalar, the intrinsic energy that measures the instantaneous discomfort of the agent. Think pain, high intrinsic energy, pleasure, low or negative intrinsic energy, hunger, etc. The input to the module is the current state of the world produced by the perception module, or potential future states predicted by the world model. The ultimate goal of the agent is minimize the intrinsic cost over the long run. This is where basic behavioral drives and intrinsic motivations reside. The design of the intrinsic cost module determines the nature of the agent's behavior. Basic drives can be hardwired in this module. This may include feeling good, low energy, when standing up to motivate a late robot to walk, when influencing the state of the world to motivate agency, when interacting with humans to motivate social behavior, when perceiving joy in nearby humans to motivate empathy, when having full energy supplies hunger, satiety, when experiencing a new situation to motivate curiosity and exploration, when fulfilling a particular program, etc. Conversely, the energy would be high when facing a painful situation or an easily recognizable dangerous situation, proximity to extreme heat, fire, etc., or when wielding dangerous tools. The intrinsic cost module may be modulated by the configurator to drive different behavior at different times. The trainable critic module predicts an estimate of future intrinsic energies. Like the intrinsic cost, its input is either the current state of the world or possible states predicted by the world model. For training, the critic retrieves past states and subsequent intrinsic costs stored in the associative memory module and trains itself to predict the latter from the former. The function of the critic module can be dynamically configured by the configurator to direct the system towards a particular sub-goal as part of a bigger task. Because both submodules of the cost module are differentiable, the gradient of the energy can be backpropagated through the other modules, particularly the world model, the actor, and the perception, for planning, reasoning, and learning. The short-term memory module stores relevant information about the past, current, and future states of the world, as well as the corresponding value of the intrinsic cost. The world model accesses and updates the short-term memory while temporally predicting future or past states of the world, and while spatially completing missing information or correcting inconsistent information about the current world state. The world model can send queries to the short-term memory and receive retrieved values, or store new values of states. The critic module can be trained by retrieving past states and associated intrinsic costs from the memory. The architecture may be similar to that of key-value memory networks, Miller et al. 2016. This module can be seen as playing some of the same roles as the hippocampus invertebrates. The actor module computes proposals for sequences of actions and outputs actions to the effectors. The actor proposes a sequence of actions to the world model. The world model predicts future world state sequences from the action sequence and feeds it to the cost. Given a goal defined by the cost as configured by the configurator, the cost computes the estimated future energy associated with the proposed action sequence. Since the actor has access to the gradient of the estimated cost with respect to the proposed action sequence, it can compute an optimal action sequence that minimizes the estimated cost using gradient-based methods. If the action space is discrete, dynamic programming may be used to find an optimal action sequence. Once the optimization is completed, the actor outputs the first action or a short sequence of actions to the effectors. This process is akin to model predictive control. In optimal control, Bryson and Ho, 1969, C0 Cs, 0, Predsa, Swan, action A's, a 0 actor, figure 3, mode 1 perception action episode. The perception module estimates the state of the world, 0 equal to onc(x). The actor directly computes an action or a short sequence of actions through a policy module, a 0 equal to A0. This reactive process does not make use of the world model nor of the cost. The cost module computes the energy of the initial state F0 equal to C0 and stores the pairs 0 F0 in the short-term memory. Optionally, it may also predict the next state using the world model S1 equal to Pred 0A and the associated energy F0 equal to C0, so that the world model can be adjusted once the next observation resulting from the action taken becomes available. The actor may comprise two components. 1. A policy module that directly produces an action from the world state estimate produced by the perception and retrieved from the short-term memory. And 2. The action optimizer, as described above, for model predictive control. The first mode is similar to Daniel Kahneman's System 1, while the second mode is similar to System 2 Kahneman 2011. In the following, we will use specific symbols to represent various components in architectural diagrams, and brief explanation is given in Appendix 8.3.3, 3.1, Typical perception action loops. There are two possible modes that the model can employ for a perception action episode. The first one involves no complex reasoning and produces an action directly from the output of the perception and a possible short-term memory access. We will call it Mode 1 by analogy with Kahneman's System 1. The second mode involves reasoning and planning through the world model and the cost. It is akin to model predictive control, MPC, a classical planning and reasoning paradigm in optimal control and robotics. We will call it Mode 2 by analogy to Kahneman's System 2. We use the term reasoning in a broad sense here to mean constraint satisfaction or energy minimization. Many types of reasoning can be viewed as forms of energy minimization. Three point 1.1. Mode. A perception action episode for Mode 1 is depicted in Figure 3. The perception module through an encoder module extracts a representation of the state of the world 0 equal to nkex containing relevant information for the task at hand. Policy module, a component of the actor, produces an action as a function of the state of 0 equal to a's. The resulting action is sent to the effectors. The function of the policy module is modulated by the configurator, which configures it for the task at hand. The policy module implements a purely reactive policy that does not involve deliberate planning or prediction through the world model, yet its structure can be quite sophisticated. For example, in addition to the state 0, the policy module may access the short-term memory to acquire a more complete information about previous world states. It may use the short-term memory for the associative retrieval of an action given the current state. While the cost module is differentiable, its output f0 equal to c0 is indirectly influenced by previous actions through the external world. Since the world is not differentiable, one cannot backpropagate gradients from the cost through the chain cost perception world action. In this mode, gradients of the cost of 0 with respect to actions can only be estimated by polling the world with multiple perturbed actions, but that is slow and potentially dangerous. This process would correspond to classical policy gradient methods in reinforcement learning. During mode -1, the system can optionally adjust the world model. It runs the world model for one step, predicting the next state S1, then it waits for the next percept resulting from the action taken, and uses the observed world state as a target for the predictor. With the use of a world model, the agent can imagine courses of actions and predict their effect and outcome, lessening the need to perform an expensive and dangerous search for good actions and policies by trying multiple actions in the external world and measuring the result. 3.1.2 Mode 2 Reasoning and planning using the world model. A typical perception action episode for Mode 2 is depicted in Figure 4. 1. Perception. The perception system extracts a representation of the current state of the world 0 equal to peaks. The cost module computes and stores the immediate cost associated with that state. 2. Action proposal. The actor proposes an initial sequence of actions to be fed to the world model for evaluation A8. 3. Simulation. The world model predicts one or several likely sequence of world state representations resulting from the proposed action sequence S. 4. Evaluation. The cost module estimates a total cost from the predicted state sequence, generally as a sum over time, steps f equal to 1 trillion Cs. 5. Planning. The actor proposes a new action sequence with lower cost. This can be done through a gradient-based procedure in which gradients of the cost are backpropagated through the compute graph to the action variables. The resulting minimum cost action sequence is denoted A8. Full optimization may require iterating steps 2 to 5. 10. C0 Cs Cs plus 1 Cs minus 1 Cs. Action. Snula. Anula. Predsa sentat. Predsa st1. Ati1. Predsa stinta. St1. Figure 4. Mode 2. Perception action episode. The perception module estimates the state of the world 0. The actor proposes a sequence of actions A0, A art, A plus, art. The world model recursively predicts an estimate of the world state sequence using C plus 1 equal to predsat. The cost Cs computes an energy for each predicted state in the sequence, the total energy being the sum of them. Through an optimization or search procedure, the actor infers a sequence of actions that minimizes the total energy. It then sends the first action in the sequence, or the first few actions, to the effectors. This is, in effect, an instance of classical model predictive control with receding horizon planning. Since the cost and the model are differentiable, gradient-based methods can be used to search for optimal action sequences, as in classical optimal control. Since the total energy is additive over time, dynamic programming can also be used, particularly when the action space is small and discretized. Pairs of states computed by the encoder or predicted by the predictor, and corresponding energies from the intrinsic cost and the trainable critic are stored in the short-term memory for subsequent training of the critic. Acting. After converging on a low-cost action sequence, the actor sends the first action or first few actions in the low-cost sequence to the Vectors. The entire process is repeated for the next perception action episode. 7. Memory. After every action, the states and associated costs from the intrinsic cost and the critic are stored in the short-term memory. These pairs can be used later to train or adapt the critic. This procedure is essentially what is known as model predictive control (MPC) with receding horizon in the optimal control literature. The difference with classical optimal control is that the world model and the cost function are learned. In principle, any form of optimization strategy can be used for step 5, while gradient-based optimization methods can be efficient when the world model and cost are well behaved. Situations in which the action cost mapping has discontinuities may require to use other optimization strategies, particularly if the state and/or action spaces can be discretized. These strategies include dynamic programming, combinatorial optimization, simulate annealing and other gradient-free methods, heuristic search techniques, for example tree search with pruning, etc. To simplify, the process was described in the deterministic case. That is when there is no need to handle the possibility of multiple predictions for SAT plus 1, resulting from a given initial state SAT, and action 8. In real situations, the world is likely to be somewhat unpredictable. Multiple states may result from a single initial state and action due to the fact that the world is intrinsically stochastic, aleatoric uncertainty, or that the state representation set contains incomplete information about the true world state epistemic uncertainty, or that the world model's prediction accuracy is imperfect due to limited training data, representational power, or computational constraints. 11. C0 CCs plus 1, C0 preds C plus 1 preds. Action. A0 D0 AC8, AC plus 1, 8 1. Actor. Figure 5. Training a reactive policy module from the result of mode minus 2 reasoning. Using mode 2 is onerous because it mobilizes all the resources of the agent for the task at hand. It involves running the world model for multiple time steps repeatedly. This diagram depicts how to train a policy module A state to approximate the action that results from mode 2 optimization. The system first operates in mode 2 and produces an optimal sequence of actions A8. Then the parameters of the policy module are adjusted to minimize the divergence data stream, the optimal action, and the output of the policy module. This results in a policy module that performs amortized inference and produces an approximation for a good action sequence. The policy module can then be used to produce actions reactively in mode 1 or to initialize the action sequence prior to mode minus 2 inference and thereby accelerate the optimization. From mode 2 is onerous. The agent engine, it is configurable by the configurator for the task at hand, but it can only be used for a single task at a time. Hence, similarly to humans, the agent can only focus on one complex task at a time. Mode 1 is considerably less onerous, since it only requires a single pass through a policy module. The agent may possess multiple policy modules working simultaneously, each specialized for a particular set of tasks. The process described in Figure 5 shows how a policy module A's T can be trained to produce approximations of the optimal actions resulting from mode 2 reasoning. The system is run on mode 2, producing an optimal action sequence A art. Then, the parameters of the policy module A's T are updated to minimize a divergence measure between its output and the optimal action at that time ast. Once properly trained, the policy module can be used to directly produce an action in mode 1 as 0 equal to A's. It can also be used to recursively compute an initial action sequence proposal before mode 2 optimization. SAT plus 1 equal to preds, at plus 1 equal to A's pluses. The policy module can be seen as performing a form of amortized inference. This process allows the agent to use the full power of its world model and reasoning capabilities to acquire new skills that are then compiled into a reactive policy module that no longer requires careful planning. 3.1.4. Reasoning as energy minimization. The process of elaborating a suitable action sequence in mode 2 can be seen as a form of reasoning. This form of reasoning is based on simulation using the world model and 12. Intrinsic cost IC. IC1s, IC2s, X trainable cost, critic, TC. TC1s, TC2s, TCLs, S. Figure 6. Architecture of the cost module. The cost module comprises the intrinsic cost module, which is immutable ICI's left, and the critical trainable cost TCJ's right, which is trainable. Both IC and TC are composed of multiple submodules whose output energies are linearly combined. Each submodule imparts a particular behavioral drive in the agent. The weights in the linear combination, UI and VJ, are determined by the configurator module and allow the agent to focus on different subgoals at different times. Optimization of the energy with respect to action sequences. More generally, the actions can be seen as latent variables representing abstract transformations from one state to the next. This type of planning, though simulation and optimization may constitute the kind of reasoning that is most frequent in natural intelligence. Many classical forms of reasoning in AI can actually be formulated as optimization problems or constraint satisfaction problems. It is certainly the case for the kind of probabilistic inference performed with factor graphs and probabilistic graphical models. The proposed architecture is in fact a factor graph in which the cost modules are log factors. But the kind of reasoning that the proposed architecture enables goes beyond traditional logical and probabilistic reasoning. It allows reasoning by simulation and by analogy. 3.2. The cost module as the driver of behavior. The overall architecture of the cost module is shown in Figure 6. It is composed of the intrinsic cost module, which is immutable ICIs, and the critical trainable cost TCJs, which is trainable. Both IC and TC are composed of multiple submodules whose output energies are linearly combined. C's equal to ICs plus TCs. KICs equal to UEHs, equal to 1, 2, 13. LTCs equal to VJTCJs, equal to 3. Each submodule imparts a particular behavioral drive to the agent. The weights in the linear combination UI and VJ are modulated by the configurator module and allow the agent to focus on different subgoals at different times. The intrinsic cost module IC is where the basic behavioral nature of the agent is defined. It is where basic behaviors can be indirectly specified. For a robot, these terms will include obvious proprioceptive measurements corresponding to pain, hunger, and instinctive fears, measuring such things as external force overloads, dangerous electrical, chemical, or thermal environments, excessive power consumption, low levels of energy reserves in the power source, etc. They may also include basic drives to help the agent learn basic skills or accomplish its missions. For example, a legged robot may comprise an intrinsic cost to drive it to stand up and walk. This may also include social drives such as seeking the company of humans, finding interactions with humans and praises from them rewarding, and finding their pain unpleasant, akin to empathy in social animals. Other intrinsic behavioral drives, such as curiosity or taking actions that have an observable impact, may be included to maximize the diversity of situations with which the world model is trained. Gottlieb et al. 2013. The IC can be seen as playing a role similar to that of the amygdala in the mammalian brain and similar structures in other vertebrates. To prevent a kind of behavioral collapse or an uncontrolled drift towards bad behaviors, the IC must be immutable and not subject to learning nor to external modifications. The role of the critic TC is twofold: to anticipate long-term outcomes with minimal use of the onerous world model, and to allow the configurator to make the agent focus on accomplishing subgoals with a learned cost. In general, the behavioral nature of an AI agent can be specified in 4 ways. 1. By explicitly programming a specific behavior, activated when specific conditions are met. 2. By defining an objective function in such a way that the desired behavior is executed by the agent as a result of finding action sequences that minimize the objective. 3. By training the agent to behave a certain way through direct supervision. The agent observes the actions of an expert teacher and trains a mode 1 policy module to reproduce it. 4. By training the agent through imitation learning. The agent observes expert teachers and infers an objective function that their behavior appears to be optimizing when they act. This produces a critic submodule for Mode 2 behavior. This process is sometimes called inverse reinforcement learning. The second method is considerably simpler to engineer than the first one, because it merely requires to design an objective and not design a complete behavior. The second method is also more robust. A preordained behavior may be invalidated by unexpected conditions or a changing environment. With an objective, the agent may adapt its behavior. 14. Loss critic. Read. Short-term associative. Memory. Write. Intrinsic cost. State sequence. Figure 7. Training the critic. During planning episodes, the intrinsic cost module stores triplets, time, state, intrinsic energy, tau, into the associative short-term memory. During critic training episodes, the critic retrieves a past state vector S, together with an intrinsic energy at a later time, I6 plus delta. In the simplest scenario, the critic adjusts its parameters to minimize the divergence measure between the target I plus delta and the predicted energy tau. In more complex schemes, it may use combinations of future intrinsic energies as targets. Note that the state sequence may contain information about the actions planned or taken by the agent to satisfy the objective despite unexpected conditions and changes in the environment. The second method exploits the learning and inference abilities of the agent to minimize the amount of priors hardwired by the designer that are likely to be brittle. 3.3. Training the critic. An essential question is how to train the critic. The principal role of the critic is to predict future values of the intrinsic energy. To do so, it uses the short-term memory module. This module is an associative memory in which the intrinsic cost module stores triplets, time, state, intrinsic energy, tau. The stored states and corresponding intrinsic energies may correspond to a perceived state or to a state imagined by the world model during a mode -2 episode. The memory may retrieve a state tau given a time tau, and may retrieve an energy ICs given a time or a state S. With a suitable memory architecture, the retrieval may involve interpolations of keys and retrieved values. The process is shown in figure 7. The critic can be trained to predict future intrinsic energy values by retrieving a past state vector tau together with an intrinsic energy at a later time I plus delta. The parameters of the critic can then be optimized to minimize the prediction loss, for example, auroric star plus delta, TCs2. This is a simple scenario. More complex schemes can be devised to predict expectations of discounted future energies or distributions thereof. Note that the state vectors may contain information about the actions taken or imagined by the actor. At a general level, this is similar to critic training methods used in such reinforcement learning approaches as a 2C. 15. The short-term memory can be implemented as the memory module in a key-value memory network. A query vector is compared to a number of key vectors, producing a vector of scores. The scores are normalized and used as coefficients to output a linear combination of the stored values. It can be seen as a soft associative memory capable of interpolation. One advantage of it is that, with a proper allocation scheme of new key-value slots, it is capable of one-shot learning, yet can interpolate between keys and is end-to-end differentiable. 4. Designing and training the world model. Arguably, designing architectures and training paradigms for the world model constitute the main obstacles towards real progress in AI over the next decades. One of the main contributions of the present proposal is precisely a hierarchical architecture and a training procedure for world models that can represent multiple outcomes in their predictions. Training the world model is a prototypical example of self-supervised learning (SSL), whose basic idea is pattern completion. The prediction of future inputs or temporarily unobserved inputs is a special case of pattern completion. In this work, the primary purpose of the world model is seen as predicting future representations of the state of the world. There are three main issues to address. First, quite evidently, the quality of the world model will greatly depend on the diversity of state sequences or triplets of state, action, resulting state it is able to observe while training. Second, because the world is not entirely predictable, there may be multiple plausible world state representations that follow a given world state representation and an action from the agent. The world model must be able to meaningfully represent this possibly infinite collection of plausible predictions. Third, the world model must be able to make predictions at different timescales and different levels of abstraction. The first issue touches on one of the main questions surrounding learning for sequential decision processes. The diversity of the training set depends on the actions taken. The issue is discussed in section 4.10 below. The second issue is even more dire. The world is not entirely predictable. Hence, the world model should be able to represent multiple plausible outcomes from a given state, and optionally, an action. This may constitute one of the most difficult challenges to which the present proposal brings a solution. This issue is discussed in section 4.8 below. The third issue relates to the problem of long-term prediction and planning. Humans plan complex goals at an abstract level and use high-level descriptions of the world states and actions to make predictions. High-level goals are then decomposed into sequences of more elementary sequences of sub-goals, using shorter-term prediction from the world model to produce lower-level actions. This decomposition process is repeated all the way down to millisecond by millisecond muscle control, informed by local conditions. The question of how world models could represent action plans at multiple timescales and multiple levels of abstraction is discussed in section 4.6. 16. Self-supervised learning. Self-supervised learning (SSL) is a paradigm in which a learning system is trained to capture the mutual dependencies between its inputs. Concretely, this often comes down to training a system to tell us if various parts of its input are consistent with each other. For example, in a video prediction scenario, the system is given two video clips and must tell us to what degree the second video clip is a plausible continuation of the first one. In a pattern completion scenario, the system is given part of an input, image, text, audio signal, together with a proposal for the rest of the input, and tells us whether the proposal is a plausible completion of the first part. In the following, we will denote the observed part of the input by X and the possibly unobserved part by Y. Importantly, we do not impose that the model be able to predict Y from X. The reason is that there may be an infinite number of Y that are compatible with a given X. In a video prediction setting, there is an infinite number of video clips that are plausible continuations of a given clip. It may be difficult or intractable to explicitly represent the set of plausible predictions, but it seems less inconvenient to merely ask the system to tell us if a proposed Y is compatible with a given X. A general formulation can be done with the framework of energy-based models (EBM). The system is a scalar-valued function (FEX) that produces low energy values when and Y are compatible and high values when they are not. The concept is depicted in figure 8. Data points are black dots. The energy function produces low energy values around the data points and higher energies away from the regions of high data density, as symbolized by the contour lines of the energy landscape. The EBM implicit function formulation enables the system to represent multimodal dependencies in which multiple values of Y are compatible with a given X. The set of Y compatible with a given X may be a single point, multiple discrete points, a manifold, or a collection of points and manifolds. To enable mode 2 planning, a predictive world model should be trained to capture the dependencies between past and future percepts. It should be able to predict representations of the future from representations of the past and present. The general learning principle is as follows. Given two inputs X and Y, learn two functions that compute representations Sx equal to Gxx and Psi equal to Y, such that 1, Sx and Psi are maximally informative about X and Y, and 2 Psi can easily be predicted from Sx. This principle ensures a trade-off between making the evolution of the world predictable in the representation space and capturing as much information as possible about the world state in the representation. concepts could such an SSL system learn by being trained on video? Our hypothesis is that a hierarchy of abstract concepts about how the world works could be acquired. Learning a representation of a small image region such that it is predictable from neighboring regions surrounding it in space and time would cause the system to extract local edges and contours in images, and to detect moving contours in videos. Learning a representation of images such that the representation of a scene from one viewpoint is predictable from the representation of the same scene from a slightly different viewpoint would cause the system to implicitly represent a depth map. A depth map is the simplest way to explain how a view of a scene changes when the camera moves slightly. Once the notion of depth has been learned, it would become simple for the system to identify occlusion edges, as well as the collective motion of regions belonging to a rigid object. An implicit representation of 3D 17, fxy energy function, xyy, time or space, x, figure 8, self-supervised learning SSL, and energy-based models EBM. SSL is a learning paradigm in which a learning system is trained to fill in the blanks, or more precisely to capture the dependencies between observed parts of the input and possibly unobserved parts of the input. Part of the input signal is observed and denoted x in pink, and part of the input signal is either observed or unobserved and denoted y in blue. In a temporal prediction scenario, x represents past and present observations, and y represent future observations. In a general pattern completion scenario, various parts of the input may be observed or unobserved at various times. The learning system is trained to capture the dependencies between x and y through a scalar-valued energy function fxy that takes low values when x and y are consistent or compatible, and higher values if x and y are inconsistent or incompatible. In a video prediction scenario, the system would produce a low energy value if a video clip yields a plausible continuation of the video clip x. This energy-based model EBM formulation enables the system to represent multimodal dependencies in which multiple values of y, perhaps an infinite set, may be compatible with a given x. In the right panel, an energy landscape is represented, in which dark disks represent data points, and closed lines represent contours level sets of the energy function. Objects may spontaneously emerge. Once the notion of object emerges in the representation, concepts like object permanence may become easy to learn. Objects that disappear behind others due to parallax motion will invariably reappear. The distinction between inanimate and animate object would follow. Inanimate object are those whose trajectories are easily predictable. Intuitive physics concepts such as stability, gravity, momentum may follow by training the system to perform longer-term predictions at the object representation level. One may imagine that through predictions at increasingly abstract levels of representation and increasingly long timescales, more and more complex concepts about how the world works may be acquired in a hierarchical fashion. The idea that abstract concepts can be learned through prediction is an old one, formulated in various ways by many authors in cognitive science, neuroscience, and AI over several decades. The question is how to do it precisely. 18. Figure 9. Latent variable energy-based model LEBM. To evaluate the degree of compatibility between Z and Y, an EBM may need the help of a latent variable Z. The latent variable can be seen as parameterizing the set of possible relationships between an X and a set of compatible Y. Latent variables represent information about Y that cannot be extracted from X. For example, if X is a view of an object and Y another view of the same object, Z may parameterize the camera displacement between the two views. Inference consists in finding the latent that minimizes the energies equal to argmins EWXYZ. The resulting energy FWXY equal to EWXYZ only depends on X and Y. In the dual view example, inference finds the camera motion that best explains how X could be transformed into Y. 4.2 Handling uncertainty with latent variables. As was pointed out above, one of the main issues is enabling the model to represent multiple predictions. This may require the use of a latent variable. A latent variable is an input variable whose value is not observed but inferred. A latent variable can be seen as parameterizing the set of possible relationships between an X and a set of compatible Y. Latent variables are used to represent information about Y that cannot be extracted from X. Imagine a scenario in which X is a photo of a scene. And Y a photo of the same scene from a slightly different viewpoint. To tell whether X and Y are indeed views from the same scene, one may need to infer the displacement of the camera between the two views. Similarly, if X is a picture of a car coming to a fork in the road, and Y is a picture of the same car a few seconds later on one of the branches of the fork, the compatibility between X and Y depends on a binary latent variable that can be inferred. Did the car turn left or right? In a temporal prediction scenario, the latent variable represents what cannot be predicted about Y the future, solely from X, and from past observations the past. It should contain all information that would be useful for the prediction, but is not observable, or not knowable. I may not know whether the driver in front of me will turn left or right, accelerate or brake, but I can represent those options by a latent variable. A latent variable EBM, LVBM, is a parameterized energy function that depends on X, Y, and Z, EWXYZ. When presented with a pair X, Y, the inference procedure of the EBM finds a value of the latent variable Z that minimizes the energy. energy. Z equal to argmin u x y z z. 4. 19. This latent variable inference by minimization allows us to eliminate z from the energy function. Fwxe equal to min u x y z equal to ewxyz. ZZ5. Technically, Fwxy should be called a zero temperature free energy, but we will continue to call it the energy. 4.3 Training energy-based models. Before we discuss EBM training, it is important to note that the definition of EBM does not make any reference to probabilistic modeling. Although many EBMs can easily be turned into probabilistic models, for example through a Gibbs distribution, this is not at all a necessity. Hence, the energy function is viewed as the fundamental object and is not assumed to implicitly represent the unnormalized logarithm of a probability distribution. Training an EBM consists in constructing an architecture, for example a deep neural network, to compute the energy function Fwx, y parameterized with a parameter vector w. The training process must seek a w vector that gives the right shape to the energy function. For a given x from the training set, a well-trained Fwxy will produce lower energies for values of y I are associated with sin the training set, and higher energies to other values of y. Given a training sample xy, training an EBM comes down to devising a suitable loss functional Lxy, Fwxy, which can be expressed directly as a function of the parameter vector Lxyw, and such that minimizing this loss will make the energy of the training sample Fwxi lower than the energies Fwxy of any y different from y. Making the energy of the training sample low is easy. It is sufficient for the loss to be an increasing function of the energy, and for the energy to have a lower bound. The difficult question is how to ensure that the energies of y different from y are higher than the energy of y, without a specific provision to ensure that Fwxe greater than Fwxy. Whenever y equal to y, the energy landscape may suffer a collapse. Given an x, the energy landscape could become flat, giving essentially the same energy to all values of y. What EBM architectures are susceptible to collapse? Whether an EBM may be susceptible to collapse depends on its architecture. Figure 10 shows a number of standard architectures and indicates whether they can be subject to collapse. A regular predictive or deterministic generative architecture, figure 10a, cannot collapse. For any x a single year is produced, the energy is 0 whenever equal to y. Any different from y will have a higher energy, as long as y is strictly larger than 0, whenever y is different from y. A generative latent variable architecture, non-deterministic generative, figure b, can collapse when the latent variable has too much information capacity. When the latent variable z varies over the set z, the prediction y varies over a set preds x z, which must match the set of y that are compatible with x. If z is too large, then the region of low energy y may be larger than the region of high data density. If z has the same dimension as y, the system could very well give 0 energy to the entire y space. An autoencoder, AE, figure 10c, can collapse when the representation cy has too much information capacity. For example, if the dimension of sy is equal or higher than that, 20, a prediction, regression no collapse b generative latent variable architecture, can collapse. See autoencoder can collapse. D-joint embedding architecture can collapse. Figure 10, a few standard architectures and their capacity for collapse. A. Deterministic generative architecture cannot collapse because it can only produce a single output. For a given x, only one value of y may have 0 energy, y equal to y. Other values of y will have higher energy if du y is larger than 0 when equal to y. B. Non-deterministic generative architecture can collapse when the latent variable has excessive information capacity. If for a given x and for all y, there exists a z that produces 0 prediction energy. For example, if z has the same or higher dimension as y, the entire y space will have low energy. The information capacity of z should be just enough so that varying z over its set will produce all the plausible y for a given x. C. Autoencoder can collapse if the system learns the identity function, or if it can correctly reconstruct a region of y space that is much larger than the region of high data density, thereby giving low energy to an overly large region. D. Simple joint embedding architecture can collapse if the encoders ignore the inputs and produce representations that remain constant and equal, or if the encoders are invariant over overly broad regions of the space. Of y, the A&E could learn the identity function, producing a reconstruction error equal to 0 over the entire y space. Lastly, a joint embedding architecture GA figure 10d can collapse when the information carried by Sx and or psi are insufficient. If the encoders ignore the inputs and produce constant and equal codes Sx equal to psi, the entire space will have 0 energy. These are but a few examples of architectures. How do we design the loss to prevent collapse? There are two approaches, contrastive methods and regularized methods. In the following, I will argue that contrastive methods have flaws, and that regularized, non-contrastive methods are much more likely to be preferable in the long run. Contrastive methods consist in using a loss functional, whose minimization has the effect of pushing down How do we design the loss to prevent collapse? There are two approaches, contrastive methods and regularized methods. In the following, I will argue that contrastive methods have flaws, and that regularized, non-contrastive methods are much more likely to be preferable in the long run. Contrastive methods consist in using a loss functional, whose minimization has the effect of pushing down on the energies of training samples xy, and pulling up on the energies of suitably hallucinated, contrastive samples xy. The contrastive sample y should be picked in such a way as to ensure that the EBM assigns higher energies to points outside the regions of high data density. This translates into designing a loss that is an increasing function of fwxy, and a decreasing function of fwxy, at least whenever fwxy is not sufficiently higher than fwxy. There are many such contrastive loss. 21. Y. Low energy region contrastive method. Y. Contrastive samples. X. Y. X. Training samples regularized method. X. Figure 11. Contrastive and regularized methods for EBM training. A conceptual diagram of an energy landscape is shown on the left. Training samples are blue dots. The region of low energy is shown in orange, a level set of the energy function. Contrastive methods, top right, push down on the energy of training samples, blue dots, and pulls up on the energies of suitably placed contrastive samples. Figure 11. Contrastive and regularized methods for EBM training. A conceptual diagram of an energy landscape is shown on the left. Training samples are blue dots. The region of low energy is shown in orange, a level set of the energy function. Contrastive methods, top right, push down on the energy of training samples, blue dots, and pulls up on the energies of suitably placed contrastive samples, green dots. Regularized methods, bottom right, push down on the energy of training samples and use a regularizer term that minimizes the volume of low energy regions. This regularization has the effect of shrink wrapping the regions of high data density within the low energy regions to the extent that the flexibility of the energy function permits it. One issue with contrastive methods is that the energy will only be pulled up wherever contrastive samples have been placed. One must devise methods that preferentially place contrastive samples in regions of low energy, which is what Monte Carlo and MCMC methods do. However, a disadvantage of contrastive methods is that the number of contrastive samples necessary to make an energy surface adopt a good shape may grow exponentially with the dimension of Y space. Functions, some of them taking a single triplet x, y, y, others requiring a batch of positive and contrastive values of y. A simple example of contrastive loss functions is as follows. The wxy equal to hfwxe if wxe me 6, where here's an increasing function of fwxe and a decreasing function of fwxe, whenever the latter is less than the former plus a positive margin function, me. A simple instance of such loss is the distance-dependent hinge loss, lwxy equal to wxy fwxy plus yor 2 plus 7, where a plus is the identity when a is positive and 0 otherwise. This makes the energy grow at least quadratically with the distance to the data manifold. Other contrastive loss, 22. Functionals take multiple contrastive samples into consideration. The wxy equal to hfwxe fwxe which must be an increasing function of the first argument and a decreasing function of all other arguments. An example of such loss is the popular inference, lwxy equal to fwxe plus log xp wxe plus kxp fwxk equal to 9. Contrastive methods are very popular, particularly for Siamese network architectures trained with pairs where G is a distorted or corrupted version of Yandy, another random or suitably chosen training sample. This includes such methods as the original Siamese net, as well as more recent methods including Glim, Perl, Moco, Simple R, CPT, and others. Contrastive methods also include such classical methods as probabilistic models trained with maximum likelihood that are not automatically normalized. Contrastive samples often produced using Monte Carlo methods, Markov chain Monte Carlo methods, or approximate versions thereof, such as contrastive divergence. Generative adversarial networks can also be seen as contrastive methods in which the Y are produced by the trainable generator network. Denoising autoencoders and their special case masked autoencoders are also examples of contrastive training methods in which the II is generated by corrupting the clean Y. A more detailed discussion of various contrastive methods is given in Appendix 8.3.3. But there are two main issues with contrastive methods. First, one has to design a scheme to generate or pick suitable Y. Second, when used in a high-dimensional space, and if the EBM is flexible, it may require a very large number of contrastive samples to ensure that the energy is higher in all dimensions unoccupied by the local data distribution. Because of the curse of dimensionality, in the worst case, the number of contrastive samples may grow exponentially with the dimension of the representation. This is the main reason why I will argue against contrastive methods. Regularized methods for EBM training are much more promising in the long run than contrastive methods because they can eschew the curse of dimensionality that plagues contrastive methods. They consist in constructing a loss functional that has the effect of pushing down on the energies of training samples and simultaneously minimizing the volume of Y space to which the model associates a low energy. The volume of the low energy region is measured by a regularization term in the energy and/or in the loss. By minimizing this regularization term while pushing down on the energies of data points, the regions of low energy will shrink wrap the regions of high data density. The main advantage of non-contrastive regularized methods is that they are less likely than contrastive methods to fall victim to the curse of dimensionality. The main question is precisely how to design such volume minimizing regularizers. The answer depends greatly on the architecture of the model, which is discussed in the next sections. However, non-contrastive methods have existed for a long time. Examples include sparse modeling, sparse autoencoders, and autoencoders with noisy latent variables such as VE. It is important to note that contrastive and regularized methods are not incompatible with each other and can be used simultaneously on the same model. How would regularized methods apply to the architectures of Figure 10 BD 23? In the latent variable generative architecture, restricting the information capacity of Z will restrict the volume of Y space that can take low energy. If Z is discrete with possible K values, at most K points in Y space will have zero energy. If Z is a manifold of dimension D, then the region of Y space with zero energy will have at most D dimensions. Similarly, in the autoencoder architecture, restricting the information capacity of SY will restrict the volume of Y space that can be reconstructed with low energy. Lastly, in the joint embedding architecture, maximizing the information that SX contains about X and SY contains about Y will minimize the volume of Y space that can take low energy. In the following, we will focus on an architecture for SSL, the joint embedding predictive architectures JEPA, which can be seen as a combination of the joint embedding architecture and the latent variable generative architecture. The JEPA is non-generative in that it does not actually predict Y, but predicts the representation of Y psi from that of X SX. 4.4 Joint embedding predictive architecture JEPA. The centerpiece of this paper is the joint embedding predictive architecture JEPA. JEPA is not generative in the sense that it cannot easily be used to predict Y from X. It merely captures the dependencies between X and Y without explicitly generating predictions of Y. A generic JEPA is shown in Figure 12. The two variables Xangier fed to two encoders producing two presentations SX and psi. These two encoders may be different. They are not required to possess the same architecture, nor are they required to share their parameters. This allows X and Y to be different in nature, for example video and audio. A predictor module predicts the representation of Y from the representation of X. The predictor may depend on a latent variable Z. The energy is simply the prediction error in representation space. EUXYZ equal to DC preds XX 10. The overall energy is obtained by minimizing over Z. Z equal to argmin EUXYZ equal to argmin DC preds X Z. ZZZ. FWXE equal to min UXYs equal to DC preds XX Z. ZZ. 11, 12, 13. The main advantage of JEPA is that it performs predictions in representation space, eschewing the need to predict every detail of Y. This is enabled by the fact that the encoder of Y may choose to produce an abstract representation from which irrelevant details have been eliminated. But there are two ways a JEPA may represent the multiplicity of values of Y compatible with X. The first one is invariance properties of the Y encoder. The second one is the latent variable Z, as explained below. Multimodality through encoder invariance. The encoder function psi equal to nqi may have invariance properties. If all the Y's in a set map to the same value of psi, all those Y's will have identical energies. With JEPA, we lose the ability to generate outputs, but we gain a powerful way to represent multimodal dependencies between inputs and outputs. 24. Figure 12. The joint embedding predictive architecture JEPA consists of two encoding branches. The first branch computes SX, a representation of X, and the second branch psi, a representation of Y. The encoders do not need to be identical. A predictor module predicts psi from SX with the possible help of a latent variable Z. The energy is the prediction error. Simple variations of the JEPA may use no predictor, forcing the two representations to be equal, or may use a fixed predictor with no latent, or may use simple latents such as discrete variables. The main advantage of JEPA is that it performs predictions in representation space, eschewing the need to predict every detail of Y, and enabling the elimination of irrelevant details by the encoders. More precisely, the main advantage of this architecture for representing multimodal dependencies is twofold. 1. The encoder function psi equal to nqi may possess invariance properties that will make it produce the same psi for a set of different Y. This makes the energy constant over this set and allows the model to capture complex multimodal dependencies. 2. The latent variable Z, when varied over a set Z, can produce a set of plausible predictions pred Z's equal to psi equal to pred Z's. If X is a video clip of a car approaching a fork in the road, SX and psi may represent the position, orientation, velocity, and other characteristics of the car before and after the fork respectively, ignoring irrelevant details such as such as the trees bordering the road or the texture of the sidewalk. Z may represent whether the car takes the left branch or the right branch of the road. Multimodality through latent variable predictor. The predictor may use a latent variable ZTO capture the information necessary to predict SY that is not present in SX. When Z is varied over a set Z, the predictor produces a set of plausible predictions. Preds X equal to psi equal to preds X SZZ. For example, if X is a video clip of a car approaching a fork in the road, SX and psi may represent the past and future positions, orientations, velocities, and other characteristics of the car, ignoring irrelevant details such as the trees bordering the road or the texture of the sidewalk. The latent Z may be a binary variable, indicating whether the car takes the left branch Z equal to 0 or the right branch Z equal to 1 if the road. If the car takes the left branch, the values equal to 0 will produce a lower energy DZC than Z equal to 1. 4.5. Training a JEPA. Like any EBM, a JEPA can be trained with contrastive methods, but, as pointed out above, contrastive methods tend to become very inefficient in high dimension. The relevant. 25. Minimize prediction. Error. Maximize information content. Maximize information content. Minimize information content. Figure 13. Non-contrastive training of JEPA. The main attraction of JEPAs is that they can be trained with non-contrastive methods. The basic principle of such training is that 1 SX should be maximally informative about X, 2 psi should be maximally informative about Y, 3 psi should be easily predictable from SX, and 4 Z should have minimal information content. Criteria 1, 2, and 4 collectively prevent a collapse of the energy function. Examples of such non-contrastive criteria for JEPA training include Vic-Craig and Barlow twins. As with every EBM, JEPAs can also be trained with contrastive methods, but doing so runs into the curse of dimensionality and limits the practical dimension of psi. Dimension here is that of psi, which may be considerably smaller than Y, but still too high for efficient training. What makes JEPAs particularly interesting is that we can devise non-contrastive methods to train them. As explained in section 4.3, non-contrastive methods use regularizers that measure the volume of space that can take low energy values. In the case of the JEPA, this can be done through 4 criteria, as depicted in figure 13. 1. Maximize the information content of SX about X. 2. Maximize the information content of psi about Y. 3. Make psi easily predictable from SX. 4. Minimize the information content of the latent variable Z used in the prediction. Criteria 1 and 2 prevent the energy surface from becoming flat by informational collapse. They ensure that SX and SY carry as much information as possible about their inputs. Without these criteria, the system could choose to make SX and psi constant, or weakly informative, which would make the energy constant of large swaths of the input space. Criterion 3 is enforced by the energy term DZC, and ensures that it is predictable from X in representation space. Criterion 4 prevents the system from falling victim to another type of informational collapse by forcing the model to predict psi with as little help from the latent as possible. This, 26, type of collapse can be understood with the following thought experiment. Imagine that Z has the same dimension as psi. Assume that the predictor is a parameterized function, for example, a neural net, that can choose to ignore SX and to simply copy Z on its output SI equal to Z. For any psi, it is possible to set Z equal to psi, which would make the energy dZ. This sentence describes a simple everyday action without conveying any particular strong emotion, so I speak in an enjoyable manner. C0. This corresponds to a totally flat and collapsed energy surface. How do we prevent this collapse from happening? By limiting or minimizing the information content of the latent variable. How can this be done? By making Z discrete, low-dimensional, sparse, or noisy, among other methods. A few concrete examples may help build an intuitive understanding of the phenomenon. Suppose that dZ, psi equal to RC, SORA2, and that Z is discrete with k possible integer values 0, k1. For a given X, there can be only k possible values of psi. Preds X 0, Preds X, k1. Hence, these can be the only values of psi with 0 energy, and there are only k of them. Consider a point psi that starts from Preds X0 and moves towards Preds X1. Its energy will start from 0, increase quadratically as psi moves away from Preds X0, until psi. When psi becomes closer to Preds X1 than to Preds X0, the energy will decrease, reaching 0 when psi reaches Preds X1. In representation space, the energy will be the minimum of k quadratic energy wells. Similarly, imagine that Z is a vector whose dimension d is lower than that of psi. Then, assuming that Preds X Z is a smooth function of Z, the set of possible predictions will be at most a d-dimensional manifold in the space of psi. More to the point, imagine that the energy function is augmented by a regularization term on Zoff the form RZ equal to alpha equal 2 d or 0, that is the L1 norm of Z. This will drive ZTO be sparse. As with classical sparse coding, this will cause the region of low energy to be approximated by a union of low-dimensional manifolds, a union of low-dimensional linear subspaces if Preds X Z is linear in Z, whose dimension will be minimized by the L1 regularizer. Making Z a stochastic sample from a distribution whose entropy is maximized will also have a proper regularization effect. This is the basis of variational autoencoders and similar models. A more complete discussion of regularizers that can minimize the information content of latent variables is beyond the scope of this paper. For now, we can mention 4 classes of methods: discretization, quantification, for example, as in VQ, Vey, Walker et al. 2021; dimensionality, rank minimization, for example, as in implicit rank minimizing A&E, Jing et al. 2020; sparsification, as in linear sparse modeling, Olshausen and Field, 1996; Lister, Gregor and LeCun, 2010 billions; and nonlinear sparse modeling, Evtimova and LeCun; and fuzzification, as in noisy A. Doi et al. 2007; Vey, Kingma and Welling, 2013; and variance used in control problems, Henaf et al. 2019. The ability of the JEPA to predict in representation space makes it considerably preferable to generative models that directly produce a prediction of Y. In a video prediction scenario, it is essentially impossible to predict every pixel value of every future frame. The details of the texture on a carpet, the leaves of a tree moving in the wind, or the ripples on a pond cannot be predicted accurately, at least not over long time periods, and not without consuming enormous resources. A considerable advantage of JEPA is that it can choose to. 27. Figure 14. Training a JEPA with Vic-Craig. Vic-Craig is a non-sample contrastive method for training embeddings. The information content of the representations, SX and psi, is maximized by first mapping them to higher dimensional embeddings, Vx and Vy, through an expander, for example, a trainable neural net with a few layers. The loss function drives the covariance matrix of the embeddings towards the identity, for example, computed over a batch. Vic-Craig can be seen as a dimension contrastive method as opposed to sample contrastive methods. Ignore details of the inputs that are not easily predictable. Yet, criteria 1 and 2 will ensure that the information content of the ignored details are kept to a minimum. How can we implement criteria 1 and 2? In other words, given a parameterized deterministic encoding function psi equal to NCWY, how do we maximize the information content of psi? If enc y is invertible, psi contains all the information about y, but that may be suboptimal for criterion 3, as psi will contain many irrelevant or hard to predict details about y. More precisely, psi is maximally informative about y if the function NCWY is minimally surjective, that is if the volume of sets of y that map to the same psi is minimal. The same reasoning applies to the zencoder. To turn this criterion into a differentiable loss, we need to make some assumptions. 4.5.1 Vic-Craig. The Vic-Craig method, Bards et al. 2021, makes a few assumptions about SEC. A graphical representation is shown in figure 14. To maximize the information content of SX, Vic-Craig uses the following 2 subcriteria. 1. The components of SX must not be constant. 2. The components of SX must be as independent of each other as possible. This is approximated by first non-linearly mapping SX and psi to high-dimensional embeddings Vx and Vy through a trainable expander module, for example a neural net with a few layers, and using a loss function with 2 differentiable loss terms computed over a batch of samples. 28. 1. Variance, a hinge loss that maintains the standard deviation of each component of psi and Vy above a threshold over a batch. 2. Covariance, a covariance loss in which the covariance between pairs of different components of Vy are pushed towards 0. This has the effect of decorrelating the components of Vy, which will in turn make the components of psi somewhat independent. The same criteria are applied to SX and Vx separately. The third criterion of Vic-Craig is the representation prediction error, dz psi. In the simplest implementations of Vic-Craig, the predictor is constant equal to the identity function, making the representations invariant to the transformation that turns X into Y. In more sophisticated versions, the predictor may have no latent variable, or may depend on a latent variable that is either discrete, low-dimensional, or stochastic. The fourth criterion is necessary when the predictor uses a latent variable whose information content must be minimized, for example a vector whose dimension approaches or surpasses that of psi. A simple instantiation of Vic-Craig to learn invariant representations consists in making Z and Y be different views or distorted versions of the same content, setting the predictor to the identity function, and defining dz. This sentence describes a simple everyday action without conveying any particular strong emotion, so I speak in an enjoyable manner. Psi DCS, CSX2. Inferring the latent variable through gradient-based methods may be onerous, but the computational cost can be greatly reduced by using amortized inference, as explained in Appendix 8.3.3. While contrastive methods ensure that representations of different inputs in a batch are different, VigReg ensures that different components of representations over a batch are different. VigReg is contrastive over components, while traditional contrastive methods are contrastive over vectors, which requires a large number of contrastive samples. But the most promising aspect of JEPA trained with VigReg and similar non-contrastive methods is for learning hierarchical predictive world models, as we examine in the next section. Biasing a JEPA towards learning useful representations. With the training criteria listed above, the JEPA finds a trade-off between the completeness and the predictability of the representations. What is predictable and what does not get represented is determined implicitly by the architectures of the encoders and predictor. They determine the inductive bias that defines what information is predictable or not. But it would be useful to have a way to bias the system towards representations that contain information relevant to a class of tasks. This can be done by adding prediction heads that take SUI as input and are trained to predict variables that are easily derived from the data and known to be relevant to the task. 4.6. Hierarchical JEPA JEPA. JEPA models trained non-contrastively may constitute our best tool for learning world models that are able to learn relevant abstractions. When trained with VigReg and similar, 29. JEPA 2, JEPA 1, XY figure 15, hierarchical JEPA. The ability of the JEPA to learn abstract representations in which accurate prediction can be performed allows hierarchical stacking. In this diagram, JEPA 1 extracts low-level representations and performs short-term predictions. JEPA 2 takes the representations extracted by JEPA 1 as inputs and extracts higher-level representations with which longer-term predictions can be performed. More abstract representations ignore details of the inputs that are difficult to predict in the long term, enabling them to perform longer-term predictions with coarser descriptions of the world state. Criteria: a JEPA can choose to train its encoders to eliminate irrelevant details of the inputs so as to make the representations more predictable. In other words, a JEPA will learn abstract representations that make the world predictable. Unpredictable details will be eliminated by the invariance properties of the encoder, or will be pushed into the predictor's latent variable. The amount of information thereby ignored will be minimized by the training criteria and by the latent variable regularizer. It is important to note that generative latent variable models are not capable of eliminating irrelevant details other than by pushing them into a latent variable. This is because they do not produce abstract and invariant representations of Y. This is why we advocate against the use of generative architectures. The capacity of JEPA to learn abstractions suggests an extension of the architecture to handle prediction at multiple timescales and multiple levels of abstraction. Intuitively, low-level representations contain a lot of details about the input and can be used to predict in the short term, but it may be difficult to produce accurate long-term predictions with the same level of details. Conversely, high-level, abstract representation may enable long-term predictions, but at the cost of eliminating a lot of details. 30. Let's take a concrete example. When driving a car, given a proposed sequence of actions on the steering wheel and pedals over the next several seconds, drivers can accurately predict the trajectory of their car over the same period. The details of the trajectory over longer periods are harder to predict because they may depend on other cars, traffic lights, pedestrians, and other external events that are somewhat unpredictable. But the driver can still make accurate predictions at a higher level of abstraction, ignoring the details of trajectories, other cars, traffic signals, etc. The car will probably arrive at its destination within a predictable time frame. The detailed trajectory will be absent from this level of description, but the approximate trajectory, as drawn on a map, is represented. A discrete latent variable may be used to represent multiple alternative routes. Figure 15 shows a possible architecture for multi-level, multi-scale world state prediction. Variables x0, x1, x2 represent a sequence of observations. The first level network, denoted JEPA 1, performs short-term predictions using low-level representations. The second level network, JEPA 2, performs longer-term predictions using high-level representations. One can envision architectures of this type with many levels, possibly using convolutional and other modules, and using temporal pooling between levels to coarse-grain the representation and perform longer-term predictions. Training can be performed level-wise or globally, using any non-contrastive method for JEPA. I submit that the ability to represent sequences of world states at several levels of abstraction is essential to intelligent behavior. With multi-level representations of world states and actions, a complex task can be decomposed into successively more detailed subtasks, instantiated into action sequences when informed by local conditions. For example, planning a complex task, like commuting to work, can be decomposed into driving to the train station, catching a train, etc. Driving to the train station can be decomposed into walking out of the house, starting the car, and driving. Getting out of the house requires standing up, walking to the door, opening the door, etc. This decomposition descends all the way down to millisecond by millisecond muscle controls, which can only be instantiated when the relevant environmental conditions are perceived obstacles, traffic lights, moving objects, etc. 4.7. Hierarchical planning. If our world model can perform predictions hierarchically, can it be used to perform mode -2 reasoning and planning hierarchically? Hierarchical planning is a difficult topic with few solutions, most of which require that the intermediate vocabulary of actions be predefined. But if one abides by the deep learning philosophy, those intermediate representations of action plans should also be learned. Figure 16 shows a possible architecture for hierarchical mode 2 planning that can exploit the hierarchical nature of a multi-scale world model. A percept is encoded into representations at multiple levels of abstractions by a cascade of encoders. 0 equal to NC1x, S20 equal to NC2's 14. Prediction takes place at all levels. Higher levels perform longer-term prediction, while lower levels perform shorter-term predictions. The overall task is defined by a high-level objective, depicted as CS24 in the diagram. The top level infers a sequence of high-level actions. 31, CS24. NC2, 0, S20, pred 2s, S2, pred 2s as S24. Cs actor 2, 0, a 0, pred 1s as 1, a 1, pred 1s as 2, a 2, pred 1s as 3, a 3, pred 1s as 4, actor own. Figure 16, hierarchical JEPA for mode 2 hierarchical planning. A complex task is defined by a high-level cost computed from a high-level world state representation CS24. A sequence of high-level abstract actions A22, A24 is inferred that minimizes CS2. The inferred abstract actions are fed to lower-level cost modules CS4, which defines subgoals for the lower layer. The lower layer then infers an action sequence that minimizes the subgoal costs. Although only a two-layer hierarchy is shown here, it is straightforward to extend the concept to multiple levels. The process described here is sequential top-down, but a better approach would be to perform a joint optimization of the actions in all the layers, a 2-2, a 2-4, to optimize this objective. These high-level actions are not real actions but targets for the lower-level predicted states. One can think of them as conditions that the lower-level state must satisfy in order for the high-level predictions to be accurate. Whether these conditions are satisfied can be computed by cost modules CS2 and Cs. They take a lower-level state S2 and a high-level condition A22 and measure to what extent the state satisfies the condition. With these subgoals defined, the lower level can perform inference and find a low-level action sequence that minimizes the mid-level subgoals CS2 and CS4. The process just described is top-down and greedy, but one may advantageously iterate the optimization so that high-level and low-level action sequences are optimized jointly. The cost modules may be configured by the configurator for the situation at hand. The idea that an action is merely a condition to be satisfied by the level below is actually an old one in control theory. For example, a classical proportional server mechanism can be seen as being given a target state. A quadratic cost measures the square distance between the target and the current state, and the control is simply proportional to the negative gradient of the cost with respect to the action variables. 4.8. Handling uncertainty. The real world is not entirely predictable. Uncertainty in predictions of future world states may be due to a number of reasons. The world is intrinsically stochastic aleatoric uncertainty, type 1, 32, CS2, NC20, S20, pred 2s, S22, pred 2s, S24, R2Z22, R2Z24. Advad actor 2, cis 24. Incidence nulla prediedens, as sed prediedens, as stave prediedi, as in action, R1Z10, a 0, R1Z11, a 1, R1 zone 2, a 2, R1 zone 3, a 3, actor own. Figure 17, hierarchical JEPA for mode 2, hierarchical planning in an uncertain environment. Realistic environments are not entirely predictable, even when using highly abstract representations. Uncertainty about predictions can be handled by predictors with latent variables. The latent variables' red circles contain information about the prediction that cannot be derived from the prior observation. The latent variables must be regularized to prevent an energy collapse and to force the system to predict as much as possible without the help of it. At planning time, latent variables are sampled from distributions obtained by applying a Gibbs distribution to the regularizers. Each sample leads to a different prediction. To produce consistent latent sequences, the parameters of the regularizer can be functions of previous states and retrieved memories. As the prediction progresses, the number of generated state trajectories may grow exponentially. If each latent variable has k possible discrete values, the number of possible trajectories will grow as kt, where t is the number of time steps. Directed search and pruning strategies must be employed. With multiple predicted trajectories, optimal action sequences can be computed that minimize the average cost, or a combination of average and variance of the cost so as to minimize risk. The world is deterministic but chaotic, hence difficult to predict without infinity. Precise perception, aleatoric uncertainty, type 2. The world is deterministic but partially observable, aleatoric uncertainty, type 3. The world is fully observable, but the sensors only give partial information about the world state, epistemic uncertainty, type 1. The representation of the world state extracted by the perception module does not contain the full information necessary for accurate prediction. Epistemic uncertainty, type 2. The world model is inaccurate due to limitations of its representational power, bounded. Rationality or epistemic uncertainty, type 3. The world model is inaccurate due to it having been trained with limited amount of data, epistemic uncertainty, type 4. Much of the literature in reinforcement learning is focused on dealing with the stochastic nature of the environment. It is often assumed from the start that models, critics, and policies must represent distributions. In the present work, we push the possible stochasticity of a predicted variable into a latent variable, which may be optimized, predicted, or sampled. This is what is often referred to in the ML literature as the reparameterization trick. We do not need to use this trick here, since we view the latent variable parameterization of the predictions as fundamental. Figure 17 represents a hierarchical planning episode in the presence of uncertainty. A prediction at a given level and time step, for example S22, requires a sample of the corresponding latent variable Z22. The sample may come from the distribution whose negative logarithm is the regularizer R2Z2. The parameters of the regularizer may be constant, for example, fixed, Gaussian, predicted from currently available data using amortized inference, for example, a multinomial or Gaussian, whose parameters are computed from stu0 or produced by the configurator. Using previous predictions to configure the latent regularizer biases the system towards generating good trajectories. As the prediction progresses, the number of generated state trajectories may grow exponentially. If each latent variable has k possible discrete values, the number of possible trajectories will grow as kt, where t is the number of time steps. Directed search and pruning strategies can be employed, as in classical Monte Carlo tree search MCTs. In the case of continuous latents, one may sample latents from the continuous distributions defined by the regularizer. Given a sample of all the latents, the optimal action sequences at every level can be inferred. However, the prediction process may need to be repeated for multiple drawings of the latents, so as to cover the set of plausible outcomes. The inference process may be used for multiple predictions to produce an action that does not just minimize the expected cost, but also minimizes the uncertainty on the expected cost. 4.8.1 World Model Architecture. The details of the architecture of the world model should depend on the type of environment the agent evolves in. It is likely that the best module architectures in a JEPA should include some sort of gating or dynamic routing mechanism. For example, the best way to handle low-level short-term predictions in videos is by extracting simple local feature vectors and displacing those feature vectors from one frame to the next, depending on predicted motions. The latent variables may encode a map of displacements, which can modulate routing connections between one frame and the next. For longer-term prediction at a higher level of abstraction, the relevant features are objects and their interactions. The evolution may be best modeled by a transformer architecture, which has the property of being equivariant to permutation and is appropriate to capture interactions between discrete objects. Vaswani et al. 2007, Carrion et al. 2020, Battaglia et al. 2016. 34. Separating the world model from the ego model, the natural world is complex and somewhat unpredictable, requiring a powerful model with latent variables to account for the unpredictability. On the other hand, the agent itself is somewhat more predictable. A particular action on effector will produce a motion that can often be predicted deterministically. This suggests that the agent should possess a separate model of itself, perhaps without latent variables. Sobel et al. 2022. As the effect of actions on proprioception somewhat easier to predict than the evolution of the external world or the effect of actions on it. In turn, the ego model that the agent has of itself can be used as a template for a model of other agents in a multi-agent scenario. 4.9. Keeping track of the state of the world. Traditionally, modules in deep learning architectures communicate states through vectors or multi-dimensional arrays, but this tends to be a very inefficient method when the state of the object being modeled only changes in minor ways from one time to the next. A typical action of an agent will only modify a small portion of the state of the world. If a bottle is being moved from the kitchen to the dining room, the states of the bottle, the kitchen, and the dining room will be modified, but the rest of the world will be unaffected. This suggests that the state of the world should be maintained in some sort of writable memory. Whenever an event occurs, only the part of the world state memory affected by the event is to be updated, while the rest is to be left unchanged. A conventional key-value associative memory can be used for this purpose, similar to what has been proposed in the context of memory-augmented networks. Borders et al. 2015, Supata et al. 2015, Miller et al. 2016, and entity networks Henaf et al. 2017. The output of the world model at a given time step is a set of query value pairs Qi, which are used to modify existing entries in the world state memory or to add new entries. Given a query Q, the world state memory returns memQ equal to CJVJ, JCJ equal to match KJ, QC equal to normalize C, 15, 16, 17. Where the KJ are keys, the VJ are stored values. Function match Q measures a divergence or dissimilarity between a key and a query. Vector C contains scalar coefficient CJ, and function normalize C performs some sort of competitive normalization or thresholding, such as the commonly used CJ equal to EXP CJ gamma plus XP CK, where gamma is a positive constant. Writing a value R using query or address Q into the memory can be done by updating existing entries. CJ equal to match KJQ, C equal to normalize C, VJ equal to update R VJ CJ. 18, 19, 20. Function update RVC may be as simple as CR plus 1 CV35. If the query is distant from all keys, the memory may allocate a new entry whose key is Q and corresponding value is R. The gamma constant in the example normalized function above may serve as a threshold for acceptable key query divergence. One can view each entry as representing the state of an entity in the world. In the above example of the bottle, the world model may contain keys car bottle, car kitchen, car dining room, respectively representing the bottle, the kitchen, and the dining room. The initial value of V bottle encodes its location as kitchen, the initial value of V kitchen encodes its content as including the bottle, and the initial value of V dining room encodes its content as not including the bottle. After the event, the location and contents are updated. All of these operations can be done in a differentiable manner, and would hence allow to backpropagate gradients through them. 4.10 Data streams. Much knowledge about the world is learnable through pure observation. The laws of motion of physical objects can, in principle, be derived from observation, without a need for intervention. But training a world model efficiently may require more active or agentive information gathering. One can list 5 modes of information gathering, with which an agent can learn about how the world works. 1. Passive observation. The agent is being fed a sensor stream, for example video, audio, etc. 2. Active foveation. The agent is being fed a stream within which the focus of attention can be directed without affecting the environment. For example, watching a scene while being able to orient the vision and sound sensors, or being fed a wide-angle, high-resolution video and/or audio stream within which the focus of attention can be directed. 3. Passive agency. Sensory streams in which another agent acting on the environment is being observed, enabling the inference of causal effects of agent actions on the state of the environment. 4. Active ego motion. The agent receives sensory streams from a real or virtual environment within which the position of the sensors can be modified without significantly affecting the environment. This may include steerable active sensors, for example range sensors, heat sensors, chemical sensors, as well as touch sensors. 5. Active agency. Sensory streams that are influenced by the agent's actions. This enables the establishment of causal models in which the agent can learn to predict the consequences of its actions. This mode brings the exploration-exploitation dilemma to the forefront. In a complex environment, it may not be practical to collect enough passive data for the world model to capture a sufficient portion of the environment's behavior. Mode 2, 4, and 5 allow the agent to collect information that maximizes its understanding of the environment, but to do so may require intrinsic motivation modules that drive attention, curiosity. 36. And exploration into corners of the state space in which the world model's prediction are currently inexact or uncertain. The main open question is how much can be learned using passive observation, modes 1, 2, 4, how much requires ego motion, mode 3, and how much requires full agency, mode 5. 5. Designing and training the actor. The role of the actor module is threefold. 1. Inferring optimal action sequences that minimize the cost, given the predictions produced by the world model for mode 2 actions. 2. Producing multiple configurations of latent variables that represent the portion of the world state the agent does not know. 3. Training policy networks for producing mode 1 actions. There is no conceptual difference between an action and a latent variable. The configurations of both sets of variables must be explored by the actor. For latent variables, configurations must be explored to plan under uncertainty. For action variables, configurations must be explored to produce an optimal one that minimizes the cost. In adversarial scenarios such as games, the latent configurations must be explored that maximize the cost. In effect, the actor plays the role of an optimizer and explorer. When the world model and the cost are well behaved, the actor module can use a gradient-based optimization process to infer an optimal action sequence. To do so, it receives estimates of the gradient of the cost computed by backpropagating gradients through the cost and the unfolded world model. It uses those estimates to update the action sequence. When the world model or the cost are not so well behaved, a gradient-based search for an optimal action sequence may fail. In this case, another search planning method may be applied. If the action space is discrete or can be discretized, one can use dynamic programming methods or approximate dynamic programming methods such as beam search or Monte Carlo tree search. In effect, any planning method developed in the context of optimal control, robotic, or classical AI may be used in this context. Once an optimal action sequence is obtained through the planning, inference, optimization process, one can use the actions as targets to train a policy network. The policy network may subsequently be used to act quickly or merely to initialize the proposed action sequence to a good starting point before the optimization phase. Multiple policy networks can be trained for multiple tasks. The actor also produces configurations of latent variables. These latent variables represent the portion of the world state that the agent does not know. Ideally, the actor would systematically explore likely configurations of the latents. Ideally, the regularizer for the latents, R1 and R2 in figure 17, would represent log priors from which the latent could be sampled. But in a similar way as the policy network, one may devise a latent amortized inference module that learns distributions of latent variables. Good distributions would produce predictions that are plausible. The distribution primates may depend on all the variables available at that time. 37. 6. Designing the configurator. The configurator is the main controller of the agent. It takes input from all other modules and modulates their parameters and connection graphs. The modulation can route signals, activate subnetworks, focus attention, etc. In a scenario in which the predictor and the upper layers of the perception encoder are transformer blocks, the configurator outputs may constitute extra input tokens to these transformer blocks, thereby modulating their connection graphs and functions. The configurator module is necessary for two reasons: hardware reuse and knowledge sharing. There is an obvious advantage to be able to reuse the same circuit for multiple tasks, particularly if the tasks can be accomplished sequentially and if the amount of resources, for example parameter memory, is limited. But there is another advantage: knowledge reuse. A reasonable hypothesis is that a world model trained for a given environment can be used for a range of different tasks with minor changes. One can imagine a generic world model for the environment with a small portion of the parameters being modulated by the configurator for the task at hand. This would be more data efficient and computationally efficient than having separate world models for each skill. The disadvantage is that the agent can only accomplish one task at a time. The configurator may prime the perception module for a particular task by modulating the parameters at various levels. The human perceptual system can be primed for a particular task, such as detecting an item in a cluttered drawer, detecting fruits or praise in a forest, reading, counting certain events, assembling two parts, etc. For tasks that require a rapid detection of simple motifs, the configurator may modulate the weights of low-level layers in a convolutional architecture. For tasks that involve satisfying relationships between objects, such as assembling two parts with screws, the configuration may be performed by modulating tokens in high-level transformer modules. The predictor part of the world model must be able to perform a wide range of functions depending on the task at hand. For predictors performing short-term predictions at a low level of abstraction, configuration may mean dynamic signal routing. In a low-level retinotopic feature array representation, prediction may be reduced to local displacements of individual feature vectors, accompanied with small transformations of those vectors. This may be advantageously implemented with local gating routing circuits. For longer-term prediction at high levels of abstraction, it may be preferable to use a transformer architecture. Transformer blocks are particularly appropriate for object-based reasoning, in which objects interact. The reason is that the function of transformer blocks is equivariant to permutation. Thanks to that property, one does not need to worry about which object is assigned to which input token. The result will be identical and consistent with the input assignment. Recent work in model-based robotics have proposed to use a transformer operating at the level of an entire trajectory, imposing constraints on the attention circuits to configure the predictor for causal prediction or other tasks. Janner et al. 2021. Conveniently, the function of a transformer block is easy to configure by adding extra input tokens. Those extra inputs have the effect of modulating the connection graph used by the rest of the network, thereby allowing the specification of a wide range of input-output functions. 38. Perhaps the most important function of the configurator is to set subgoals for the agent and to configure the cost module for this subgoal. As mentioned in section 302, a simple way to make the cost configurable is by modulating the weights of a linear combination of elementary cost submodules. This may be appropriate for the immutable intrinsic cost submodule. Allowing for a complex modulation of the intrinsic cost may make the basic drives of the agent difficult to control, including cost terms that implement safety guardrails. In contrast, one can imagine more sophisticated architectures, allowing the trainable critic part of the cost to be flexibly modulated. As with the predictor, if the high-level cost is formulated as a set of desired relationships between objects is the nut set on the screw, one may use a transformer architecture trained to measure to what extent the state of the world diverges from the condition to be satisfied. As with the predictor, extra token inputs can be used to modulate the function. One question that is left unanswered is how the configurator can learn to decompose a complex task into a sequence of subgoals that can, individually, be accomplished by the agent. I shall leave this question open for future investigation. 7. Related work. Most of the ideas presented in the paper are not new and have been discussed at length in various forms in cognitive science, neuroscience, optimal control, robotics, AI, and machine learning, particularly in reinforcement learning. Perhaps the main original contributions of the paper reside in an overall cognitive architecture in which all modules are differentiable and many of them are trainable. JEPA, a non-generative, hierarchical architecture for predictive world models that learn representations at multiple levels of abstraction and multiple timescales. A family of non-contrastive self-supervised learning paradigm that produces representations that are simultaneously informative and predictable. A way to use JEPA as the basis of predictive world models for hierarchical planning under uncertainty. Below is an attempt to connect the present proposal with relevant prior work. Given the scope of the proposal, the references cannot possibly be exhaustive. 7.1 Trained world models, model predictive control, hierarchical planning. The use of models in optimal control goes back to the early days with the Kelly-Bryson method. See Bryson and Ho, Rep. or the Review, Marari and Lee, 1997. Some methods allowed for online system identification. Richley et al., 1978. Using neural networks to learn models for control is an old idea, going back to the early 1990s. Jordan and Rumelhart, 1992. Narendra and Parthasarathi, 1990. Miller et al., 1995. 39. In the context of optimal control, learning a mode 1 like policy network is known as direct inverse control. The idea of mode 2 style inference of actions using a predictive model in the context of reinforcement learning is also an old idea, with, for example, Sutton's Diner architecture, Sutton, 1991. See Bertsekas, 2019 for an extensive review. The idea of learnable models has recently enjoyed a renewal of interest in various contexts. Ha and Schmidhuber, 2018 Billions, Ha and Schmidhuber, 2018a, Hafner et al., 2018, Hafner et al., 2020. See Moreland et al., 2020, for a recent survey of model-based reinforcement learning. Learning world models is particularly important in the context of robotics, especially for grasping and manipulation, where sample efficiency is paramount, and simulation is often inaccurate. In fact, because classical reinforcement learning approaches require too many trials for real-world applications, interesting advances in learned model for control have emerged from ML-based robotics research. Agrawal et al., 2016, Finn and Levine, 2017, Chua et al., 2018, Srinivas et al., 2018, Yu et al., 2020, Yaratz et al., 2021. For a recent review, see Levine, 2021, and references therein. A difficult setting is one in which the main input is visual, and a world model must be learned from video. Early attempts to train predictive models without latent variables from simple video produced blurry predictions. Lehrer et al., 2016. To handle uncertainty in the predictions, one can use various flavors of latent variable models, such as generative adversarial networks, Gan Goodfellow et al., 2014, variational autoencoders, Vey Kingma and Welling, 2013, vector quantized Vey VQ Vey van den Oord et al., 2017. Variations of these methods have been applied to video prediction and help represent multimodal outputs and reduce blurriness using Gan Mathieu et al. 2015, Luke et al. 2020, Vey, Babaizadeh et al. 2017, Denton and Fergus 2018, Henaf et al. 2019, or VQ Vey, Walker et al. 2021. Although many of these methods have not been applied to control problems, some have been applied to vehicle trajectory prediction for autonomous driving, Henaf et al. 2019, Mercat et al. 2020, or various robot control tasks, O et al. 2015, Fakidaki et al. 2015, Agrawal et al. 2000. Unlike the proposed JEPA, these models are generative. The key issue of how to represent uncertainty in the prediction remains. The alternative to regularized latent variable models is constructive methods, such as contrastive predictive coding, CPC, Henaf et al. 2019, which has been applied to learning visual representations through video prediction, Van den Ord et al. 2018. To solve the multimodality blurriness problem, other works have proposed to perform video prediction in representation spaces. In some works, the representation space is obtained from a vision pipeline that has been trained in supervised mode, for example to perform semantic segmentation, Luke et al. 2017, Luke et al. 2018. Unfortunately, the requirement for a pre-trained vision pipeline reduces the general usability of these methods for learning world models by observation. In the same spirit as JEPA, there have been proposals for automatically learning representations of video frames so they can be easily predicted. These proposals are generally limited to learning low-level features and often use reconstruction through a decoder as a way to prevent collapse. Goroshin et al. 2015, A. Shrivastava et al. 2015. Some authors have proposed to use temporal invariance or consistency to separate the content of an image region from its instantiation parameters. Wiscott and Sijnowski, 2002, Gregor and Likun, 2010a, Goroshin et al. 2015b. At least one recent work has applied non-contrastive SSL methods to a joint embedding architecture for robotics control with some success. Parry et al. 2021. Contrastive methods applied to joint embedding and prediction have been applied successfully to speech recognition. Bayevsky et al. 2020. C. Mohammed et al. 2022. For a recent review of SSL to speech. To perform state trajectory predictions, recent works have advocated the use of transformers, as proposed in the present paper. Transformers are ideal to represent the dynamics of discrete objects in interaction, and have successfully been applied to the prediction of car trajectories. Mercat et al. 2020. An interesting proposal is the trajectory transformer architecture, in which a transformer is fed with a sequence of predicted states over an entire episode. Jana et al. 2021. The pattern of attention can be constrained so as to force the system to only attend to the past, so it can be operated in a causal manner without looking at the future, and trained to predict the next state actions and costs from previously observed or predicted states, actions, and costs. Hierarchical planning is a largely unsolved problem. Wayne and Abbott proposed an architecture that uses a stack of trained forward models that specify intermediate goals for the lower layers. Wayne and Abbott 2014. Some recent works specify intermediate goals for robots in terms of posed parameters. Gehring et al. 2021. A more recent proposal is the director system, Hafner et al. 2022, which contains a hierarchical world model and planning architecture trained end-to-end through reinforcement learning. The idea of intrinsic motivation to train an agent has been studied in the context of robotics. Gottlieb et al. 2013. The presence of an intrinsic cost provides a differentiable and efficient way to direct the agent to follow certain behaviors and to learn certain skills. 7.2 Energy-based models and joint embedding architectures. For many authors, energy-based model EBM designates a probabilistic model whose distribution is the normalized negative exponential of an energy function. In this paper, EBM designates a much broader category of models that treat the energy function as fundamental and directly manipulate its landscape through learning. Many methods have been proposed in the past that directly manipulate the energy. In fact, all traditional optimization-based learning methods can be interpreted as energy-based methods. Lecon et al. 2006. In particular, discriminative training methods for structure prediction problems can be formulated as EBM. Lecon et al. 1998. Lecon et al. 2006. Most EBM approaches for unsupervised or self-supervised learning have been contrastive. The earliest example is the Boltzmann machine, Hinton and Sednowski, 1983, which is a probabilistic generative energy-based model trained contrastively. Joint embedding architectures, GA, trained with contrastive methods and mutual information maximization methods have a long history. The first non-contrastive GA was Becker and Hinton, 1992, which was based on maximizing a measure of mutual information between the representations from two branches, seeing to different views of the 41, same scene. Perhaps the first contrastive method for GA is the so-called Siamese network, Bromley et al. 1994. This was trained contrastively for the purpose of verifying signatures handwritten on a pen tablet. The idea of GA remained largely untouched for over a decade until it was revived in a series of papers from my group, Chopra et al. 2005, Hatzel et al. 2006, and Jeffrey Hinton's group, Goldberger et al. 2005. Following the rebirth of deep learning, a few papers used GA for fine-grained recognition, including face recognition, Tegman et al. 2014. With the emergence of SSL approaches, the use of GA trained contrastively has exploded in the last few years, with methods such as Peel, Misra, and Martin 2020, Moko, and Moko v2, he et al. 2020, Chen et al. 2020b, and Sinclair, Chen et al. 2020a. Some methods can be seen as distillation approaches, in which one branch of the Siamese network is a teacher, whose output are used as targets for the other branch. This includes methods in which the output vectors are quantized to discrete cluster prototypes, see Karen et al. 2020, and predecessors. In recent years, a number of new non-contrastive methods have appeared, such as BYL Grill et al. 2020. But the class of non-contrastive methods advocated in the present proposal prevent collapse by maximizing the information content of the embeddings. This includes Barlow twins, Zabontar et al. 2021, Vikreg, Bards et al. 2021, whitening-based methods, Ermolov et al. 2021, and maximum coding rate reduction methods, C. Dye et al. 2022, and references therein. Human and animal cognition. The limitations of current approaches to machine learning when compared with human learning are obvious. Lake et al. A. Zadnordyk et al. Young children quickly learn abstract concepts, Murphy, 2002, and models that allow them to navigate, to form goals, and to plan complex action sequences, to fulfill them. Gopnik and Meltzoff, 1997, Spelke and Kinsler, Das New Serekari, Das New Neue Gopnik et al., Das New An. In cognitive science, the idea that the brain builds predictive world models is a common one, and have inspired attempt to reproduce the process in machines, Lake et al., 2017b, Orhan et al., 2020. Some efforts have been devoted to building video datasets to test intuitive physics common sense in machines and infants, Ryoshe et al., 2019. The ability to plan is a well-studied feature of human intelligence, Matar and Lengyel, 2022. There is evidence that people construct simplified representations of the world for planning, in which irrelevant details are abstracted away, Ho et al., 2022. Consciousness is a rather speculative topic, owing to the difficulty of defining what consciousness is. I will not speculate about whether some version of the proposed architecture could possess a property assimilable to consciousness, but will only mention the work of Dehaene and collaborators, who have proposed two types of consciousness that they call C1 and C2. C1 is largely related with the modulation of attention, while C2 requires a self-monitoring ability, perhaps assimilable to what the configurator module needs to do in the present proposal, Dehaene et al., 2021. 42. 8. Discussion, limitations, broader relevance. Constructing the cognitive architecture of the present proposal, instantiating all the details, and making the system work for non-trivial tasks will not be an easy task. The path to success is likely riddled with unforeseen obstacles. It will probably take many years to work them all out. 8.1. What is missing from the proposed model? A lot of hard work needs to be done to instantiate the proposed architecture and turn it into a functional system. There may be flaws and pitfalls that may appear to be unsolvable within the specifications of the proposed architecture. The first question is whether a hierarchical JEPA can be built and trained from videos. Could it learn the type of abstract concept hierarchy mentioned in section 4.1? One somewhat open question relative to the JEPA is how precisely to regularize the latent variable so as to minimize its information content. A number of possible mechanisms are proposed, making the latent variable discrete, low-dimensional, sparse, or stochastic. But it is not clear which approach will ultimately be the best. The current proposal does not prescribe a particular way for the actor to infer latent variable instantiations and optimal action sequences. While the differentiability of all the modules makes it possible in principle to use gradient-based optimization to infer optimal action sequences, the optimization problem may be very difficult in practice. In particular, when the action space is discrete, or when the function from actions to cost is highly non-smooth, gradient-based method may be ineffective, requiring to use other gradient-free search methods, dynamic programming, belief propagation, MCTs, SAT, etc. Instantiating multiple configurations of latent variables in Mode 2 planning, reasoning may require additional mechanisms not described in the present proposal. Humans seem to be endowed with an ability to spontaneously cycle through alternative interpretations of a percept, as demonstrated by the Necker cube and other visual illusions that have several equally plausible interpretations. In the context of the present model, different interpretation of an ambiguous percept may be represented by different values of a latent variable. While one could imagine a number of exploratory mechanisms to systematically explore the space of possible latent variable values, no such mechanism is described here. The present proposal does not specify the details of the architecture of the various modules. For example, it is probable that the predictor will require some sort of dynamic routing and gating circuits in its microarchitecture. Predictors for low-level representation may have to be specialized to represent the kind of small transformations of the representation that can occur in the short term. Predictor modules dealing with higher-level representations may require more generic architectures that manipulate objects and their relationships, but none of this is specified in the present proposal. Similarly, the precise architecture and function of the short-term memory and how it may be used to represent beliefs about the state of the world are somewhat fuzzy. The original memory network system and its successors contained the idea that a neural net could use an associative memory as a working memory to store and retrieve beliefs about the state of the world between compute cycles. Bordes et al. 2015, Sukbata et al. 43, 2015. But getting such an architecture to work for complex planning and control may prove difficult. Of all the least understood aspects of the current proposal, the configurator module is the most mysterious. In particular, while planning a complex task, the configurator is supposed to identify sequences of subgoals and configure the agent to successively accomplish those subgoals. Precisely how to do that is not specified. This is merely a list of foreseeable questions, but many questions and problems will inevitably surface as instances of the proposed systems are put together. 8.2. Broader relevance of the proposed approach. Although the proposed architecture is not specifically designed to model autonomous intelligence, reasoning and learning in humans and other animals, one can draw some parallels. The following is somewhat speculative and provided as a way to connect some concepts in cognitive science and neuroscience that have inspired the present work. 8.2.1. Could this architecture be the basis of a model of animal intelligence? Many of the modules in the proposed architecture have counterparts in the mammalian brain that perform similar functions. The perception module corresponds to the visual, auditory, and other sensory areas of the cortex, as well as some of the association areas. The world model and the critic correspond to various parts of the prefrontal cortex. The intrinsic cost module corresponds to structures in the basal ganglia involved in rewards, including the amygdala. The trainable critic may correspond to part of the prefrontal cortex involved in reward prediction. The function of the short-term memory overlaps with what is known of the hippocampus. The configurator may correspond to structures in the prefrontal cortex that perform executive control and modulate attention. The actor regroups areas in the premotor cortex that elaborate and encode motor plans. The idea of predictive world model has long been a prominent concept in cognitive science, and the idea of predictive coding has been a prominent concept in neuroscience. The JEPA architecture and the corresponding non-sample contrastive self-supervised learning method are somewhat consistent with ideas of predictive coding and efficient coding. The proposed architecture has a single world model engine that can be configured for the task at hand by the configurator. I have argued that this may not only confer a computational advantage through hardware reuse, but also allow knowledge to be shared across multiple tasks. The hypothesis of a single configurable world model engine in the human brain may explain why humans can essentially perform a single conscious reasoning and planning task at a time. A highly speculative idea is that the illusion of consciousness may be a side effect of a configurator-like module in the brain that oversees the function of the rest of the brain and configures it for the task at hand. Perhaps if the brain were large enough to contain many independent, non-configurable world models, a configurator would be unnecessary, and the illusion of consciousness would disappear. What is the substrate of emotions in animals and humans? Instantaneous emotions, for example, pain, pleasure, hunger, etc., may be the result of brain structures that play a role similar to the intrinsic cost module in the proposed architecture. Other emotions, such as fear, or 44. Elation may be the result of anticipation of outcome by brain structures whose function is similar to the trainable critic. The presence of a cost module that drives the behavior of the agent by searching for optimal actions suggests that autonomous intelligent agents of the type proposed here will inevitably possess the equivalent of emotions. In an analogous way to animal and humans, machine emotions will be the product of an intrinsic cost, or the anticipation of outcomes from a trainable critic. Could this be a path towards machine common sense? It is a widely held opinion that none of the current AI systems possess any level of common sense, even at the level that can be observed in a house cat. Animals seem to be able to acquire enough background knowledge about how the world works to exhibit some level of common sense. By contrast, AI systems, even when pre-trained with self-supervised mode, for example from text, seem to exhibit very limited levels of common sense, making them somewhat brittle. For example, large language models (LLMs) seem to possess a surprisingly large amount of background knowledge extracted from written text, but much of human common sense knowledge is not represented in any text and results from our interaction with the physical world. Because LLMs have no direct experience with an underlying reality, the type of common sense knowledge they exhibit is very shallow and can be disconnected from reality. A possible characterization of common sense is the ability to use models of the world to fill in blanks, for example predicting the future, or more generally, filling in information about the world that is unavailable from perception or from memory. With this definition, common sense is an ability that emerges from a collection of models of the world, or from a single model engine configurable to handle the situation at hand. This view of common sense sits squarely in the camp of grounded intelligence. Common sense is a collection of models from low levels of abstraction to high levels, all the way up to knowledge acquired through language. Could SSL applied to configurable HJEPA constitute the substrate of machine common sense? Could a properly trained and configured HJEPA embed enough predictive knowledge and capture enough dependencies about the world to exhibit some level of common sense? I speculate that common sense may emerge from learning world models that capture the self-consistency and mutual dependencies of observations in the world, allowing an agent to fill in missing information and detect violations of its world model. 8.3. Is it all about scaling? Is reward really enough? The section reviews a few potential paths towards human-level intelligence that have been proposed in recent years. The surprising power of large transformer architectures trained to predict text and other modalities have led some to claim that we merely need to scale up those models. Brown et al. 2020. Brown et al. 2020. The surprising power of reinforcement learning for games and other simple environments have led others to claim that reward is enough. Silver et al. 2021. Finally, the limitations of current deep learning systems when it 45 comes to reasoning have led some to claim that deep learning systems need to be augmented by hardwired circuitry to enable symbol manipulation. Marcus and Davis, 2019. 8.3.1. Scaling is not enough. Large language models (LLMs) and more generally, large-scale transformer architectures trained with a form of generative self-supervised learning have been astonishingly successful at capturing knowledge present in text. This has led to a debate in the AI community as to whether human-level AI can be attained by scaling up these architectures. My position in this debate is that I do not believe that scaling is enough for two main reasons. First, current models operate on tokenized data and are generative. Every input modality must be turned into a sequence or a collection of tokens encoded as vectors. While this works well for text, which is already a sequence of discrete tokens, it is less suitable for continuous high-dimensional signals such as video. The type of SSL training used for LLM-style models can be seen as a particular kind of latent-free generative model trained with a particular kind of contrastive method called denoising autoencoder Vincent et al. 2010, or in this case, masked autoencoder Devlin et al. 2018. Hence, they are subject to the limitations of generative models, latent variable free models, and contrastive methods. Generative models have difficulty representing complex uncertainties in continuous spaces. LLMs simplify the representation of uncertainty in the prediction by only dealing with discrete objects from a finite collection, for example words from a dictionary. Representing uncertainty about a word being predicted comes down to producing a vector whose components are scores or probabilities for each word or discrete token in the dictionary. But this approach doesn't work for high-dimensional continuous modalities such as video. To represent such data, it is necessary to eliminate irrelevant information about the variable to be modeled through an encoder, as in the JEPA. Furthermore, the high dimensionality of the signal precludes the representation of uncertainty through a normalized distribution. Second, current models are only capable of very limited forms of reasoning. The absence of abstract latent variables in these models precludes the exploration of multiple interpretations of a percept and the search for optimal courses of action to achieve a goal. In fact, dynamically specifying a goal in such models is essentially impossible. 8.3.2 Reward is not enough. The proposed architecture is designed to minimize the number of actions a system needs to take in the real world to learn a task. It does so by learning a world model that captures as much knowledge about the world as possible without taking actions in the world. It uses intrinsic costs that are differentiable functions of measured or predicted world states. This makes the proposal more similar to optimal control than to reinforcement learning. In the proposed model, much of learning takes place at the level of the world model perceptual encoder and predictor. In this context, what is the role of reinforcement learning RL? In most RL settings, the reward, or the cost, which is a negative reward, is fed to the agent by the environment. In other words, intrinsic cost module is the environment itself, and is therefore an unknown function. The value of the function can be probed by observing the state of the world, taking an action, and observing the resulting reward. The gradient of the reward with respect to the action or the state is unknown and must be estimated by 46. Multiple action trials, as in policy gradient methods. In actor-critic methods, the reward function is approximated by a critic module that is trained to approximate expected future values of the reward. The critic provides a differentiable approximation of the reward function. But model-free RL is extremely sample inefficient, at least when compared with human and animal learning, requiring very large numbers of trials to learn a skill. Scalar rewards provide low information feedback to a learning system. As a consequence, a pure RL system requires a very large number of trials to learn even relatively simple tasks. Model-based RL clearly has the potential of being considerably more sample efficient, but the question becomes how to train the world model. Is it trained from taking actions and getting rewards, or is it trained by predicting the world state? In the latter case, reward is clearly not enough. Most of the parameters in the systems are trained to predict large amounts of observations in the world. Contrary to the title of a recent position paper by Silver et al., 2021, the reward plays a relatively minor role in this scenario. 8.3.3. Do we need symbols for reasoning? In the proposed architecture, reasoning comes down to energy minimization or constraint satisfaction by the actor using various search methods to find a suitable combination of actions and latent variables, as stated in section 3.1.4. If the actions and latent variables are continuous, and if the predictor and the cost modules are differentiable and relatively well behaved, one can use gradient-based methods to perform the search. But there may be situations where the predictor output changes quickly as a function of the action, and where the action space is essentially discontinuous. This is likely to occur at high levels of abstractions, where choices are more likely to be qualitative. A high-level decision for a self-driving car may correspond to turning left or right at the fork, while the low-level version would be a sequence of wheel angles. If the action space is discrete with low cardinality, the actor may use exhaustive search methods. If the action set cardinality and hence the branching factor are too large, the actor may have to resort to heuristic search methods, including Monte Carlo tree search or other gradient-free methods. If the cost functions satisfy Bellman's equations, one may use dynamic programming. But the efficiency advantage of gradient-based search methods over gradient-free search methods motivates us to find ways for the world model training procedure to find hierarchical representations with which the planning reasoning problem constitutes a continuous relaxation of an otherwise discrete problem. A remaining question is whether the type of reasoning proposed here can encompass all forms of reasoning that humans and animals are capable of. Acknowledgements. Ideas in this paper are a distillation of years of interactions with many people. It is impossible to list them all here. I will list some of the more salient ones: Elion Botu, Joshua Bengio, Jeffrey Hinton, Rob Fergus, and Jitendra Malik, Emmanuel Dupu, and Stanislas Towards Data and Knowledge-Driven AI, a survey on neurosymbolic computing. Wang Wang, Senior Member, IEEE, Yi Yang, Senior Member, IEEE, and Fei Wu, Senior Member, IEEE. October 3rd, 2024. CSAI, ArXiv 2000-2158889v5. Abstract, Neural Symbolic Computing (NESI), which pursues the integration of the symbolic and statistical paradigms of cognition, has been an active research area of artificial intelligence (AI) for many years. As NESI shows promise of reconciling the advantages of reasoning and interpretability of symbolic representation and robust learning in neural networks, it may serve as a catalyst for the next generation of AI. In the present paper, we provide a systematic overview of the recent developments and important contributions of NESI research. Firstly, we introduce study history of this area, covering early work and foundations. We further discuss background concepts and identify key driving factors behind the development of NESI. Afterward, we categorize recent landmark approaches along several main characteristics that underline this research paradigm, including neural symbolic integration, knowledge representation, knowledge embedding, and functionality. Next, we briefly discuss the successful application of modern NESI approaches in several domains. Then, we benchmark several NESI methods on 3 representative application tasks. Finally, we identify the open problems together with potential future research directions. This survey is expected to help new researchers enter this rapidly evolving field and accelerate the progress towards data and knowledge-driven AI. Index terms: neurosymbolic AI, symbolic AI, statistical AI, deep learning. 1 introduction. Current, CLE large, advances, AI models in artificial, have caused intelligence significant. AI changes in numerous research fields and have profound impacts on every aspect of societal and industrial sectors. At the same time, there is also growing concern in the public and scientific communities regarding the trustworthiness, safety, interpretability, and accountability of the modern AI techniques. 1. This leads to a natural question: what could be the key enabler for the next generation of AI? AI has historically been dominated by 2 paradigms: symbolism and connectionism. Symbolism conjectures that symbols representing things in the world are the fundamental units of human intelligence, and that the cognitive process can be accomplished by the manipulation of the symbols through a series of rules and logic operations upon the symbolic representations. 2. 3. Many early AI systems, from the mid-1950s to the late 1980s, were built upon symbolistic models. Symbolic methods have several virtues. They require only a few input samples, use powerful declarative languages for knowledge representation, and have conceptually clear internal functionality. It soon became apparent, however, that such a rule-based top-down strategy demands substantial hand-tuning and lacks true learning. Moreover, as discrete symbolic representations and handcrafted rules are intolerant of ambiguous and noisy data, symbolic methods typically fall short when solving real-world problems. Connectionism, represented by its most successful technique, deep neural networks (DNNs) serves as the architecture behind the majority of recent successful AI systems. Inspired by the physiology of the nervous system, connectionism explains cognition by interconnected networks of simple and often uniform units. Learning happens as weight modification. In a data-driven manner, the network weights are adjusted in a direction that minimizes the cumulative error from all the training samples, using techniques such as gradient backpropagation. 5. Connectionist models are fault-tolerant, since they learn sub-symbolics, i.e., continuous embedding vectors, and compare these vectorized representations instead of the literal meaning between entities and relations by discrete symbolic representations. Moreover, by learning statistical patterns from data, connectionist models enjoy the advantages of inductive learning and generalization capabilities. Yet, like every coin has 2 sides, such approaches also suffer from several fundamental problems. 6. 7. First, connectionist models fall significantly short of compositional generalization, the robust ability of human cognition to correctly solve any problem that is composed of familiar parts. 8. Second, such bottom-up approaches are known to be data inefficient. Third, connectionist models are logically opaque, lacking comprehensibility. It is almost impossible to understand why decisions are made. In the absence of any kind of identifiable or verifiable train of logic, people are left with systems that make potentially catastrophic decisions that are difficult to understand, arduous to correct, and therefore hard to trust. These shortcomings hinder the adoption of connectionist systems in decision-critical applications and reasoning-heavy tasks such as medical diagnosis, autonomous driving, and mathematical reasoning, and lead to the increasing concern about contemporary AI techniques. Against this background, neural symbolic computing, pioneered by combining logic and neural networks. 9. And then officially introduced by the Neural Symbolic Learning and Reasoning (NESI) Association as a hybrid of symbolism. W. Wang, Yang, and F. Wu are with College of Computer Science and Technology, Zhejiang University. Email: wenwanwang.ai@gmail.com, yanggeeks@zju.edu.cn, wufei@cs.zju.edu.cn. Corresponding author: Wen Wang. IEEE Transactions on Pattern Analysis and Machine Intelligence 2. Data and Knowledge-Driven AI. Neurosymbolic Computing. NESI. Conclusion. Introduction. Section 8. Section 1. Challenges. History. Section 2. Human Cognition. Biologic Neural Network. Versus Symbolic Logic Machinery. NESI. Best of both worlds. On next generation of AI 10. Have demonstrated its superiority in many application scenarios. NESI. And connectionism is widely recognized as an enabler of the. A summary of the structure of this article can be found next generation of AI 10 11. NESI essentially looks for in Figure 1, which is presented as follows. SEC 2 gives the integration of 2 fundamental cognitive abilities. 12. Brief review of early research results of NESI, which shape 13. Learning, the ability to learn from experience.
One, two, 1, 2. 1, 2. Okay. Still recording. Yeah, this AI speechify thing is messing up for this block of text. Plus, I'm getting a little tired of hearing this British dude talking to me. So I'm going to just read off part of this, and hopefully it'll pick back up later on a different page. Connectionism is widely recognized. Oh, let me start from above, from the top of the sentence. So, against this background, neurosymbolic computing, pioneered by combining logic and neural networks, and then officially introduced by the Neurosymbolic Learning and Reasoning (NESI) Association as a hybrid of symbolism and connectionism, is widely recognized as an enabler of the next generation of AI. NESI essentially looks for the integration of 2 fundamental cognitive abilities: learning, the ability to learn from experience, and reasoning, the ability to reason from what has been learned, so as to exploit the major strengths and circumvent the inherent deficiencies of the 2 paradigms. However, building such an integrated machinery is challenging. One has to conciliate the methodologies of distinct areas. For example, statistical inductive learning based on distributed representations. I'm not sure what that word is. Logical deductive reasoning based on localist representations. Though challenging, Nessie has attracted soaring research attention in the recent past and has demonstrated its superiority in many application scenarios, including visual relationship understanding, visual question answering, visual scene parsing, and common sense reasoning. In order to facilitate readers to catch up on the rapidly developing evolution of this field, alright, I'm going to skip this part because it's pretty much backstory, right? I don't need to know the history. That's fine. Background and context. Let's check if the AI works for here.
Background and context emphasizes high-level reasoning and sticks to structure. This section elucidates the two main driving forces behind world in terms of objects.
It still doesn't. Alright. Background and context. This section elucidates the two main driving forces behind the field of Nessie. So, you know what? If this whole paper is going to just be like this, is it all going to be like this? No, it looks like it gets a little bit better, at least on this page. Okay. Let's just read this page then. So the background and context, This section elucidates the two main driving forces behind the field of Nessie. The first one is the theoretical aspiration to understand and model human cognition, while the second one is the practical value of combining connectionism and symbolism paradigms in AI application scenario. Section 3.3 further summarizes the recent AI debate among influential thinkers, which motivates a broad range of AI researchers to recognize the significance of Nessie. 3.1 Human cognition, biologic neural network versus symbolic logic machinery. Symbols versus neurons. What is the essence of human cognition? Many researchers agree that symbolic facility is what distinguishes humans from other animals. The prosperity of human sociology and technology is closely concerned with the coevolution of human brain with symbolic thinking, making us the symbolic species. Many cognitive scientists hold the view that human thinking relies on symbol manipulation. From this perspective, human mind is undisputedly symbolic. Therefore, symbolism was conceived in the attempts to structurally code knowledge and logic reasoning into machines. However, human cognition has a physical basis in the brain, which is composed of numerous, mostly homogeneous neurons. The neurons, together with the connections or synapses, as well as diverse firing patterns among them, support different cognitive processes such as attention, problem solving, memory, learning, decision-making, language, perception, imagination, and logic reasoning. So it seems reasonable to assume if we can simulate the anatomy and physiology of the nervous system with artificial neurons, intelligence will be developed in computers. This belief leads to the emergence of connectionism. Spontaneously, in order to advance the understanding of the human mind, it appears to be reasonable to seek ways of integration of symbolic and connectionist approaches instead of focusing on the dichotomy. In this context, artificial neural networks can be regarded as an abstraction of the physical workings of the brain, while the symbolic logic can be viewed as an abstraction of what we introspect when we engage in explicit cognitive reasoning. Therefore, it is of necessity to ask how these two abstractions can be related or even unified, or how symbol manipulation can emerge from a neural substrate. Deduction versus induction. Deductive reasoning and inductive learning arguably constitute two indispensable building blocks of human thinking, helping humans to develop knowledge of the world, even though there are yet other building blocks such as abductive reasoning. However, their tension might be the most fundamental issue in areas such as philosophy, cognition, and of course AI. The deduction camp is aware of the expressiveness of formal languages for representing knowledge about the world, along with proof systems for reasoning from such knowledge bases. The learning camp attempts to generalize from examples about partial descriptions of the world. Historically, the dichotomy between the two camps roughly divided the development of AI. Symbolic techniques clearly stand on the side of deductive reasoning. Symbolic logic emphasizes high-level reasoning and sticks to structure the world in terms of objects, attributes, and relations. By contrast, neural networks are in the statistical learning camp. They learn statistical patterns, i.e. distributed representations of entities from data. Nevertheless, humans make extensive use of both deduction and induction in everyday life as well as scientific investigation. We cannot precisely determine which part of human cognition is essentially symbolic and which part is essentially statistical. Consequently, It is imperative to rethink the relationships between deductive reasoning and inductive learning, necessitating robust computational models that are able to coordinate the symbolic essence of reasoning with the statistical nature of learning. Compositionality versus continuity. Smolensky et al. Proposed to simultaneously exploit two scientific principles, which can explain the way the human brain works, for machine intelligence, from the viewpoint of the underlying computation mode of human cognition. Neurophysiological measurements suggest that information is encoded in the brain through the numerical activation levels of massive neurons and is processed by spreading this activation through myriad synapses of varying strengths and permanence. Hence, it seems evident that human cognition deploys neural computing, which conforms to the continuity principle. The encoding and processing of information are formalized with real numbers that vary continuously. However, modern scientific studies in philosophy and cognition suggested that all aspects of human intelligence, from language and perception to reasoning and planning, rely on a different type of computing, compositional structure processing. This type of computing follows the compositionality principle. Complex information is encoded in large structures, which are systematically composed from smaller structures that encode simpler information. Compositionality is widely acknowledged as a core of human intelligence. Our knowledge representation is naturally compositional. For example, we understand the world as a sum of its parts. Objects can be broken down into pieces, events are sequences of actions, and sentences are a series of words. Human cognition exhibits strong compositional generalization, the ability of reorganizing familiar knowledge components in novel ways to solve new problems, so as to handle the potentially infinite number of states of the world. Historically, compositional structure processing is formalized in the form of discrete symbolic computing, like using words to make sentences. Thus, to some extent, the nature of computation in our brains is both neural and compositional structure. How can this be? Smolensky called this the central paradox of cognition. Resolving this paradox inevitably calls for a new computing mechanism that addresses both the continuity and compositionality principles simultaneously. Let's see if we can let AI Speechify take back over now.
System 1 versus System 2. Kahneman's fast and slow thinking theory, which explains the machinery of human thought, also motivated recent research interest in NESI 56. In 57, Kahneman argued that human decisions are supported by the cooperation of two different kinds of capabilities, called System 1, fast thinking, and System 2, slow thinking. Specifically, System 1 thinking is a near instantaneous and experience-driven process for intuitive, imprecise, quick, and largely unconscious decisions, accounting for 98% of thinking. System 1 thinking, for example, can be in the form of knowing how to zip your jacket without a second thought. Differently, System 2 thinking is slower, deliberative, and conscious, often associated with the subjective experience of agency, choice, and concentration. It provides a powerful tool for solving more complicated problems, where logical, sequential, algorithmic thinking is needed. For example, System 2 thinking is used when working on math problems. It is also worth mentioning that compositional generalization is exhibited in both System 1 thinking and System 2 thinking 7. Interestingly, System 2 can be viewed as a slave of System 1. When System 1 runs into difficulty, it is System 1 that decides to initiate System 2. Even during the execution of System 2, System 1 is ultimately in charge. 58. In addition, solutions discovered by System 2 can be readily available for later use by System 1. Thus, after a while, some problems, initially solvable only by resorting to System 2, can become manageable by System 1 56. The consistent and effective use of System 2 can calibrate System 1, which in turn promotes System 2, leading to a feedback loop. As the characteristics of System 1 and System 2 are strikingly similar to those of the connectionist approach and the symbolic approach to AI, more and more AI researchers began to rethink the relation between the two traditions and recognize the value of NESI. 3.2. NESI, best of both worlds. Rather than taking the motivation from the objective of achieving rational understanding and modeling of human, 1. Note that the solution, neurocompositional computing proposed by Smolensky et al. 7, is slightly different from NESI. Cognition, the study of NESI, is also driven by a more technically motivated perspective, combining numerical connectionist and symbolic logic approaches in order to construct more powerful reasoning and learning machines for computer science applications. The second motivation is based on the observation that connectionist techniques, especially modern DNNs, and symbolic approaches, complement each other with respect to their strengths and weaknesses. In particular, connectionist techniques are good at discovering statistic patterns from raw data and are robust against noisy data. Hence, they are effective in intuitive judgments, such as image classification. On the other hand, connectionist techniques are data hungry and black boxes. It is especially challenging to understand their decision-making processes. Alternatively, symbolic approaches are excellent at principal judgments, such as logical reasoning. They exhibit inherently high explainability and provide the ease of using powerful declarative languages for knowledge representation. Nevertheless, symbolic approaches are far less trainable and susceptible to out-of-domain brittleness. As a result, the integration of neural and symbolic approaches seems to be a natural step toward more powerful, trustworthy, and robust AI. 3.3 Current debate on AI. Recent years have witnessed remarkable breakthroughs in AI, brought by connectionist approaches and deep learning in particular. But researchers are also coming to realize that contemporary AI systems suffer from serious deficiencies in terms of, for example, data efficiency, comprehensibility, and compositional generalization. 68. This led to influential debates between famous researchers, which are about the underlying principles of AI. As a result, NESI research gained renewed importance. Specifically, the 2019 Montreal AI debate between Joshua Bengio and Gary Marcus 45, and the Jet AI 2025 side conversation with economics Nobel laureate Daniel Kahneman, and the 2018 Turing Award winners and deep learning pioneers Jeff Hinton, Joshua Bengio, and Jan LeCun brought new perspectives and concerns on the future of AI. In the debate between Joshua Bengio and Gary Marcus, Marcus emphasizes the importance of hybrid systems. In order to get to robust artificial intelligence, we need to develop a framework for building systems that can routinely acquire, represent, and manipulate abstract knowledge, with a focus on building systems that use that knowledge in the service of building, updating, and reasoning over complex internal models of the external world. Though Hinton agreed that we need those high-level concepts to be grounded and have distributed representation to achieve generalization, he also addressed that numerical connectionist approaches can get many of the attributes of symbols without the kind of explicit representations of them, which has been the hallmark of classical AI, and that the reason why connectionists really wanted to depart from symbolic processing is because they thought that it wasn't a sufficiently rich kind of representation. At Drake AI 2020, Kahneman highlighted the importance of symbol manipulation in System 2. As far as I'm concerned, System 1 certainly knows language. System 2 does involve certain manipulation of symbols. Although there are disagreements about, for example, how to represent symbols in DNNs and IEEE transactions on pattern analysis and machine intelligence 5. Table 1. Summary of essential characteristics for reviewed NESI methods I. Please note type 1 is presented here to show the input and output of a neural network can be made of symbols, albeit it may not qualify as NESI from a rigorous perspective. Neurosymbolic integration. How to achieve the hybrid of connectionism and symbolism. The thinkers, in broad strokes, are in agreement that new generation AI systems ought to be able to handle high-level abstract concepts and to conduct sound reasoning. 4. NESI, taxonomy, and state of the ART. As already alluded to in the introduction, this section is devoted to a structured and comprehensive review of state-of-the-art NESI algorithms. SEC 4.1 details our taxonomy for NESI, based on which we survey recent major research results in this area from 4 perspectives: neurosymbolic integration, knowledge representation, knowledge embedding, and functionality. 4.1 Our taxonomy for NESI. Our overall taxonomy for NESI AI is mainly built upon the classification scheme proposed by Sebastian and Hitzler in 2005-28, but modified according to our specific focus and recent development in this field. Basically, our scheme has 4 main dimensions, namely neurosymbolic integration, knowledge representation, knowledge embedding, and functionality. Each dimension contains elements representing the notable properties of NESI approaches. The first dimension, neurosymbolic integration, categorizes NESI systems according to the combination mode, how the symbolic and neural parts are integrated as a hybrid. Along this dimension, we further adopt the classification schema recently introduced by Henry Kautz at JAAI 2020-58, which is influential and insightful. More details of this dimension will be given in SEC 4.2. For the second dimension, knowledge representation, we focus on the symbolic aspect of the NESI AI system. Depending on how the knowledge is represented, i.e. symbolic versus logic, we can distinguish the systems as discussed in SEC 4.3. The third dimension, knowledge embedding, considers which component of the neural machine the symbolic knowledge is integrated into. We find that the integration can be made at every key part of the connectionist pipeline, namely data preprocessing, network training, network architecture, as well as final inference. Based on this insight, in SEC 4.4, we make the categorization along this dimension. The fourth dimension refers to the functionality of the NESI system, namely whether it focuses more on machine learning or automated symbolic reasoning. More detailed discussions can be found in SEC 4.5, learning and reasoning, reasoning functionality, SEC 4.5, learning, NESI type 1, symbolic neurosymbolic type 2, symbolic neuro type 3, neuro or symbolic type 4, neuro, symbolic neuro type 5, neurosymbolic type 6. By first order logic, the programming language may not be able to express. Figure 2, our 4-dimensional taxonomy for NESI. The dimensions are independent and not mutually exclusive, as explained in SEC 4.1. Note that the axes indicate the order in which each section is structured, not the sequence of their evolution. For example, things can be represented by first order logic, the programming language may not be able to express, and vice versa. Note that the 4 dimensions are proposed to comprehensively describe the key characteristics of an NESI system. They are independent and non-exclusive. Along with these 4 dimensions of our taxonomy, we summarize the key features of recent remarkable works in this field in Table 1 and give detailed review below. 4.2 Neural symbolic integration. With a good understanding of the reasons behind the need for integrating symbolic and connectionist approaches, it should turn next to the integration mode. Following the rationale laid out in 58, we distinguish 6 types of NESI AI systems. Neural network, symbols, vectorization, discretization symbols, Fig. 3. Type 1. Symbolic neuro. Symbolic, also referred to as neural networks with symbolic input-output, symbolic model. Type 1. Symbolic neurosymbolic. Also referred to as neural networks with symbolic input-output. Figure 3. This is, in neural Kautz network words, the current standard operating neural network procedure of deep learning methods. In some application tasks where the input and output are symbols, dot current symbolic model for. Example. Most. Knowledge embedding. SEC 4.4. Neural inference. NLP systems, including large language models like GPT-361, fall under this category. See Table 1. The input symbols are converted to vector embeddings by WORD2, VEC 59 plus 60, etc., and then processed by the neural models, whose output embeddings are further converted to the required symbolic category or sequence of symbols via a softmax operation. This type is included by Kautz to emphasize that the input and output of a neural network can be made of symbols 93, e.g., in the case of language translation, or graph classification. Neural network nowadays, some may. Symbols. Vectorization, discretization symbols. Argue that this type is a stretch to refer to as NESI since it may encompass almost any deep learning model where the input and output spaces have clear human interpretable semantics, e.g., tabular classification. Symbolic model. Figure 5. Type 3. Neuro or symbolic, also referred to as neural learning plus symbolic solver. Abstract concept. Type 2. Symbolic neuro, also referred to as neuro, the individual and collective performance. Therefore, the resubroutines. Figure 4. Type 2 refers to hybrid but overall simulation between neural networks.
One, two. Okay. Sorry. Is it worth reading all this? Yes. It's a little redundant because they covered these concepts in one of the earlier papers, but the goal of going through all these is to ingrain these ideas in my brain. So it's fine. I'll read it. We already talked about symbolic, neurosymbolic, ChatGPT. You have text, become vectors, become text. So type 2, symbolic neuro, also referred to as neuro subroutines. Type 2 refers to hybrid but overall symbolic systems, where neural modules, sorry, 1 second. Can I hear myself? I can't hear oh, I can, okay. Type 2 refers to hybrid but overall symbolic systems, where neural modules are internally used as subroutines within a symbolic problem solver. In a nutshell, the symbolic and neural parts are only loosely coupled. Kautz includes DeepMind's AlphaGo as an example. The problem solver is the Monte Carlo tree search algorithm, and its heuristic evaluation function is a neural network. In a NESI model is designed, in 63, which is a reference to a paper, a NESI model is designed to learn and generalize compositional rules. Based on a sequence-to-sequence generation network, a symbolic stack machine is adopted for supporting recursion and sequence manipulation, and the execution trace is produced by a neural network. In 64, a rule-based system, which uses abstract concepts captured by a neural perception module as input-output specifications, is introduced for program synthesis from raw visual observations. Another example is recent large language model LLM-based AI agents, e.g. VizProg, Hugging GPT, and Viper GPT, which leverage LLMs to decompose a complex task into a sequence of subtasks that can be solved using off-the-shelf AI models. So I think something like the React framework would probably fall under this, right? It's a hybrid but overall symbolic system where neural modules are internally used as subroutines within a symbolic problem solver. Yeah, so I think React falls into this category. Type 3, neurosymbolic. Or is it neuro-given symbolic or neuro-pipe symbolic, neuro-or symbolic? I don't know. I see. Also referred to as neural learning plus symbolic solver. Type 3 is also a hybrid system where the neural and symbolic parts focus on different but complementary tasks in a big pipeline. Kautz mentioned Type 3 and Type 2 differ in that the neuro part is a coroutine rather than a subroutine. To eliminate ambiguity here, we further restrict Type 3 as the hybrid systems where the interaction between neural and symbolic parts can boost both the individual and collective performance. Therefore, the relation between neural and symbolic parts in Type 3 systems is collaboration rather than only functional dependency in Type 2. For instance, 84 presents an abductive learning framework which conducts sub-symbolic perception learning and symbolic logic reasoning separately but interactively. Many deep learning-based program synthesis algorithms that leverage deep learning techniques to generate symbolic programs/rule systems satisfying high-level task specifications also fall in this category. Let me read that again. Many deep learning-based program synthesis algorithms. So we have algorithms that can synthesize programs using deep learning that leverage deep learning techniques to generate symbolic programs/rule systems. So maybe this is like code generation to some extent. Satisfying high-level task specifications. So you have these symbolically defined high-level task specifications also fall in this category. So I'm not sure if I have that right, but in my head, you can think about you have this specification for some code, and you're kind of going back and forth with the deep learning, statistical neural network generation, but then also following the symbolic step-by-step routines. So maybe that's how you think about it more as a coroutine rather than React, which uses LLMs as a subroutine of a symbolic routine. Another notable case is 18, where a neural perception module learns visual concepts and a symbolic reasoning module executes symbolic programs on the concept representations for question answering. The symbolic reasoning module provides feedback signals that support gradient-based optimization of the neural perception module. Again, the symbolic module, right? Yeah. So another notable case, 18, there's a neural perception module, so we're using a neural network to perceive things. It's learning visual concepts, and a symbolic reasoning module is executing programs on the concept representations for question answering. So maybe this is like you have a video stream going, and it's coming into a neural network which is perceiving the visual, and it's learning concepts from the visuals. So maybe it's learning the concept of car or day and night, things like this. And you have a symbolic reasoning module which is executing programs on the concept representations for question answering. So maybe something like executes programs on the concept representation. So we've extracted these representations, let's say, of day and night. This visual, the neural network connected to our video can determine whether it is day and night. So now we're executing programs on the fact that it's night for question answering. I'm confused a little bit about if the intent is for the user to question and for the machine to answer, or for the program to sort of query the concepts. I think it's user based. So then I could go type in, is it day or is it night? And because we've used the neural network to determine these concepts and it's got the stream going to the neural network, now our program can execute functions on these concepts, and it can spit out, oh, the neural network says that the video is of night, so now we know that it's night. The symbolic reasoning module provides feedback signals that support gradient-based optimization of the neural perception module. So the way I interpret that is, in some sense, let's say it's actually day, but the system says it's night. Then perhaps we could downvote this response and do some reinforcement learning with human feedback and negatively weight that response so that the model then knows to change the way that it's categorizing whether it's day or night via gradient-based optimization of the neuroperception module. Recent efforts in neurosymbolic reinforcement learning also belong to type 3. For example, in 79, symbolic planning are integrated into reinforcement learning for robust decision making. Symbolic plans are used to guide task execution. Okay, and the task experiences are fed back for improving symbolic planning. So I'm not gonna decode all this because I got a lot to get through. It is better to learn right when you're kind of talking out loud and thinking about it, but I'm trying to get through these papers. So let's see if my British guy is working now. I think he'll work. Okay, at least for this page, and it looks like for the next page. Okay, he'll be working for a while, except for that page. All right, I'll be back.
For example, in 79, symbolic planning are integrated into reinforcement learning RL for robust neural decision-making .network. Symbolic plans are used to guide task execution, and the task experiences are fed back for improving symbolic planning. Some other examples include neural theorem provers NTPs, Neurologic, conditional theorem unit, Provis unit, CTPS 87, NL prolog, deep prolog 89, Neurolog 90, difflog 91. Among them, a notable case is deep prolog 89, which adopts neural networks as predicates to compute the probabilities of probabilistic facts, and hence uses the inference mechanism of prolog 129, a probabilistic logic programming language based on first-order logic, to compute the gradient of the desired loss. Type 4. Symbolic neuro, also referred to as symbolic compilation into neural topology, figure 6, in a type 4, NESI system, symbolic rules, knowledge, are compiled into the architecture or training regime of neural networks. See, compile, training data, symbolic knowledge, neural network, table 3. For instance, there is a recent surge of interest in learning vector-based representations of symbolic knowledge. For instance, there is a recent surge of interest in learning vector-based representations of symbolic knowledge so as to naturally incorporate symbolic domain knowledge into connectionist architectures 97, 103, 111, 124, 125. A few neural symbolic mathematics systems for equation solving 98, 99, and verification 100 represent mathematical expressions as trees, which are used as training data. A family of visual question answering models 19, 101, 102, 104, 110 generate and execute symbolic programs for answering questions, where the programs are implemented as fully differentiable operations and/or neural networks. Some studies 123, 126, 127 attempt to incorporate domain knowledge as logical constraints in the output layer to ensure that the output adheres to specified logical constraints, while in 128, a tractable probabilistic model is proposed as the input layer to impose lexical constraints in autoregressive text generation models, e.g. GPT-2 130. A huge body of recent algorithms 121 leverage graph neural networks GNNs to embed entities and relations in external knowledge bases, so as to boost the performance in various applications, tasks in computer vision and NLP. Broadly speaking, these methods fall into this type, as suggested by Kautz, while some may argue that the reasoning ability of GNNs is rather weak. Type 5. Neurosymbolic, also referred to as symbolic integration in loss function figure 7. This type of NESI systems turns symbolic knowledge into additional soft constraints in the loss function used to train DNNs. Thus, the knowledge is compiled into the weights of DNNs, see table 4. Some other neural network, symbolic, IEEE transactions on pattern analysis and machine. Recent efforts in this direction include 146, logic tensor networks LTNS 133, and logistic circuits 134. As prominent neuro examples, translate logic first-order logic formulae, unit. As fuzzy relations on real numbers for neural computing, so as to allow gradient-based sub-symbolic learning. The core idea is to relax Boolean first-order logic as soft fuzzy logic, which deals with reasoning that is approximate instead of fixed and exact. In fuzzy logic, variables have a truth degree that ranges in 0, 1, 0, and 1, meaning that the variable is false and true with certainty, respectively. 153. LTNS approximate non-differentiable logic connectives, i.e., and quantifiers, i.e., with differentiable fuzzy logic operators. 141. In this way, logic rules can be embedded into network learning objective for end-to-end training. A trend of approaches consider class hierarchies when designing classifiers. 147, 148, where the class hierarchies act as both classification targets and background knowledge. They design different training objective functions to encourage the coherence between the prediction and the class hierarchy. For instance, in 21, compositional relations over semantic hierarchies are cast as extra training targets for hierarchical scene parsing. To efficiently compute losses, 139 proposes approximating the likelihood of the constraint on a local distribution centered around the model sample, rather than enforcing the constraint on the entire distribution. Type 6, neurosymbolic. Also referred to as full hybridization of neural and symbolic components, figure 8. Type 6 system, which Kautz believes has the greatest potential to combine the strengths of logic-based and neural-based AI, are fully integrated systems that directly embed a symbolic reasoning engine inside a neural engine. By imitating log, neuro unit, figure 8, type 6, neurosymbolic. Also referred to as full hybridization of neural and symbolic components, eigen reasoning with tensor calculus. A line of approaches learn the execution of symbolic operations through neural networks. 151, which to some extent can be classified into type 6, see table 4. Yet, their symbolic reasoning ability is still relatively weak. Kautz views type 6 methods as computational models of Kahneman's system 1 and system 2, and further addresses that type 6 methods should be capable of combinatorial reasoning. From Kautz's viewpoint, it seems that there is no NESI approach to date that can truly meet the standard of type 6. 4.3 knowledge representation. After clarifying and categorizing the main ways in which symbolic and deep learning approaches are integrated together in this area, we turn next to symbolic knowledge, based on which symbol manipulation, logical calculus can be carried out. Understanding symbolic knowledge serves as the cornerstone of an NESI system. Hence, a new categorization dimension for NESI approaches emerges purely from the perspective of how symbolic knowledge is represented. As illustrated in figure 9, the representation approaches for symbolic knowledge can be classified into 5 main groups: knowledge graph, propositional logic, first-order logic, programming language, and symbolic expression. Hence, this section is structured according to such these different categories of knowledge representations. Knowledge graphs, as a popular and effective tool for knowledge representation, contain a large amount of entities and the relationships between them. Knowledge graphs are typically directed, labeled graphs. Logic unit. IEEE transactions on pattern analysis and machine intelligence. 9. Cat. Animal, eat, knowledge graph. Polio, mouse, vaccine, cause 0.98 ability dice. Propositional logic. Proposition A, cat is an animal. Proposition B, cat is a living thing. A B. First order logic. Cat is an animal. Machine locale go state look left. X, cat X, animal X, running robot move. Formed by representing entities, e.g., people, places, things, predicate, a statement, due to the simplicity of propositional as nodes and relations between entities. E.g., is a friend logic. Many early NESI systems, such as 30
One, two, one, two, one, two, one, two, one, two. Okay, I'm back. So, knowledge representation. We're talking about knowledge graphs. I'll just start from the top of this section. After clarifying and categorizing the main ways in which symbolic and deep learning approaches are integrated together in this area, we turn next to symbolic knowledge, based on which symbol manipulation / logical calculus can be carried out. Understanding symbolic knowledge serves as the cornerstone of a NESI system. Hence, a new categorization dimension for NESI. Sorry, I'm chewing gum. Okay. Understanding symbolic knowledge serves as the correspondence of a NESI system. Hence, a new categorization dimension for NESI approaches emerges purely from the perspective of how symbolic knowledge is represented. As illustrated in Figure 9, the representation approaches for symbolic knowledge can be classified into 5 main groups: knowledge graph, propositional logic, first-order logic, programming language, and symbolic expression. Hence, this section is structured according to these different categories of knowledge representations. Knowledge graph. Knowledge graphs, as a popular and effective tool for knowledge representation, contain a large amount of entities and the relationships between them. Knowledge graphs are typically directed labeled graphs formed by representing entities, e.g. people, places, things, as nodes, and relations between entities, e.g. is a friend of, is located in, is a, as edges. They contain facts that are represented as SPO triples: subject, predicate, object, where subject and object are entities and predicate is the relation between them. Edges are directed from subject to object, and edge labels represent different types of relations. So in this example here, you can see you have cat, and since it says edges are directed from a subject to an object, cat eats mouse. At least I think that's what that says. And cat is an animal, mouse is an animal. So back where we were, edges are directed from subject to object, and edge labels represent different types of relations. In an unweighted graph, all edges have the same weight. In a weighted graph, each edge is associated with the number representing its weight. The edge weight quantifies the strength and the sign of the corresponding relationship between nodes. Please refer to the first two examples in Figure 9. A considerable body of works in computer vision and NLP fields build weak NESI systems upon knowledge graphs. Their knowledge graphs are frequently built upon our world knowledge. Since we humans understand the world by components, graphs are naturally used to represent relations between visual entities in the field of computer vision. Many famous computer vision datasets, such as ImageNet and Cityscapes, are released with structured / hierarchical annotation. For example, the ImageNet labels are organized according to WordNet. A family of visual parsing algorithms are developed for interpreting the part of compositional relations in common visual scenes or human object-centric visual stimuli. These methods fall into a broader field of machine learning called hierarchical classification, which is devoted to class taxonomy-aware classification. Propositional logic. Logical statements provide a flexible declarative language for formalizing knowledge about facts and dependencies, hence playing an important role for the integration of prior knowledge into connectionist architectures. Propositional logic, also known as Boolean logic or sometimes zeroth order logic, is the simplest form of logic, where all the statements are made by propositions. A proposition is a declarative statement that is either true or false. Propositional logic studies the logical relationships between propositions, which are connected via logical connectives. Typically, logical connectives or operators, including conjunction, disjunction, negation, and implication, are used to create compound propositions or represent a sentence logically. Propositional logic allows for translating ordinary language statements, i.e., if A then B, into formal logic rules. A implies B. In propositional logic, simple statements that contain no other statement as a part, are treated as indivisible wholes. Hence, propositional logic does not deal with logical relationships and properties that involve smaller parts of statements, such as the subject and predicate of a statement. Due to the simplicity of propositional logic, many early NESI systems, such as 3536, consider the symbolic knowledge in the form of propositional logic. Recent work in this direction, blah blah blah, for instance, 138 derives differentiable semantic loss. It derives differentiable semantic loss from constraints expressed in propositional logic for improving the performance in semi-supervised classification. Interesting. I wonder how they do that. In the RODAR dataset, logical constraints are incorporated into agents, actions, and locations which reflect real-world conditions, e.g., given an autonomous driving scenario containing a traffic light, TL, one such requirement is that a traffic light cannot simultaneously display both red and green signals. This rule can be expressed in propositional logic as not red traffic light or not green traffic light. In 140, domain knowledge regarding monotonic relationships between process variables are incorporated into deep neural networks training. Considering a function h of x equals y such that x1 is greater than x2 implies h of x1 is greater than h of x2, then x1, x2, and h of x1, h of x2 are said to share a monotonic relationship. First order logic. Propositional logic is a finitary system that only involves a finite number of propositions and does not require sophisticated symbol manipulation operations, i.e. substitution and unification, which are needed for nested terms. Thus, it is relatively easy to implement propositional logic programs using deep neural networks. However, the expressive power of propositional logic is rather limited, since it cannot express assertions about elements of a structure. First-order logic, also called quantified logic or predicate logic, is an extension to propositional logic and more powerful. First-order logic can express the relationship between objects by allowing variables in predicates bound by quantifiers. Specifically, first-order logic augments propositional logic with two new linguistic features, viz., variables and quantifiers. Variables are introduced to refer to objects of a certain type, i.e., domain of discourse, and can be substituted by a specific object. The universal quantifier, all, and existential quantifier, exists, allow us to quantify over objects. See examples in figure 9. What they got. So cat is an animal. For all x, cat x implies animal x. Everybody has a father. For all x, there exists a y such that father of y x. A few solutions have emerged to enable deep neural networks to represent first-order logic. However, most of these solutions can only handle restricted fragments of first-order logic. For example, some NESI systems turn to data log for logical reasoning, or leverage graph neural networks to reason over local subgraph structure for inductive relation prediction, or regularize distributed representations via domain-specific logic rules. To capture the full expressive power of first-order logic, some approaches use fuzzy logic to translate prior knowledge expressed as a set of first-order logic clauses into extra training objectives. In 85 and 92, first-order logic rules are compiled into differentiable operations. Another group of approaches use first-order logic to generate a random field based on Markov logic networks. Some other approaches adopt Prolog, a logic programming language, for knowledge representation. It shall be noted here that due to the conflict between the infinitary nature of first-order logic, allowing the use of function symbols as language primitives, and the finiteness of deep neural networks, it is much harder to model first-order logic in a connectionist setting compared with propositional logic. Programming language. Programming language, such as logic language Prolog and action language BC, is a family of formal language used for writing computer programs and communicating with machines. Typically, they consist of syntax and semantics, where syntax represents rules that define the combinations of symbols, and semantics assigns computational meaning to valid strings formulated with respect to the syntax. A set of NESI methods store knowledge in programs to execute. For example, 80 and 81 formulate domain knowledge in action language BC to perform long-term planning, performs a type-directed search over the library composed of parameterized programs defined in the Houdini language for concept reusing in other tasks. Note that for the NESI systems that adopt Datalog or Prolog, a subset of first-order logic for knowledge representation, they are classified into the group of first-order logic along the dimension of knowledge representation. Symbolic expression. Symbolic expression here roughly refers to other types of knowledge representation other than those mentioned above. Representative examples include mathematical expressions and specific symbolic sequences generated from some informal symbolic systems with self-defined rules. For instance, in 97, the source symbolic strings can be arbitrary forms of algebraic or logic expressions. In 98 to 100, learning and reasoning are conducted in conjunction with mathematical equations, which are typically translated into a syntax tree according to the grammatical or structural knowledge. Apart from that, 71 to 73 decompose the generation of complex program into multiple predefined operators and combine them together afterwards, which improves the accuracy and can be applied to different domains by simply extending the set of symbolic operation. This kind of compositionality is also a notable case of NESI in symbolic reasoning. Okay, can I select the page right? No, I can't. That's terrible. How much longer is this? Okay, it's pretty long. Not too bad, but I'm gaining from reading it, so it's fine. I just might not read the next paper then. Okay. Where are we? Knowledge embedding. Okay. After studying how the knowledge is represented in NESI, we focus on the dimension of knowledge embedding, which addresses the question of where in the neural network-based connectionist solutions the symbolic knowledge is embedded. Answering this question renders us a more profound understanding of the integration of symbolic knowledge and neural networks in modern NESI systems. Our literature survey revealed that modern NESI solutions are able to embed symbolic knowledge into training data, sub-symbolic representation, connectionist architecture, and neural inference, corresponding to the key element of the connectionist pipeline. Note that Type 1, Type 2, and Type 3 NESI systems are not discussed here, as they either do not take symbolic knowledge into consideration, Type 1, or adopt an independent symbolic model for exploiting knowledge, Type 2 and Type 3, whereas Type 4, Type 5, and Type 6 NESI systems, the knowledge can be simultaneously integrated into different components of the neural pipeline. Data. A natural strategy to embed knowledge into connectionist approaches is to straightforwardly embed it in the structure of data. A prominent approach is to translate symbolic expressions such as computer programs, molecular structures, mathematical expressions, logic formulae, into a structured, typically tree or graph organized, symbolic sequence with respect to the corresponding grammars, semantics, and or the relational structure of the knowledge. The advantage of this knowledge embedding strategy is the tremendous relief of burden on the engineering of network architecture and training objective. Off-the-shelf sequence-to-sequence networks and graph node networks can be directly applied. A few Type 4 NESI systems adopt this strategy. However, such simple strategy has its limits for embedding complex knowledge. Sub-symbolic representation. Type 5 NESI systems embed symbolic knowledge into the distributed representation by means of training objectives that are specialized to the knowledge. A common way of building such knowledge-specialized training objectives is to make discrete symbolic operations differentiable. Designing appropriate loss functions for distributed encoding of symbolic knowledge is appealing, as it does not require architectural change to the connectionist models or extra load of pre-processing the input data. However, it appears to be particularly challenging, for example, when encoding highly abstract symbolic knowledge such as compositional generalization. Moreover, there is no guarantee that distributed knowledge embedding can always lead to valid outputs that are coherent with the symbolic knowledge. Network architecture. Another common way to integrate knowledge into deep neural networks is to design the network architecture to reflect the structure of the knowledge. For instance, graph neural networks are widely adopted for capturing the complex relations in knowledge graphs and graph-structured symbolic expressions. In 112 and 113, compositional relations between visual entities are explicitly encoded into differentiable network layers/models. Although this strategy is adopted by many Type 3 systems and is believed as the key building block for Type 6 systems, it requires significant engineering efforts in neural architecture design. Neural inference. Embedding symbolic knowledge into network feed-forward inference is also a feasible way, which imposes explicit constraints to force the final hypothesis to agree with the knowledge. For instance, 94, 95, 99 generate both syntactically and semantically correct predictions of molecular structures by parsing a feasible path from a tree-structured knowledge space. 152 packages logical constraints into an iterative process and injected into the deep neural networks in a form of several matrix multiplications so as to bind logic reasoning into network feed-forward prediction. Those two papers ensure that no hierarchy violation happens in the hierarchical multi-label classification at inference time. 126 combines exact probabilistic inference with logical reasoning, guaranteeing that predictions are always consistent with constraints during inference for structured output prediction. 127 applies multiple inference rules that ensure compliance with requirements given the available knowledge about propositional logic requirements and data points. 166 and 167. Damn, how many references can one paper have? I feel like I'm reading off half numbers. Okay, whatever. Unveil effective algorithms using logic constraints that empower neural language models to produce articulate text while meeting intricate lexical requirements. So here we have this figure which shows examples. Scientific discovery. They're making a graph out of I think that's it's an amino acid structure. We have robotics and control. I'm sorry, but the text is very blurry, so I can't really read that. There's some sort of instruction, and it moves through these sequence of steps, it seems. We have programming systems, telling it to write a function, giving it an example, and it's generating a function. Question answering, using a graph. We have vision, language, analysis, and reasoning, again using a knowledge graph. Visual scene understanding, where these items are broken up into a hierarchical structure where you have plate and fork. And as you get higher up, you get to things like object, animal. Mathematical reasoning. There's a problem, there's an equation, solution, and argumentation. Patient has something, so it seems like the orange highlighted objects have some sort of latent or explicit knowledge representation. I'm not entirely sure. Functionality. It is clear that the ultimate goal of NESI is to implement a powerful AI system with combined capabilities of both data-driven learning and knowledge-driven reasoning. However, most NESI systems are either good at learning or good at reasoning, but rarely both. To better understand the strengths and weaknesses of the systems, we examine the current NESI systems from another dimension, core functionality. This dimension reflects whether the systems focus more on statistical learning or on symbolic reasoning. Learning. Some Type 3 NESI systems, like those Neurosymbolic RL approaches, and the vast majority of Type 4 and Type 5 systems, usually exhibit strong learning ability but are relatively weak at logic reasoning. For example, Neurosymbolic reinforcement learning approaches and visual reasoning algorithms of Type 4 are typically limited to a small set of predefined and simple programs or operations, and the sequences of the programs are usually generated through deep neural networks. For those Type 4 systems based on knowledge embedding or training regime modification, and Type 5 systems that integrate logical knowledge as additional constraints in the loss function, they pay more attention to symbolic knowledge embedding rather than performing logic reasoning. As the symbolic knowledge is only implicitly encoded into the weights of deep neural networks, they struggle with explicit reasoning, and their explainability is also weak. Reasoning. Generally speaking, most Type 2 NESI models and a few Type 3 systems that are built upon statistical relational learning and logic programming retain the main focus on the manipulation of the symbols and thus yield relatively strong reasoning ability rather than statistical learning. Again, most Type 2 and a few Type 3 that are built upon statistical relational learning and logical programming retain the main focus on the manipulation of the symbols and thus yield relatively strong reasoning ability rather than statistical learning. And I think that makes sense because when I was going through the types, I believe I associated, well, let's just see. Type 2, symbolic neuro, like AlphaGo. Okay, it makes sense that AlphaGo is... Does it make sense that AlphaGo is put into a category that's described as more focused on symbols than learning? Perhaps. I don't know too much about its internals. Type 3, which... Okay, but then also... I believe I put React into Type 2. And Type 3 is self-driving cars, I think. Hybrid system. Oh, okay. The coroutines. What was the example I used? Oh, yeah, like a coding assistant or something like that. Okay. I think this makes sense. I don't know enough about AlphaGo, but if I characterize Type 2 as React and Type 3 as a coding assistant, which might be the wrong examples to use, but for now, if I'm categorizing it like that, then it makes sense to me to describe them as more focused on reasoning rather than statistical learning, manipulation of symbols rather than the ability to continuously learn. In particular, for the Type 2 NESI systems, the neural part is only involved as a sub-module, while the whole system acts as a symbolic model. For those logical programming-based Type 3 systems, they allow for differentiable logical inference over probabilistic evidence from neural networks. However, their scalability is typically limited. In a related vein, informed machine learning focus in particular... Now that I think about it, I don't think coding assistant is the right characterization for Type 3. It actually might better be suited to Type 1. But anyway, I just wanted to say that so as not to be confusing. But anyway, yeah. For those logical programming-based Type 3 systems, they allow for differentiable logical inference over probabilistic evidence from neural networks. However, their scalability is typically limited. In a related vein, informed machine learning focus in particular on how to integrate prior knowledge into deep neural networks. On the one hand, the findings about the reasoning capability of NESI methods may stimulate the potential of models learned by informed machine learning. On the other hand, the advances in informed machine learning, e.g. knowledge source, representation, and integration, offer invaluable references for the development of NESI systems. I'm going to read that part again. For those logical programming-based Type 3 systems, they allow for differentiable logical inference over probabilistic evidence from neural networks. Okay, you're inferring differentiable logic from the probabilistic evidence from the neural network. However, their scalability is typically limited. In a related vein, informed machine learning focus in particular on how to integrate prior knowledge into deep neural networks. On the one hand, the findings about the reasoning capability of neurosymbolic methods may stimulate the potential of models learned by informed machine learning. On the other hand, the advances in informed machine learning, e.g. knowledge source, representation, and integration, offer invaluable references for the development of NESI systems. Okay. Reasoning and learning. Despite the recent progress, it is still hard to achieve a compact NESI system that has both strong logic reasoning and expressive statistic learning abilities. In the sense of Cox's vision, Type 6 symbolic systems would have such combined abilities. However, there are only a few models, 149 to 151, can be barely recognized as Type 6. I wonder what these are. What page am I on? 11? Oh, they're not hyperlinks. Whatever. 5. Application areas and tasks. With the ambitious goal and recent rapid progress of NESI research, various novel applications and tasks have emerged across different domains, such as computer vision, NLP, robotics, and even other scientific disciplines. In this section, we will showcase some of the prominent application examples that illustrate the potential and impact of NESI. However, we note that due to the high diversity of the application scenarios and the significant difference among different NESI systems, it is not feasible to provide a comprehensive and fair evaluation framework for all the NESI systems under a unified setting. Furthermore, we provide a variety of popular PyPy packages that can assist in building more complex NESI systems. See Table 5. So for example, you have LTN, which is a differentiable first order logic as a key feature, dependency both PyTorch and TensorFlow. That's how to install it, and that's the link. Let's see, what features do I care about? Programmatic constraint specification could be interesting. Background knowledge injection could also be interesting. Probabilistic logic programming, these all are interesting. Universally quantified FOL clauses, not sure what that is, and it uses TensorFlow, so screw it. Differentiable logic programming uses Java, I don't care. I mean, like, I don't care about it because I hate Java, but I don't really care. Explainable deep learning models, Torch Explain, interesting too. I'm gonna make a note. Well, I'll take a picture of this. So, scientific discovery. Scientific discovery typically requires algorithms that discover scientific hypotheses or concepts from data and respect physical constraints. Hold up. Is this? No, it still won't work. How much more do I have to go? Okay. Let's push. Let's push through. Scientific discovery typically requires algorithms that discover scientific hypotheses or concepts from data and respect physical constraints and domain-specific knowledge that are known to hold in the world. Moreover, the algorithms should better interpret and explain how they come up with their solutions and convey their insights to human scientists. As a result, scientific discovery poses great challenges for current pure data-driven AI techniques, yet serves as a good testbed for NESI. Several recent studies showed the extraction of symbolic models from experimental data of mechanical systems, and in astronomy. For instance, the authors of 119 apply a symbolic regression technique to a graph neural network model that is trained on cosmological dark matter data and demonstrate that explicit physical relations can be discovered in the form of analytic formula. For protein structure prediction, 171 applies the gradient descent algorithm to uncover the graph structure of proteins in 3D space, where the edges of the graph are determined by the proximity of residues. Moreover, some recent works employ neurosymbolic programming to analyze the behavior of laboratory animals, such as classifying sequential animal behaviors, clustering animal behaviors in an interpretable way, and representing expert knowledge in a reusable domain-specific language and more general domain-level labeling functions. In addition, NESI techniques are applied to retrosynthesis and reaction prediction in organic chemistry. For example, 175 combines Monte Carlo tree search with an expansion policy network to discover retrosynthetic routines. 94 adds syntax and semantics checking during molecule. I know that there must have been so many authors on this paper, because how does one person cannot read this many papers and still be a productive individual? There's just so many references. So 94 adds syntax and semantics checking during molecule synthesis. 176 devises a conditional graph logic network. You know what I just thought about? Maybe they could if they're doing what I'm doing and they got the Speechify going, but I hope that they read it a little bit deeper than that. 176 devises a conditional graph logic network to learn when to apply rules from reaction templates, implicitly considering both the chemical and strategic feasibility of the resulting reaction. Programming systems. Program synthesis is another important application domain of NESI. The goal is to automatically generate programs from high-level task specifications. The specifications are typically hard logical constraints, for example, test cases that need to be satisfied exactly, pre-post condition pairs, or temporal logic formulas. The programs are structured, symbolic expressions that follow the syntax of a domain-specific language. NESI tools are more suited for this domain than purely neural alternatives by virtue of their modularity and use of symbolic primitives. To combine neural learning with the formal logic constraints of programming languages, NESI-based programmers typically learn input and context-specific heuristics from large-scale data and use such heuristics to guide search-based symbolic methods to guarantee soundness. For example, given some tokens that indicate the desired program functionality, such as API calls, types, or keywords, 177 generates strongly typed Java-like source code in 2 steps. First, it learns neural models to produce sketches of programs, which are abstract representations of program syntax that omit low-level details. Second, it concretizes the sketches into type-safe programs using a combinatorial search procedure. 180 utilizes a combination of deep neural networks and stochastic search to parse drawings into symbolic specifications. These specifications are then fed into a general-purpose program synthesis engine to infer a structured graphics program. 179 introduces the concept of neurosymbolic attribute grammars, which combine a stochastic context-free grammar with semantic attributes computed by static program analysis. The neural network learns to condition its generation actions on these attributes, which provide useful semantic clues and long-distance dependencies. Question answering is a long-standing AI task that aims to build intelligent systems that can automatically answer questions from humans in natural language, typically with the aid of a knowledge source composed of unstructured text corpora and/or structured concepts. Answering complex questions that involve multiple subjects, compound relations, and numerical operations is a grand challenge in QA. To address this challenge, NESI-based QA systems have been recently developed, typically following either a semantic parsing paradigm or a knowledge embedding paradigm. Semantic parsing-based methods learn to translate a question into a symbolic logic form by conducting semantic and syntactic analysis, and then derive the answer by executing the parsed logic form against the knowledge source. For example, 73 adopts a neural sequence-to-sequence model that maps language utterances to programs and utilizes a key variable memory to save and reuse intermediate execution results for supporting language compositionality and complex semantics. Then, a symbolic Lisp interpreter is used to perform program execution over the knowledge source and helps find good programs by pruning the search space. Knowledge embedding based methods learn and store neural representations of the knowledge source and then retrieve the answers from the stored neural form of the knowledge source, considering the information conveyed in the questions. For example, 181 builds a fact memory that encodes the entities of a knowledge source as numerical vectors and provides a contextualized reference for a neural language model to create answers. Overall, semantic parsing-based NESI QA systems can produce a more interpretable reasoning process by generating expressive logic forms. However, they heavily rely on the design of the logic form and parsing algorithm, which turns out to be the bottleneck of performance improvement. As a comparison, knowledge embedding based NESI QA systems enjoy more benefits of end-to-end training, but lack traceable reasoning. Okay, I a little bit don't care about vision, robotics, and visual, and I care about mathematical reasoning, so I'll read that. Mathematical reasoning as a distinct and specialized capability inherent in humans. Mathematical reasoning has garnered substantial attention within the AI community. This multifaceted skill encompasses linguistic reasoning, visual reasoning, common sense reasoning, logical reasoning, numerical reasoning, and symbolic reasoning. Human approach to understanding and solving mathematical problems is not primarily rooted in experience and evidence, but on the basis of learning, inferring, and applying laws, axioms, and symbolic manipulation rules. The structured and reasoning-heavy nature of mathematical problems enables the construction of NESI-based solvers. For mathematical problem solving, 197-198 introduced tree-structured decoder to explicitly explore the abstract syntax tree of mathematical expressions and stimulate many follow-up efforts. For theorem proving, 200 considers syntax trees of formulas as graphs and apply message passing for higher order proof search for handwritten formula evaluation. 205 models the symbol solution states as a Boltzmann distribution, avoiding expensive state searching and facilitating mutually beneficial interactions between network training and symbolic reasoning. For discovering faster matrix multiplication algorithms, 204 makes use of a Monte Carlo tree search planning procedure aided by deep neural networks. Argumentation. Argumentation, a distinctive cognitive capacity of humans, plays a pivotal role in managing diverse mental attitudes and navigating situations characterized by incomplete or inconsistent information. 206. The argumentation framework, which represents arguments and their relationships between them as a directed graph, excels in capturing and generalizing various forms of non-monotonic reasoning. 231, 232, essential for dealing with rules and exceptions that give rise to logical conflicts. The combination of this framework with the powerful computational capacity of the neural networks has led to advancements in computational argumentation. While early research in this field was predominantly built upon symbolistic models, recent NESI-based methods have made significant strides. These include translating argumentation networks into neural networks, exploring correspondences between argumentation frameworks and neural networks, and using networks to extract argumentation frameworks for subsequent symbolic and argumentative reasoning, e.g. ADA. 210 mines argumentation frameworks from text reviews and reason with them to provide movies recommendations. Furthermore, that's cool. So it takes film reviews as text and extracts argumentation frameworks from them for reasoning and recommendation. Furthermore, reasoning over argumentation frameworks can be integrated into neural networks as a form of inductive bias, as exemplified by argumentation Boltzmann machines. Recent developments in this field have also explored explanation robustness, such as counterfactual explanations in neural networks and multi-agent argumentation systems, which combine argumentation frameworks with distributed reasoning for decision making. So then they do a performance comparison, quantitative retrosynthesis prediction results on this benchmark test in terms of top K exact match accuracy. The 3 best scores are marked in red, blue, and green respectively. So the best is red, second best is blue, third best is green. Graph to edits, it's looking pretty good. Megan, when the K goes up, top K exact match accuracy. Interesting. So when you're seeing exact match for 50, Megan is doing pretty good. But when you just need one, just in general, they all go down, which makes sense. So we are looking at 4 NESI-based retrosynthesis algorithm. Megan, GLN, so NSR, these 4 on the bottom are NESI, neurosymbolic. Everything above it is pure neural. Interestingly, this paper came out in 2024. I wonder why they didn't use better neural methods. I don't know. Or even just better in general. I don't know too much about these methods, so I'll say that. But just interesting. I wonder how this would look if they threw the top performing models and tested it with this. So anyway, this is all fine and cool, but doesn't really matter anymore. I don't care about these benchmarks or this test. And this is performance benchmarking on a math word problem open challenges. I'll skim this. We have recursive neurosymbolic engine, testbed for metacognitive skills of Nessie, and Nessie in the big model era. Oh, up here we also have scalability, compositional generalization, automated knowledge acquisition. Okay, I care a lot about that, so I'm going to read this section. Symbolic knowledge serves as the foundation for developing a Nessie system. It influences the quality and scope of the system's reasoning capability. Nevertheless, most modern Nessie systems simply take the knowledge for granted, ignoring two crucial issues. How to acquire domain-specific knowledge that is required for the system, and how to ensure the completeness and adequacy of the knowledge for supporting the system's functionality. Given the aforementioned challenge of scalability, knowledge acquisition seems a bottleneck in the process of developing Nessie systems in large-scale and real-world application scenarios. This calls for the automatic acquisition of knowledge, preferably from different data sources. This is also closely relevant to the concept of learning to reason, which studies the entire process of learning a knowledge-based representation from examples, and then reasoning with that knowledge base by querying with similar examples. In fact, automated knowledge acquisition, which is essentially a problem in modeling a human expert's introspective capabilities, has experienced a long period history of development in the field of AI. Despite recent efforts in this direction are mainly restricted to the construction of conceptual knowledge graphs, we believe the integration of automated knowledge acquisition, symbolic reasoning, and subsymbolic learning will lead to more complete and powerful Nessie systems. Such an integration touches many fundamental challenges and aspects of Nessie and even AI, such as which kind of knowledge representation is more favored for building Nessie systems, how to abstract knowledge from data, how to build a close and mutual feedback loop between deductive reasoning and inductive learning, i.e. grounding knowledge onto data to guide the practice and updating knowledge according to the practical results. Okay. Interesting. Not a bad paper. I wish it was formatted better and that I could have had AI read that to me more than I had to, but it's fine. Learn some things. For now, I'm out. Peace.